1, 2, 2. So we're getting audio coming in.
Okay.
So now everything in the house will
So maybe
come in.
let me get down. And since I'm connected to the Zoom, I want to see that I hear you from outside. Here. Or how? Do you want? Don't say anything. So are we live on YouTube now? Uncheck. Are we live on YouTube now?
1, 2, 2.
Okay, so maybe you should join
Speakers are you having at a time?
just one.
Just one. Okay.
Just a speaker.
Great. The camera.
Hello,
please,
can you hear me?
Yeah, actually,
Hello, can you hear me?
Yes, I can hear you. Can you hear me?
Okay, very good. And then let me see if I needed to share my camera, but I don't think that will be needed. Let me
I'm
see
not
now.
hearing you very clearly. Let me see if I can send you out through the house. Can you try talking again?
Hello, 1, 2, 3.
Yep. Okay.
But I think this is going to be just a webinar, and so I don't think people are going to be, no one is giving a presentation through Zoom remotely. Everyone will be in person.
You're just
So
using Zoom to record.
I think what is needed is that I hear you well, and I think that's working.
So no video at all?
I don't think there will be, so we need to record the video. We need to record the video of the room and of the speaker, but you don't need to record video of me, who am now remote. That's what I mean.
Okay. Yeah, well, the way that Zoom works, it gets it records whoever's pinned, and then I believe it records one with all the participants on the other side of it. So you'll get 2 recordings.
This is working. I'll just go back to the room, okay?
Great. Yep.
Okay.
Yep.
I don't think there is remote question. Regarding the cameras, do we have only one or many?
You just have one camera, and it's that one right there.
Okay.
But it's a PTZ camera. It's just that
And
wherever.
once you set it, it's frozen, or do we have the
yes.
ability to control it?
It's static. Or
Okay.
it's not static, but the way we set it up, the bureaucracy deems it as such.
Yes.
So
I think it is better to have the camera. Adam, what do you think? In terms of the camera, it can be moved, but it's fixed once for the day or so. So do we just have it zoomed in to the podium, and that's it? I think that makes sense. Right, because otherwise is what you see, which is yeah. Yes, all right, exactly. So I think it's zoom in on the.
got it. All right, so I'm gonna go adjust that. Oh, I'm gonna have to go with that.
Yeah.
Okay. There are some things that okay. I think there's a lag in the screen, but I'll see it soon. Right. Yeah, that looks good.
How do we eliminate the?
here you can minimize this. Yep, yeah. I usually, yeah, so down there. Yeah, so there's not as books in this room, so he'll probably move this.
Yeah, perfect. So you're looking at the stream directly on the stream on
That's
YouTube?
YouTube.
Okay. So it's already being transmitted.
Yes.
But just for testing, I guess.
Yeah.
Then the other part is we're recording. So the other part is we're recording everything, right?
Yes, I think if you go live on YouTube, then there is a archive version of.
Okay, but we're maybe should we record ourselves as well?
We could. I can do right now.
Good. And this is my account, so you have a pro or whose account?
No, my account.
And how are you sure that it's not going to stop in 20 minutes?
It won't, because the C's has the Zoom account as a pro version, so I checked. Okay. It can last 30 hours.
30 hours. Okay. Excellent.
Can you all hear me?
Yes, we can. Yes.
All right, so can you pull up the camera just so I can see?
Over here.
Maybe this does not look so good here.
Okay.
We could have it, we just need a couple of bottles, I think. Like just have one bottle per speaker or two, and then you just keep changing throughout the day.
Yeah, we can just every
Let's
before
see
before
what
we
he
talk.
zoomed in. Zooms in. And then do we have a clicker for people if they need to? Otherwise, I think I put mine.
Okay, I always have mine also, but mine is a little old.
And so that one just goes there.
Okay.
Okay.
Oh,
Okay,
good.
so indeed we see the water. Profesor, buenos días. So. Okay, I'm looking into it. That looks good. Adam, do you think it should be more zoomed in or this is fine? Okay. Good. Yeah, that looks good. Okay, so we don't need to continue work that. So when it's beginning would be good. One.
Well, your event starts at 8:45. Yeah, well, just hang out and guess I think the boys. Thank you, bro. Cool. I think you guys are good. Perfectly come.
You're all set.
I just don't. It's really more like I don't want to.
I just,
But
right, but I, all the, my concern is what if anything breaks?
well, yeah, that's yeah. Totally.
Yeah.
I'll hang out with you're running the YouTube. Right? We'll both be at the same.
We are keep on both on,
Oh, okay. Well, I'll just hang out with you guys then.
yeah.
And then when you think you're comfortable, you tell me.
Kind of before I think.
And then there you.
Cameron? And went to lunch. Yeah, but I'm right across the border. Almost there, yeah. Okay.
Testing 1, 2, 3.
I think it's a. Okay,
Yeah,
maybe.
like turn up the volume.
Yeah. Okay, cool. Test 1, 2, 3.
Got it.
Test 1, 2, 3. I just since they turn off when you put them back in,
Testing.
Second.
Hello.
Yep.
So
Okay,
you want to use the podium mic? Yeah. Okay. Okay.
If I steal this water, should I go downstairs and grab
Oh,
it?
it's not stealing. Yeah, that's for yours. That's for you. All right, is it coming through? Am I?
Yes, yes.
Excellent. Okay, fantastic. All right, we'll give people one more minute. Something happened?
I'm not sure how you want to like.
I'll mention it. Okay, yes. Okay. No, no.
Oh, so that I can clean it up quickly.
Pleasure to meet you, by the way. I'm Adam. Thanks for coming. Give people another minute or two.
This talk is okay for these guys. I always get worried about talking about, interpretable models with the deep learning.
No, that's the point of this. I mean, we started this conference. Of like ML, neuroscience, science people who were, more and more and more. Are there still people outside or should we just go ahead? Yeah, sure. Yeah, so I'll just turn off all the stage mics.
Then to that end, maybe like, are you the MC/host?
Yes, for now.
So maybe like what I would recommend doing, muting the stage mics throughout, and then you would use the podium microphone. Then you can pass the lavalier to the presenter. And then for the question and A, on stage mics. Okay. Does that make sense?
Okay. All right. You got that? Yeah. Okay. Thank you.
So for you, it's just
Just talking to them. Yeah.
and that's all, and then you can.
I'll change it. All right, we should get started. Thank you all for coming. It's a pleasure to be doing DeepMath once again. This is the 6th year now that we're doing this. And so it's become, kind of tradition, let's see, to start off and let me blow off some steam, making some jokes the night before. So why deep math? Well, we're all enticed by this promise of deep learning and all the wonderful things that, it can do. It can play, games. It can talk to us when we're lonely and only have ChatGPT. But, then when we try to use it for very serious applications, right, reality starts setting in and, we are all familiar with adversarial examples, implicit bias, hallucinations, all the stuff that make it difficult to apply in certain circumstances. And, leads to us understanding that we don't quite understand all the nitty-gritty details of the full thing. So a lot of people have tried to figure this out. If you look in the literature, there's analogies to sparse coding, the brain, random forests, information bottlenecks, kernel methods. You can pretty much find anything. And so, what is the right way to think about deep learning? What is the right, process in which to mathematically understand the fundamentals? And, I think that's why those of us that started the conference and continued this conference, we really care about this, these sets of questions. So this, we figured this is probably going to be a long-term endeavor. It's probably going to take people thinking about deep math, right? Deep learning, deep neural networks, recurrent neural networks from multiple, directions. And, so when we started the conference, we really wanted to bring this in from a fundamental point of understanding from multiple directions. So bringing in mathematicians, engineers, physicists, computer scientists, cognitive scientists who have also been thinking about, big distributed systems for a long time. And thinking about all the different ways that we can quantitatively and theoretically understand real things about these systems like generalization, approximation, convergence, stability, and others. So it's been a while, but we're getting closer. So far, we're still got a little ways to go. But it's great to see continued interest and all of you coming and joining us and being a part of the effort to no longer draw 25 cards. So we have an amazing lineup of plenary speakers. So thank you in advance to all the speakers, and we'll thank you, of course, after as well. And so stick around for the 2 days. We also have a number of really great contributed talks and a poster session. So just to kind of give you an outline of the days. So today will be in here. The schedule is up on the website. I am in the process of trying to fix it for the mobile, but it is there. We'll get it working on mobile. But you can also download the booklet from the website, and that has the schedule as well. Oh, and yes, and there's a QR code. Thank you, Renee, on the back of your very fancy badges that also has a map. Way fancier than last year. So this will be the outline for the first day. So we have a number of plenary speakers. We have a lunch break, coffee breaks. So don't worry, we'll supply you with enough caffeine to make it through and attentive all day. And then tomorrow we will have a poster session in the morning. This will be at a different location, so check the online for the location. This will be at the Singh Center for Nanotechnology, so 3205 Walnut Street. And there we have a nice space for the poster session and the remainder of the talks. So links are all up here. And I do want to say a special thank you, to UPenn, Renee, and our other partners here at UPenn for hosting us and making, this wonderful space. And I would like to hand it off now to Renee to discuss more details. Thanks.
Good morning. Welcome to Penn. We're really delighted to have you all, and we hope that you have a great visit at the university. Just very briefly, a few things about logistics. So we are going to be here today for most of the day, except for lunch. So if you came from here is the entrance, we are now in this building. The restrooms are here in this floor. Coffee breaks will be both here as well as upstairs where you entered. But at lunchtime, you need to go one more floor up and then go around through this courtyard, and lunch will be in Levine Hall, which is on the other side here. So just remember that at our lunchtime. I think there'll be some of our volunteers helping you with the transition at that time. Remember also that tomorrow we're going to be in a different venue. It's just half a block from here, so have a look at the website. Other than that, I just want to thank all of the organizers, both here at Penn, Johns Hopkins, and many others. I also want to thank the sponsorship that we have received from the Office of Naval Research, as well as Johns Hopkins University and the Idea Center here at UPenn. Just going back, I think, to the map, tomorrow will be here, as I just said, is half a block. And that's it. Thank you very much.
Let me stop sharing so you can share.
No.
Yep. Oh,
Yeah,
I,
I'll do that thing.
you want this?
Sure. Which mic is better?
Both are the same. It's just that this one you can only stand around here.
All right.
Is it working? Is this mic still on?
No, I
Or
turned it off.
is? Oh, no, okay.
Yeah, I'm good.
Oh, okay.
You want to use it?
Yeah, just to present you, because, all right, I'll make this quick because this is an awkward way to do it. Our first speaker is Cynthia Rudin from Duke. We're very excited to have her, and she will be presenting work on interpretable models. So thank you very much for kicking us off.
Absolutely. Cool. Okay. Get myself situated here. I'm excited about this conference. I love the goal of it. Okay, sorry, this is some gymnastics here. Share. Present. Share. Okay, great. So yeah, I'm excited to be here talking about simpler models. All right, so my lab at Duke is called the Interpretable Machine Learning Lab. And one of my most important goals is to create machine learning models that are small enough to fit on an index card, yet are as accurate as the best black box models like deep neural networks. You're probably thinking, is this for real? Like, can you actually do this? Because this would mean a lot for trustworthy and fair machine learning if you could do this. And the answer is yes, we could totally do this for a lot of important problems. I mean, and now we think we know under what circumstances we could do it. You can't do it for computer vision or for language, but you can do it for many, many other problems. So let me give you an example. So a few years ago, there was a competition sponsored by FICO, which is the major credit scoring agency in the United States. It was also sponsored by Google, MIT, Oxford, Berkeley, and others. It was called the Explainable Machine Learning Challenge. And they gave everyone a data set about loan decisions, and they told everyone to create a black box predictive model and explain it, because they didn't think it was possible to create an interpretable model with the accuracy of a black box for this kind of like complicated data set. But several years after the competition ended, we figured out that there are accurate interpretable models. You just have to look for them carefully. All right, so just to tell you about this data set, it's got about 10,000 loan applications from a particularly difficult to classify subpopulation, and the goal is to use credit history to predict whether someone's going to default on their loan. Okay, now at the time, which was 6 years ago, nobody produced a really tiny interpretable model that was as accurate as a black box. But then 4 years ago, 4 years later, so about 2 years ago, we produced the first small models that performed as well as the black box models for this data set, because we had some very new powerful machine learning algorithms that could do it. And because the models fit on an index card, they fit on a PowerPoint slide. So I can actually show them to you, okay? So the first model that I'm going to show was produced by the algorithm that we call fast sparse, which creates sparse generalized additive models. And this is work done with Jiacheng Liu, Trudy Zhang, and Margot Seltzer. And it's an extremely fast coordinate descent method that minimizes the exponential loss with L0 regularization. And it has analytical solutions for the step size at every iteration, which makes it really, really fast because it's just zoom, 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 zoom. So let me show you the model that fast sparse produces on the FICO data set. Okay, so here's the model. So this is the whole fast sparse model for that data set. You just get a score for each of the features and you add them up. And it translates, the total score translates into a risk for defaulting on a loan. So let's take a look at some of the factors here. So months since oldest trade open, if your oldest trade is recent, you get more risk points. Okay, and if number of satisfactory trades is not so good, right? You only had a few satisfactory trades, then you get more risk points. And then look at this one, external risk estimate. Like this one is very sensitive here because you can see it's a really important feature because it has a lot of steps right in a row like that. And it's very sensitive between values sort of 60 to 80. But what's really shocking about this model, besides its simplicity in describing this like very difficult benchmark data set, is that we created the whole model in under 4 seconds. And that's how fast this algorithm runs on average for this data set. It's like 4 seconds. Okay, it used to be that finding high quality interpretable models was so computationally expensive that nobody could do it at all. And now we can do it in 4 seconds. So let me just show you a different type of predictive model for this data set. This one's going to be a sparse decision tree. Can you turn this mic off over here? Yeah, see if that Okay, great, thank you. Okay, whoops. I think I'm still picking up something from here. All right. Yeah, it's this guy.
No,
Maybe
but
not.
then this is the one for this, for this,
Huh, podium mic should be off, but
yeah.
it doesn't seem to
This,
be.
all the
And what's all that noise being created? Oh, well, maybe no, can you guys hear all that noise or not? Oh,
No.
perfect, okay, it's just me who hears it. Perfect, okay, great. So anyway, cool, so I'm gonna show you a decision tree, a sparse decision tree. It was created by the GHOST algorithm. So GHOST is generalized optimal sparse decision trees. And it was developed over the course of a decade. I'll put up pictures of the army of people that we've had working on GHOST. GHOST is very fast. It's like orders of magnitude faster than the previous algorithms for producing sparse optimal trees. And it's so much better than Carter C4.5 that produced trees from the top down in a greedy fashion, right? This thing optimizes the whole tree at once. So let me show you that. So this is the ghost tree for the FICO data set. So let's take a look at that. So if the external risk estimate is too high or too low, then you get the prediction, okay, right? Because default versus no default, right? But if you're in the middle here, if you're in the sensitive range, then you have to ask these more detailed questions, like how many months since the most recent inquiry, excluding the last 7 days, stuff like that. So I just want to point out how difficult this type of model is to create. Your algorithm has to figure out all kinds of stuff, including all of these thresholds, right? The 73.5 and the 70.5 and all that. Where to put each of the variables, so where these all are, even the shape and size of the tree, all of that has to be figured out by the algorithm. And it's actually computationally hard to do this. It's NP hard with no provable or with no polynomial time approximation. And yet this optimal tree was created by GHOST in 8.1 seconds. Okay, so this tree, this is actually the same tree as the previous slide. It's just done in a more artistic way by a friend of my collaborator, Margos, who's an artist. And it's kind of like this predictive, powerful predictive model growing in nature, right? I mean, I find interpretable models much more kind of natural than black box models, right? Black box models might be kind of snarls of branches or something. Here you've got something kind of elegant and nice. Okay, so what I've showed you is that even on competition data sets, we find interpretable models that are as accurate as the best black box models. So if people are not using interpretable models, what are they using? Okay, so they're using black boxes. And these black boxes, I define them as being too difficult for humans to understand, or proprietary, which means you're not allowed to understand them. All right, so what's wrong with black box models? Well, they're difficult to use in practice. So here's an example of, this is a newspaper article about someone whose risk score was calculated wrong before his parole hearing, and he was denied parole and he had to spend an extra year in prison. There was a typographical error on his criminal history features. Okay, and so, that's really not the way we want our criminal justice system to work. Like, typos should not be making decisions, right? People spending a year in prison because of a typo, that's embarrassing. Black boxes are difficult to explain. So if I get denied a loan and I can't purchase a house, I actually want to know why. I don't just want some crappy explanation of a black box. Black boxes are difficult to troubleshoot. Here's an example from healthcare where a model for intracranial hemorrhage was approved by the FDA, launched into the real world, didn't work, and no one knows why because it's a black box. So healthcare's a huge can of worms. It deserves its own slide because it causes so many issues. Like, you often have this situation where the model's right, but for the wrong reasons, like because of some correlation. You're working on high stakes decisions in healthcare. You don't really want to trust those high stakes decisions to a tool that doesn't really understand the whole situation. Troubleshooting becomes harder. You can't second guess the reasoning process of a black box because you don't know it. Is it going to work if I switch equipment? It's going to work for all types of patients. What about my current patient? Is the information that I fed into the system even correct? right? All this stuff becomes difficult when you use a black box. Issues of responsibility. It's the doctor's responsibility to make a good decision. So there's this like accountability issues, you know? Whose decision is it? Who's making this decision, the human or the machine? So basically, black box models in these situations turn what would be computer-aided decisions into automated decisions. So black box models really shouldn't be used in many healthcare decisions, if at all possible. So if black boxes are bad, why do people use them? Well, first of all, they don't believe that interpretable models can be as accurate as black box models. They say there's this accuracy interpretability trade-off, and it doesn't matter how many examples you give them, right? It doesn't matter how many FICO examples you give them. When a new problem comes along, they still go, this is probably something that needs a black box. Right? And I can understand this from domains that really benefit from neural networks, like computer vision or for speech. But even if it's a domain that's never benefited from more complex models, they still think this. And second, you can sell a black box. People like black boxes, right? Black boxes can be someone's secret sauce, right? You can't really sell something that fits on an index card, right? You got to sell the mechanism to collect all the data from patients and combine it and so on. And then the third reason is that interpretable models, well, people say they are hard to create. I want to convince you that they were hard to create, right? I'm working hard at that, right? Showing you these algorithms that can create models in just a few seconds, right? So I'm not sure if I can handle the politics on the secret sauce bit, but I can definitely help with the first one and the third one. So I'm going to keep discussing the third one for a while. All right, so I think a key reason why interpretable models are hard to construct is because of something that I call the interaction bottleneck. And this arises when people realize that interpretable models have interpretable flaws and they need to fix them. So let's say that a doctor uses data to produce an interpretable model, and the doctor looks at the model, which is now possible because they can understand it, and they find that it doesn't align well with what they know about medicine. So what do they do about it? Right? The machine learning algorithm gave them the model. So now they're stuck. Right? The doctor's stuck. So even if there were hundreds of millions of equally accurate models, the algorithm returned only one of them. Right? And these models, they're all equally accurate with respect to the data. There's no way using the data that you could figure out which one of these is the right one. Right? The only way to tell the difference is with domain knowledge, but there's no easy way to put the domain knowledge into the algorithm. Right? This is the real problem. You know, and doctors don't even know in advance necessarily what information they want to put into the algorithm. If they had, they would have done it in the first place. Right, so yeah, so this is the problem. There's no feedback loop, right? Machine learning algorithms only return one model at a time. And interacting with machine learning algorithms is a problem that the standard machine learning framework is just not equipped to deal with. So I think we need a entirely new paradigm for machine learning at this point, right? I think machine learning is just totally broken here. Okay, so my collaborators and I decided that the standard machine learning framework had to go. So we proposed a new paradigm for machine learning, something that was like more human-facing than the standard machine learning, which is to hand the user all good models from a given function class, right? Not just one. Give them all of the good models and let them choose which model they want so they can pick something that doesn't just agree with the data, but also agrees with their domain knowledge. And, you know, then they might actually use it. And so we call this set of good models the Rashomon set. Now, I'm going to point out that doing this is extremely technically difficult because finding even one sparse model is provably hard. But now I'm saying we've got to find all of these models. We have to store all of them, even if there are hundreds of millions of them. And we have to visualize them so that the user can choose from them. So it's not easy from a technical perspective, but it's extremely useful in practice. And it changes the whole notion of machine learning from just optimization-based to being also about enumeration of all of these models and visualization of them. Okay, so I'm going to show you an example of this because we now have the first algorithms that compute the whole Rashomon set for non-trivial function classes. And so the first algorithm that did this is for sparse decision trees, and it's called tree farms. So I'm just going to show you this is an example of a ghost tree. This is a tree from the ghost algorithm I showed you earlier on a criminal recidivism data set. So this one says like, if you have more than 3 prior offenses, then predict arrest within 2 years of your score being calculated at the police station, otherwise blah, blah. Okay, so this is just one tree. And the new algorithm, Tree Farms, finds not just one optimal sparse tree like ghost, it finds all of these optimal and slightly suboptimal trees. And it does this for any reasonably sized data set, and it displays them in an interface called TimberTrack. So I want to show you TimberTrack, and this is going to be a little bit tricky from a Zoom sharing perspective, so bear with me here for a second. So I wonder what would happen if no. Let's see. Okay, I'm just going to do the easiest way to do this. Okay, so I'm going to grab TimberTrack here, which I have open. Okay, now I have to share again. Oh boy, this is actually much trickier than I thought. Okay, you know what I'm going to do? I'll share my whole desktop. That'll solve it. Okay, good. All right, so this is TimberTrack. I've just gone to a website. Any one of you could do this at the same time as I'm doing it. I didn't do anything special here on my computer. But basically, this is showing you the entire Rashomon set for this data set that I was showing you, the recidivism data set. And you know, all of the trees are in the Rashomon set. All the trees in the Rashomon set are in these gray kind of bars here. And as you walk outward from the center, you're like walking down a tree. You're into a leaf. Okay, so for instance, right here, I picked. I don't know which tree I picked. I don't know. I'll just pick another one. So let's see if I find a pretty tree. That's a pretty tree. So this tree, I got it from this leaf. So that leaf is the one I clicked on, and this is where I went. Number of prior crimes greater than 3 is true, and go this way. And if I want to, I can kind of look through this the way that a person would look through an encyclopedia. So if I wanted to limit myself to just trees with the top split being prior crimes greater than 3, I could just click that. And then if I wanted to limit myself further to age less than 26 being the second split, I could do that as well. And then I could, you know, pick and choose from the trees that are here. And if I like a tree, I can put a little heart here, and I can write a little note saying, I like this tree. I like this tree. There we go, like that. Cool. And then if I wanted to, I can incorporate constraints. So if I click this search bar, then let's say I wanted like to incorporate like a fairness constraint. Like I don't want any models that have sex equals female. Sorry, let me zoom out before I do that so that you can see this happening. So if I click that right there, then what happens is that I've removed all of the models that have that sensitive feature of sex equals female in them. And so the nice thing about this kind of you know, using the Rashomon set is that you can handle any kind of constraints very easily, because once you have the Rashomon set, handling a constraint is just a loop through the Rashomon set. You just find all the models that obey the constraint. So if you want to like maximize fairness subject to accuracy within epsilon of optimal, you just loop through the Rashomon set, find the model with the most fair, that's the model with the most fair, and then you grab that one and that's the answer. So it really handles things like constraints very, very easily. Okay, so let me stop sharing that and let's go back to this lovely, let's try that. Okay, come on. All right, share. Present. Share. Okay, great. Cool. Great. So, yeah, so again, the nice things about the setup, there's no more interaction bottleneck, makes the feedback loop to humans essentially instantaneous. It also allows you to incorporate constraints, basically for free. Okay, yeah, because like I said, it used to be hard to put constraints like, you know, fairness and monotonicity into these models. You used to have to like solve an optimization problem with the fairness constraint in it or something. And now it's just like a loop through the Rashomon set. So Tree Farms already did the hard part of finding that Rashomon set. So anyway, I hope you're starting to see the value in this new paradigm. It's a lot more computation up front, but it completely annihilates the interaction bottleneck and constraint handling. Okay, so let me tell you a little bit about how it works. I'm not going to go into detail since it's quite complicated, but the first step in the Tree Farms algorithm is to run the ghost algorithm. Ghost finds an optimal sparse decision tree that minimizes this objective, which is a combination of classification error and the number of leaves in the tree. You really do want this regularization term in there, even if you have a depth constraint on your trees, because if you don't have this term in here, it will produce extra leaves that are not needed, right? Even with a depth constraint, it will fill up that depth. And so you really want it to be a small tree and as small as you can in terms of the number of leaves, not just sort of constraint to the depth. So anyway, you run Ghost, you get the minimizer, and then you want all of the trees within epsilon of Ghost optimal solution, and that's the Rashomon set, and Tree Farms is going to find it. So the key ingredients for tree farms are a dynamic programming formulation, including theorems that reduce the size of the search space so that the dynamic program hits dead ends all the time. Because you don't really, like, you basically want to search as small an amount of the space as you can. And so if you can prove that large portions of the search space don't contain any element of the Rashomon set, you can exclude them, and then your dynamic program hits dead ends all the time, and that's really what you want, because then you can search the smaller part of the space more easily. And these theorems involve finding lower bounds on the objective, that objective function from the previous slide, for different subtrees. And then the third element is what we call the model set representation, which is our data structure that efficiently stores hundreds of millions of trees. And it stores them in an implicit way. So it's not storing them like tree. That's not how it works. It's storing parts of trees that can be combined with other parts of trees to form the entire Rashomon set. So the storage is like combinatorially more compact than if you stored the trees one by one. It's much, much more compact. Okay, so you might be wondering if we need something as fancy as tree farms. Can we get the Rashomon set in other simpler ways? Okay, can we get it maybe just by sampling lots of trees? So we asked, okay, do other methods produce almost optimal models? And as it turns out, they do not. So just to show you an example, on the Monk2 dataset, Tree Farms finished creating the Rashomon set in 46 seconds. Now, we tried running a bunch of sampling methods for 46 seconds. Now, in 46 seconds, Bayesian additive regression trees created 488 unique trees. And how many of them were in the Rashomon set? Well, only 3. Random forest created over 20,000 unique trees. 0 of them were in the Rashomon set. What about CART on random bootstrap samples of the data? In 46 seconds, it created over 20,000 trees. Only 7 of them were in the Rashomon set. And then we compare that to Tree Farms, which provably provides the whole Rashomon set, and it gives us over 105 million unique trees. And so we would have no idea that the Rashomon set was quite that large if we didn't have Tree Farms. And we get similar results on other data sets. Yeah?
I have a question about the definition
Mhm.
of all, for example, 26 years, 26 plus epsilon years, then technically you get a new model, but it will probably be just better.
So you take the unique split point among, okay, so you're asking about how to convert continuous features into discrete features, basically, which, yeah, and so in that case, what you would just do is you take, let's say, you're saying age, right? Age was the feature you chose? Okay, so age is, has numbers, let's say that you have 2,000 people in your data set, and you have them at different ages, right? So you write down all of the different ages, and then you just use the midpoint of all of the possible pairs of, ages that are next to each other as the possible split points. So you wouldn't have like age, because let's say age is in integers, right? So you would have age 53, and maybe you'd have someone who's age 54. Then you use age 53.5. You wouldn't use age 53.6 because that would be the same as age 53.5. Does that make sense? So it's just the unique split points within the values that are contained in the variable. Optimal on the training set, but with the regularization term. Yes, that's right. Because that's all you have is the training set. Okay, cool. So let me show you another model class where we've been doing, trying to create Rashomon sets. This is risk scoring. So our latest method for risk scores is called faster risk. Okay, so faster risk sounds like asterisk, which is why there's a giant asterisk on the slide back there. So risk scores are sparse additive models, sparse generalized additive models with integer coefficients. So, I mean, scoring systems are really kind of like simple model forms. You just add up the points and you get the total score, and it translates into a risk using a table here. So it's very simple. But these things are notoriously hard to construct because you've got both sparsity constraints and integer constraints. So it's like this massive number of constraints. So it makes the optimization sort of painfully hard, and you tend to lose accuracy because it's just like, you're doing so much optimization there. This is faster result on the FICO data set. It does lose a little bit of accuracy over Ghost and fast sparse that I was showing you earlier, but it's so crazy simple. And the algorithm is pretty fast. I mean, this one took about 13 seconds to create this thing. I'm going to show you another risk score. This one was, we've been using it using faster risk to make mortality risk scores from the giant MIMIC3 data set, which is an large public ICU data set. And physicians, they like to use scoring systems a lot. I'm just going to make this bigger on the next slide. Let me just zoom in again. Okay, so you can kind of see what's going on here. So here, what it's showing is that if your temperature over a certain, your maximum temperature over the last, 6 hours or something, if it's abnormal, like if your temperature is too low or too high, then you get some risk points. Whoops, I'm sorry. And if you're if you're not here for elective surgery, then you get more risk points, or if your heart rate is too high or too low, you get more risk points. And then the total number of points translates into a risk using this table here at the top. Okay, so this algorithm doesn't just spit out one model. It spits out a whole bunch of models from the Rashomon set. And so what I want to do is just show you the Riskamon app that we've been creating for risk scores. And now, again, I have to do some Zoom gymnastics, so apologies here. Okay, stop share. Okay, and let's grab Riskamon. Here it is. And then we'll share again. Okay, cool. So this is Riskamon. And basically, each of the risk scores that Faster Risk produces is one of these columns here. And then each of the columns, when you click on them, it produces a model card over here. And if you look at the model card, this is the model right there. So, and this is a model for breast lesions. So if you have a circumscribed margin, you're less likely to have a malignant lesion. And so you get, lower points for that. And then the total number of points translates into the risk using this table over here. And so it's showing you how the scores translate into these risks. And it's kind of fun, this tool. You can move things around if you want certain variables to be more important than other ones, or you want to view them in a certain way, or you want, and all the coefficients are displayed right here. So you could say, oh, well, I want the circumscribed margin to have, -4 points or whatever it is. And then it'll do it that way. So it's kind of fun to play around with. I've been really kind of enjoying that. Okay, let me go back to PowerPoint. Let's see. All right. Share. View. Share. There. Cool. Okay, I'm getting good at that. All right, so great. So at least we've made a lot of headway on this third issue, which is that interpretable models can be hard to create. So now that we've established this Rashomon set paradigm and dealt with this third point, I want to switch gears toward the first issue, which is this idea of belief. This sort of, people don't believe that interpretable models can be accurate. So what in the world would convince these people? I mean, look, I figured I've been presenting examples from real data sets about the existence of interpretable models for over a decade, and they didn't believe them then, and they don't believe them now. So if they don't believe the evidence from data sets, I said, well, what can I do? I said, well, okay, maybe I could try to convince them with a mathematical proof, okay? So I said, look, I'm going to try to prove that interpretable models are likely to exist, okay, for data sets with specific characteristics. And that way, by knowing something about how your data is generated, you should be able to know right then and there, before you do any calculations, whether this is going to work. So in order to get us into the right frame of mind for this, I want to just talk about the universe of supervised learning problems, okay? So there are really two different worlds of machine learning based on the kind of data that you're working on. Most people think these two types of problems are the same, but they are not. They are fundamentally different, which is probably why people are getting confused. Now, the field of machine learning has mostly focused on raw data problems like vision and speech and language. And here you can make really complicated models like deep neural networks, and they still actually generalize between the training and the test. But for tabular data, which are the kinds of problems I've been showing you, if you try to use a really complicated model, it is not going to work. It's just going to overfit. And you're not going to see the benefit of the extra complexity you added there. Now, there's one important difference between these two problem types, which is the raw data problems tend to have certain outcomes that are certain. So for image recognition, we know, for instance, whether an image contains a chair or not. So it's possible to identify chairs in images with over 99% accuracy. But most data-driven problems in the world are not like that. They have uncertain outcomes, right? Like the FICO data that I was showing you earlier. And for another example, consider two medical patients that have the same medical history. Then next year, one of them might have a heart attack and the other one might not. Right? That's completely plausible. Okay, so yeah, and it's you know, deep learning really hasn't had an impact in those kinds of problems, in these kinds of uncertain outcome problems. And I believe I understand why it can't. And it's not about whether we have the right algorithms. It's just something different about these problems that always kind of allows us to find simpler models for them that are accurate. Okay, so that's what I'm going to tell you about. And I'm just going to show you a simple visual example in 2 dimensions. So this is a clean data set where you can fit the data perfectly and everything's fine. But then as soon as you introduced a little bit of unpredictability, like a little bit of like label noise, then boom, you overfit. Okay. All right. So Leslie Semenova, Ron Parr, Harry Chen, Zach Boner, and I have written these 3 papers, which together, at least, they aim to give kind of like some semblance of the beginning of a mathematical proof that noise actually causes this whole thing. Right? Noise is what leads to large Rashomon sets, and large Rashomon sets lead to the existence of interpretable models. So I'm going to, again, show you a picture at the bottom so you can see kind of what I mean here. So you can kind of see that noisier data has larger Rashomon sets intuitively. So here's a noisier data set with the larger Rashomon set, and here's a cleaner data set with the smaller one. Now, the theory is a little bit hard to understand if you're not a machine learning expert, but I'm going to try to explain it. And to be honest, it doesn't really matter if you understand every step in the proof outline I'm going to give, as long as you come away knowing that there's like some sort of proof out there. Okay. So first, in this proof, noise in the world leads to increased variance of the outcomes and increased variance of the error. I used to think that if you took a clean data set like this one, right, and you added a little bit of uniform random label flipping noise, kind of, you know, if you added some noise to, you know, just uniformly flip some of the labels. I figured in that case, the predictive error of all the models would go up by about the same amount. The good models would still be good, and the bad models would still be bad. Sounds reasonable, but it's totally wrong. It's just totally wrong. So in fact, when you add noise, what happens is that the variance of the labels increases. And so that means the variance in the error increases. And since, you know, the labels go into the error function, and so the error gets harder to estimate. So not only does the error go up, but all of a sudden you can't see what's going on. You got all this shimmery uncertainty all over the place, right? The error gets harder to estimate. And so like on top of. And so you can't see anything. You're in this like cloud of uncertainty smog, okay? And we've been able to prove that this happens for special circumstances. So for instance, we proved it for uniform label flipping noise. We proved it when labels flip with a probability that depends on X. We proved it for margin noise, which is where you basically smush two Gaussians together to create noise. So all of these have increased variance of the error with noise. Okay, now second, this higher error variance leads to worse generalization between the training and the test sets. Okay, and we can see this from a theorem based on Bernstein's inequality. I mean, I know generalization bounds are not perfect, but they tend to have the important quantities in them. And in this case, it's the variance of the error, right? And this is tighter than Hufting's inequality, which is typically used for learning theory bounds. So, you know, it's actually pretty tight. And so what I'm saying is that the loss variance is an important quantity in generalization, and it's increasing with noise. So anyway, model doesn't generalize. So luckily, the analyst is not stupid. They're not just going to use an overfitted model. The analyst can see this happening because they're doing cross-validation. They've got a validation set. So the analyst compensates by simplifying the function class. So they were going to use a complicated function class, and now they're going to use a simpler function class. Okay, so I could stop here because now I've got to simpler functions. But I'm going to keep going because it goes further. Okay, so when the analyst simplifies the function class, the new class has a larger Rashomon ratio, which means a larger fraction of good models, okay? So the fraction of good models goes up when they simplify the function class. So why is that? So as you go to more and more complex function classes, if you increase the complexity of your function class, you have more good models because you got more models, so more good models. But you also have more bad models. And in fact, the number of bad models grows much faster than the number of good models, okay? So all of a sudden, for these more complicated function classes, you've got tons and tons of bad models, and the number of good models is tiny in comparison. So this happens because each good model, like when you go to the more complicated class, it gives rise to more bad models than good models, right? So let me show you an example. So if you have a good decision tree that's small, and you grow it in all possible ways, it gives rise to a few good models, but it mostly gives rise to bad models. And if you started with a bad model, it mostly gives rise to bad models. And so you end up with a situation where you have, you know, you're in a much larger function class with much smaller fraction of good models, okay? So when the person simplifies the function class, they have a larger fraction of good models. Okay, so we have now larger Rashomon ratios. We have two proofs for this, one for decision trees, showing that the Rashomon ratio is larger for decision trees of smaller depth. And we have one for ridge regression that shows that the Rashomon ratio increases with noise in the case of ridge regression. And so now we have a large fraction of the function class being good models. I mean, not like half or anything. It's like less than 1%, but still, you get the idea. And now we do a covering argument. So the set is large, okay? This set is large, the set of good models, it's large. It's large enough to contain a big ball inside of it. And then we say that there is an even simpler class of models that serves as a good cover for the space. So you should think of this space as being like trees of depth, I don't know, trees of depth 5 or something. And then the simpler models are like trees of depth 3, okay? And that covers the space, right? So every depth 5 model can be approximated by a depth 3 model, okay? So, and now because this simpler model set covers the big set, and because the Rashomon set is large enough to contain this big ball, it contains at least one simpler model. So you have now one model, at least, that's accurate and interpretable, right? Because it's accurate because it's in the Rashomon set, and it's interpretable because it's in the simpler class. Okay, so by this argument, you get quite simple models that also perform well. And that was the last step, which is that if you have a large Rashomon ratio, simpler models are likely to exist by this covering argument. And so that's the proof. And one really nice thing about this, all of this mathematics, yeah?
Explain in step 4, I'm not following why the good models remain once I simplify. It seems like there's some kind of a hidden assumption. It seems like there's an assumption here that already a simple good model exists.
No, it doesn't. It's a covering argument. Well, you've got this big ball here, and you have this cover, right? So the cover can't avoid the big ball. There's got to be at least one point in the big ball that's also in the cover. And that's the model you need. Okay, good. Okay, cool. So the one nice thing about all this math is that the practitioner actually never needs to know how much noise is present for any of this to work. It just works. They just can run their algorithms and it works. We've also been kind of approaching this from kind of some other perspectives as well, kind of a more direct approach to get to simpler models, which is to prove that noise acts as implicit regularization, which is the focus of this NeurIPS paper that was accepted recently. So the paper basically shows that if you add noise, that's actually equivalent to adding more regularization if you hadn't added noise. All right, cool. So I've just told you about the Rashomon set theory. And the implications of this theory are pretty intense because it means that optimizing for simplicity won't sacrifice accuracy for a vast set of problems. In fact, it's any problem where there's noise and you can't predict perfectly. So you can get a sense just by knowing like one thing about how the data are generated, whether or not simple yet accurate models can exist. Okay, so if I'm right, this has huge implications for a lot of high-stakes decisions that are made using data in our society that deeply affect people's lives. And this includes criminal justice decisions that determine people's freedom, for loan decisions that determine someone's ability to purchase a home, or medical decisions that determine life or death. Because if I'm right, then for none of these decisions can we really justify black box models. For none of them. And it's not like we didn't know this already. So for instance, now interpretable AI models also have a precedent in high-stakes healthcare decisions. So this model, for example, is the 2 helps 2B score, which predicts seizure in critically ill patients. And it is the only AI model used in critical care brain monitoring, and it was developed by our lab. Let's talk about criminal justice. Do we need black box models there? My first paper on this was in 2017. I've been studying this for like 9 years. And tiny little models do just fine for recidivism prediction, even on data sets that consist of over 40,000 people. So I don't see any good reason why we should allow black box models in the determination of someone's freedom. And for loan decisions, I already showed you models built on the FICO dataset. Both were built in under 10 seconds, and they're about equally accurate to black box models like boosted decision trees and neural networks. Right? If the major credit scoring agency in the United States provides data that they don't think can be handled by an interpretable model, and they are wrong, think about how many other people are wrong about this. Okay. So far, I've shown you that even on competition data sets, we find interpretable models that are as accurate as the best of the black boxes. I've explained to you the Rashomon set paradigm, where we find Rashomon sets, not just single models. This really solves the interaction bottleneck, because that's now instantaneous to interact with the algorithm. And constraint handling is now easy because you can just loop through the Rashomon set to satisfy constraints. I've also showed you this path to simpler models that starts with noise, which is like a proof that simpler models exist. And I've explained that it has huge implications for criminal justice, for loan decisions, and for other high-stakes decisions. So where do we go from here? Or at least, where do I go from here? Well, I think one thing these ideas could help with is regulation. So, I think we should have no black box models for high stakes decisions unless no equally accurate interpretable model can be constructed. And that's not very likely to happen for problems with uncertain outcomes like I showed you. I think performance comparisons should be done in practice and not on a static data set. You should consider the whole system, not just the predictions, but, including just the ability to troubleshoot and get it right. And that's really going to show the advantage of using a model that people can understand because they can troubleshoot it. And we should have no more stupid explanations of black box models. We don't want to know which variable is important. right? That's not good enough. We should demand to know exactly what calculation was made to give you that, that went into that decision. But, you know, regulation is taking too long. I'm trying to help. I spend a lot of time volunteering on a government committee that makes recommendations, so I'm trying, but it's really challenging. And in the meantime, I'm not waiting around. I'm building a lot of tools beyond what I've discussed. So, for instance, we've been expanding the Rashomon set calculation to additive models, and we're working on a user interface for that. We're using the Rashomon set for variable importance calculations. Someone told us this was kind of like XAI on steroids. Our variable importance measure is called the Rashomon importance distribution because it averages over the Rashomon set and over bootstraps. It's kind of a more holistic view of variable importance that's model independent. This algorithm is called Oak Ridge. Its goal is to discover the governing equations of dynamical systems. And to do that, it solves sparse ridge regression problems to provable optimality. Changing topics, about half my lab works on interpretable neural networks and applications to healthcare, specifically mammography, neurology, and heart monitoring with wearable devices. I actually got a lot going on. This stuff is a talk for another day. But one thing I really wanted to mention, though, is our work on dimension reduction for data visualization. This is really useful stuff. It allows you to project high-dimensional data to 2 dimensions so that you can see the structure in the data. This is an example here on the Mammoth data set. So Mammoth is a 3D data set, and I want to project it. The goal is to kind of smush the Mammoth onto the screen like you'd crush a leaf between 2 pieces of paper. So let me just show you so the older methods don't work, by the way, on this Mammoth data set. This is TSNE, and it just like dismembered the Mammoth and ran it over with a steamroller or something. Like it's really, you know, it doesn't matter what parameters you set. The best you can do is get it to look like a chicken. And then this is a UMAP, which doesn't do much better. This is large viz, which separated out the Mammoth's legs. And then this is our method called PackMap. This PackMap is quite a good method. We use it just about for every applied paper that we write at the moment in our lab. Other people are using it too. It's got it's got a whole bunch of GitHub stars. It's got some nice software awards from the American Statistical Association. I mean, just a little about the name. Kind of a stupid name. PackMap sounds like Pac-Man. It actually has a meaning, like it's like pairwise controlled manifold something. I mean, it actually has like a real name, but like it's kind of my collaborators named it. I didn't name it, right? It wasn't my choice. So anyway, it's a useful algorithm. Do you want to see what it does on the FICO data set? Yeah? Okay. So I was curious. So I asked my student to do it, and she did it. And I said, no way. I said, PackMap did that? And she said, yeah, what's the problem? I said, no, you've got to be kidding. No way. I've seen a ton of these PackMap plots. None of them look like that. And she said, no, it's real. I said, oh, okay. So I'm going to show you the result. PackMap produced Pac-Man on this data set. And I said, there's got to be some technical explanation for this. And it turns out there is. There's some structural missingness in the data. This is where that important feature kicks in. You know, it's sort of mimicking what we see in our models. But anyway, it's really hard to take this kind of result seriously. Okay. So anyway, just some takeaways. So vast number of real world problems do not benefit from black box models. They do not, they cannot, and they never will. I've given you both empirical and theoretical evidence, including something like a proof that interpretable models should exist for noisy problems. I've pointed out that regulation is needed to prevent abuse in high-stakes problems because entities like to inflict black box models upon people in high-stakes situations. I've hopefully pointed out that interpretable AI is cool. But I decided I would do one more thing before I end this talk. So I'm going to do that just before I end the talk. So let me try to figure out the sharing thing once again. So about 5 years ago, I wrote a whole bunch of songs about machine learning bluegrass songs. I like bluegrass. I like machine learning. I wrote bluegrass songs about machine learning to make my class enjoy the class more. And then somebody told me, well, what, and I was trying to record them, but I could never figure out the recording equipment and the logistics of getting multiple musicians who different distances to, anyway, I couldn't figure out how to do it. And somebody said, well, you got to let people hear it. So I was like, okay, fine. I'll just perform it then because it's otherwise nobody will ever get to hear them. So what I'm going to do is sing you a song. So I'm going to sing you a song. It's called The Knight's Overfitting Game. And it's a bluegrass song about machine learning, okay? I'm going to sing you the song. All right. Oh, and I forgot to tell you, you want to think of a guy sitting in a cabin in the woods, overlooking a lake, sunset. He's coding like crazy. He can't stop overfitting. He's just stuck. It's just, there's nothing he can do to get this thing to work. Okay, that's the setting of the song. Okay. As the evening rolls by, the sun has passed set. My code has a bug, and I ain't found it yet. I tried all kinds of trials, ablated large scripts, depleted my memory, search Stack Exchange for tips. In training, it predicts easy, like a cheating gambler. But in test, it's a random guess. On the midnight oil, the fire is lit. Despite these flames, it's still overfit. I know all the secrets, you know that I do. I randomized, regularized, reduced dimension to 2. Reset the seed and reshuffle them all. Increase parameters and prepare again to fall. In training, it predicts easy, like the sun in the desert. But in test, it's that random guess. The machine and I, we play this dreadful game. And overfitting has become my name. Okay, cool. Let me do the sharing thing again so I can, well, I'll just say thank you. Thank you.
Thank you very much. That was amazing. I'd like to open up for questions.
Very nice talk and song. So, yeah, right. So I think it's really amazing that, I think when you started with like interpretable, that you can understand, then you can build these white box models that are interpretable and stuff. But I was wondering, do you have any insights on, let's say, if you're given visual image or text image, text data, given an image, how do you know if, let's say, an atom is in the room, or given text, how do you know if, the text is toxic? Like, how do you build interpretable, like, how does one build interpretable models when the input features are not, explainable?
Okay. Okay. I need to reproject again because I have to show you, because if you're asking about visual stuff, it's impossible to do it without showing people. But now I'm completely tangled up. Oh boy. All right. Mental note, don't do untangling in front of people. That's impossible. I think I'm forever entangled here. Okay, where was the where's the court that I was using?
Were you just on Zoom?
Was I on Zoom? Oh.
Yeah. Just
Okay.
Actually, while we get that set up, could the next speaker, Rosabla, come up? Oh, yeah. Yeah.
Right, so, see, where'd that mic go? This is an example of, this is a proto-PNet, which is an interpretable neural network. And it does case-based reasoning, which is kind of like nearest neighbors, except it looks at parts of nearest neighbors, but like parts of images, parts of prototypical nearest neighbors. And so what it's doing is it's telling you why this bird is classified as a clay-colored sparrow. And it's saying it's because these different parts of the bird look like these parts of prototypical birds. And every calculation in here is either a visual comparison that you can see whether this looks like that, or it's a bunch of numbers being added up. And that's it. So every calculation can be verified by a human, even if the concepts don't have names. No, this is how the prediction is made. I don't have a, yeah, we can talk more offline, but basically, yeah, it's a calculation that's done on each class where every comparison gets a score and you just add up the points for each comparison, and that's how it works. Yeah. Sure. Stop sharing. Cool.
Any more questions from the audience?
It's like, you could explain the name Rashomon?
Okay, so Rashomon, sorry, maybe I should try to use this mic or no. Okay. Right. Okay. So Rashomon is a Japanese movie about a murder, and it was viewed by 4 different observers, and you end up feeling like there's no ground truth. It's just what people think. So there's like a whole bunch of good models, but none of them is like the model. And Leo Breiman used this analogy to that movie to describe the fact that there were a lot of good models. And so we used that terminology from Breiman to call it the Rashomon set. There you go. Cool.
Any other questions? All right, well then let's thank Cynthia one more time. All right, like to bring up our next speaker. Our next speaker is a contributed talk. Rosabla Pacelli will be telling us about the effect of weight sharing in Bayesian shallow networks in the proportional regime. So, thank you.
Thank you. Okay. Hi, everyone. And let me start by thanking the organizers for giving me this opportunity. And today I want to start by showing you a statistical mechanics framework to study deep neural networks in general. And I will show you also how this is essentially the Bayesian approach. And then I will delve into the calculation. I will specialize to shallow models and delve into the calculations of an effective theory, an effective action, and so an effective theory in the so-called proportional thermodynamic regime. And then finally, I will show you how to use this theory to investigate the effect of training in different models, and in particular in fully connected and convolutional models, so networks that do or do not have weight sharing. Of course, this framework involves a deep neural network. I am calling the layer, the weights of each layer with the letter W, and I will denote the activation function with sigma. Then, of course, I need a set of labeled data and a loss function, an energy function, and, of course, prior statistics for the network weights. The goal of such exploration is to compute the Gibbs posterior distribution or Boltzmann distribution of the network weights, which is this quantity here. And beta here is the inverse temperature parameter. Really, what one wants to compute is the normalization factor of this probability distribution, which we call the partition function, which is what you expect. I will choose a loss function, which is the mean squared error, so quadratic loss function, and a Gaussian prior for the weights. With this choice, what I am really computing is the Bayesian posterior in disguise, where the partition function is just model evidence, and we have Gaussian likelihood with a variance which is the temperature, 1 over beta, and of course, Gaussian prior for the weights. The partition function computation can get very, very hard. And exact solutions with a finite number of parameters exist for deep linear networks. This has been done rigorously. In all the other cases, you can also check Pietro Rotondo's poster tomorrow at this regard. And in all the other cases, we need a thermodynamic limit. So we will end up with an asymptotic solution for the partition function. The thermodynamic limit is just the limit where the number of parameters is taken to be large. And this raises a question that is how do I do that? Moreover, since one is performing the thermodynamic limit, one has also to choose a scaling for the parameters themselves. And in general, I would want that the parameters in layer L scale with a negative power of the number of the width of the layer, which I call NL. And here again, how do I choose this power? One popular choice, which is also the first that was done historically, is the following. You take the limit where the width of the hidden layers goes to infinity, while the size of the train set P stays fixed. And one can choose gamma equal 1/2. This is, of course, a non-exhaustive list because of papers, because it was extensively studied over the last almost 30 years. Okay, but this lazy training infinite width has one problem, which is networks in the infinite width lazy training regime do not exhibit feature learning. What I mean by feature learning is that is a change in the statistic of the parameters. So in the lazy training infinite width, there is no change in the statistics of the parameter before and after training. One way to overcome this problem is to choose the mean field scale, so-called mean field infinite width, where we have the same thermodynamic limit, but we have a different scaling for the parameters. And this cures the fact that one does not have feature learning. So mean field scaled networks do exhibit feature learning phases. But for the sake of this story today, let me consider a third way, which is the proportional thermodynamic limit, where one takes both the size of the train set and the width of the layers to be large, to go to infinity, with the ratio fixed and finite, and gamma equals 1/2. The advantage of such a description is that predictions from this theory can be tested against finite networks. Provided, of course, that both P and NL are large and of the same order of magnitude. So I wanted to show you I wanted to sketch for you the computation of the partition function in the case of a one hidden layer network with a single output neuron. So in this case, I will have the matrix W for the parameters of the first layer and the vector W for the weights of the last layer. So here I've just rewritten the partition function in a more explicit way. And also I have explicitated the function, analytical function that the network implements. So the first thing that you want to do is to switch to a representation in terms of preactivations and outputs rather than a representation in terms of parameters. So we introduce these two identities. H mu I are the pre-activations, and F mu are the network outputs. Mu is the index that runs over the data set, while I is the index that runs over the neurons of the hidden neurons. Okay, so once I do this, I have this form of the partition function with these two averages. With this symbol, I denote the averages. And this average over the first layer weights can be done easily. If I denote H bold symbol, the vector of hidden pre-activations corresponding to the train set examples, I get that this average becomes a factorized probability distribution, factorized over the index I, and it's a product of Gaussian distributions, where the covariance matrix is just the two-point correlation function of the train set. For this average, I need an extra step. I need to use this exponential representation of the delta function, and then the average can be computed. So I end up with this expression, and I can, here, I notice that I can factorize over the neuron index. So I do that, and I end up with this expression. Now I have this problem here that I cure with the following identity. So I define an extra variable Q. And once one does that, one ends up with this expression, where now I have a P of Q, distribution for the variable Q. And here is the critical point of the computation, because this now I need a Gaussian equivalence, which I cannot justify. I can only heuristically justify, because of course I am invoking a Gaussian equivalence under inside an integral over an infinite number of variables. So it's not rigorous. That's why we check that this assumption is reasonable, at least numerically. Here I am showing you P of Q for a random dataset and the CIFAR10 dataset. So as you can see, the Gaussian approximation is reasonable. And the covariance of this distribution is has this expression. It depends on this F bar, which is the conjugate variable of the outputs. And this matrix, K and NGP, is the NNGP kernel evaluated at train input pairs. This is a well-known quantity. It was identified firstly in infinite width networks. Okay, so now I need to disentangle this F bar mu's, and I do that with Euler's integral that allows me to compute the remaining Gaussian integrals, and I end up with this simple expression. So I have reduced the partition function to be an integral over a finite number of parameters, Q, and in a form suitable for saddle point integration. So now I have just to minimize this effective action with respect to the variable Q, and I obtain a solution in this way. Let me remind you that this derivation holds for this kind of network with a single output neuron. But if I wanted to do multiple outputs on the same architectures, the situation doesn't change a lot, but there is a big difference. The order parameter Q is now promoted to be a matrix. It has dimension D times D, where D is the number of networks output. To disentangle the Fs, now I need an extension of the Euler's integral, a more powerful result, and I will use the Ingham-Siegel relation. And in this way, I end up with a similar expression, where now, of course, we have the promotion of the parameter Q to be a matrix. Okay, so I showed you that this is possible. So I can reduce in a non-rigorous way the partition function to be an integral over, in general, a matrix order parameter Q with an effective action that's this form. And this holds for fully connected models, as I showed you, but it also holds for a lot of different architectures and in a number of different settings. So this is a very general description of shallow architectures. And the quantity that depends on the specific topology of the network is this renormalized kernel, renormalized with respect to the NNGP kernel matrix. Both the dimension of the order parameter and the precise relation that defines the renormalization of the kernel are defined by the network's topology. For fully connected networks with multiple outputs, we have that the renormalized kernel is the outer product between the Q matrix and the NNGP kernel matrix. And this renormalization is a global rescaling of the NNGP kernel matrix. In the single output network, this is especially clear because this just becomes a product. And so everything that you can do with the scalar Q, you can do with the scalar lambda, which is the Gaussian prior over the last layer weights. So this is a trivial rescaling of the kernel. For convolutional models, the story is different. And we have that the renormalized kernel is a local rescaling of the NNGP kernel matrix. The matrix Q is now a matrix that has dimension, number of patches, time number of patches, where the number of patches is this light blue squares that you see here. And this is finite. Let me point out that the proportional regime for convolutional networks involves the size of the train set and the number of convolutional filters, while the number of patches remains finite. And this is totally different from the fully connected case, because this renormalization is a rotation of the kernel, so it changes its eigenspectrum. It is really a local operation. The proportional weight theory really boils down to minimizing this effective action with respect to parameter Q. Once we do this, we end up with predictive posterior distribution that is Gaussian and takes this form. But let's for now, just for a moment, forget about the proportional regime. And let's pretend that we wanted to really fit our data with a Gaussian process regression, where our ansatz for the kernel matrix, the kernel function, sorry, would be really, would really be the renormalized kernel. So we have a kernel that depends on hyperparameters, the entries of the matrix Q. And if we were doing Gaussian process regression, we would fix these hyperparameters by maximizing the log of the model evidence. Finding a Q star in this way would give us exactly the same predictive posterior distribution as the proportional regime description. But as you can see, the parameter Q star that results from from the two description would be different, because the effective action is not exactly the same as the log model evidence in a Gaussian process regression. We have these extra terms that really enforce a physical constraint of positivity, because Q has a physical interpretation that you can ask Paolo Baglioni. I will just briefly say that Q is linked to the statistics of the weights of the hidden layer. So these terms pop out because of the physical meaning of the order parameter. Okay, so we have this effective action, but we lack a rigorous treatment. So we need, of course, numerical validation. And one straightforward way to test the validity of our theory is to measure the generalization loss. So here I am showing the generalization loss as a function of the number of hidden units in the network with the size of the train set that is fixed. I am showing the generalization loss for 3 different data sets, a random data set of Gaussian data, the MNIST data set, and the CIFAR10 data set. The colored lines are the predictions from our proportional width investigation. So the average of the generalization loss over the Gibbs ensemble. The dots are the outcome of numerical experiments with Bayesian networks, meaning that we have to train our models with a discretized Langevin equation to make sure that we are really sampling from the desired Bayesian posterior. And the dotted lines are a heuristic solution that comes from perturbation theory, which is much less computationally costly than really computing the true prediction, but as you can see, it gets close. Okay. And as you can see, we have discrepancies for small values of n1, which is expectable because this is an asymptotic theory, so it holds for large values of n1, and what is large depends really on the data set under consideration. Okay, but the generalization loss is an indirect evidence of what is really happening in a neural network during training. So to probe really if this kernel renormalization is happening, and is happening really as we predict, we look at this observable, the empirical post-activation 2-point function of the post-activations, and we are restricted to odd activation functions for simplicity. We could also do non-odd activation functions, but it's much messier. Okay, so here N1 is always the number of neurons in the hidden layer. This means that for the convolutional neural networks, this is the number of channels times the number of patches. By definition, at the initialization, this observable is the limit for infinite number of hidden units of this observable is the NNGP kernel function. But what happens on the Gibbs distribution? So really, if one measures the difference between trained and untrained empirical kernels, this matrix delta K, we call it the similarity matrix. What happens to this quantity? Okay, so in the limit of perfect interpolation of train set, which is the zero temperature limit, we have these 2 expressions for the fully connected and the convolutional model. This computation follows through. And the first striking observation that we can make here in the fully connected side is that this matrix of internal representation, this delta K, is just an order 1 over n1 correction of the NNGP kernel. And we have no hope that it can be otherwise. In the convolutional model, we have a different situation because we have sum over p elements that can compensate this vanishingly small prefactor. And so we can have that the entries of this matrix are of order 1. So it's not clear that in the convolutional case, the effect of training on internal representation is just a correction to the NNGP kernel. If we restrict further to 0 and 1 labels, we can get more analytical insight because we get simpler expressions, but still very involved. So if we let me denote delta K 0, 1, the similarity submatrix of labels 0 and 1. So where one label is 0 and the other one is 1. For the fully connected case, we expect that these entries have an average in 0 for odd activation function, where the kernel has 0 average, and we expect the distribution of these elements to be more and more peaked around 0, while increasing n1 with alpha fixed. And this happens. We get a distribution that is more and more peaked around 0 when n1 increases and alpha is equal 1. And the variance of this distribution goes to 0, shrinks to 0 with a slope of -2, which is what we expect. In the convolutional case, we also expect to have an average in 0 for odd activation function, but we don't expect this distribution to shrink, to be more and more peaked around 0. And also this happens, this is verified. Let me stress that differently from the plots that I showed you in the previous slide, these experiments were done with networks trained with the Adam optimizer. So these are not Bayesian networks. They do not sample explicitly from the Bayesian posterior, but still we get that our scaling predictions are met. We can do the same with the similarity submatrix of labels 1, delta k 1, 1. And we have that in the fully connected case, we expect, again, that the average should drift to 0, not be 0 always, while increasing n1 with alpha fixed. And we expect the distribution, again, to be more and more peaked around 0. And again, this is verified. We have the average that drifts to 0 and distribution that gets shrinked. And this is the drift. This is the drift of the average to 0, which is a slope of -1. In the convolutional model, again, similarly to the previous slide, we expect the same drift to 0 of the average, but we don't expect the distribution to shrink, to become more peaked. And again, this is verified. So we can safely say that in a fully connected case, the difference between trained and untrained internal representation is just a correction. It vanishes while increasing n1, while in the convolutional case, this is not the case. Okay, and this brings me to the conclusion. So I presented a flexible statistical mechanics framework for Bayesian neural networks in the proportional regime. As you will see today in the afternoon in Alessandro Ingrosso's talk, this framework is suitable also to study transfer learning, which is a very common practice in state-of-the-art machine learning. And I showed you that this statistical mechanic framework is able to capture effects of training. It fairly well reproduces the generalization laws in Bayesian networks, and it also predicts the scaling properties for non-Bayesian networks, networks trained with the Adam. And I want to leave you with a question, a very general question. Can this approach be made rigorous? And if so, to which extent? And with this, I conclude, and I thank you for your attention.
Any questions?
I didn't really understand it. It's kind of over you know, just like the second line there.
This is just by definition.
I see.
Okay.
Will I be able to see the slides afterwards there?
Yeah. Clicker. One more time. Let's make it so you can hear me. There we go. There is a coffee break now for half an hour till 11. I was informed to please leave the food and drink outside. So there's carpet and felt, all kinds of things that stain in here. So to be polite to our gracious hosts, let's try to keep the food out there. Thank you. See you in half an hour. Thanks again.
Thank you.
Great.
Thank you. But sorry, were you by any chance in the sushi?
In where?
In Le Sushi in 2022?
I
Are you in Utah? Okay. If someone wants to-
There's a big component Hopkins in there. Actually. Secondary. What is that? My primary is in biomedical engineering.
Okay, I just want to add in the word.
Right, so I need It is. All right. Shall we? Okay, welcome back. We're about to get started for this second session. For those who don't know me, my name is Jeremiah Sulam. I'm an assistant professor at Johns Hopkins University, and I'm part of the organizing committee of DeepMath. So I'm going to be running this short second session right before lunch. We have 3 contributed talks for this hour and a half. And first up, we have Shiva Bishwal, who is at Los Alamos National Labs, and she's going to be talking about identification of mean field dynamics with transformers. Shiva, the stage is yours.
Oh, thank you so much. Good morning, everyone. My name is Shiba Biswal, and I'm currently in Los Alamos National Lab. And today I'll be presenting my work which is joint work with Karthik Alambazuti, who's also in Los Alamos, and with Rishi Santalia, who's at, these are the pictures, and Rishi, who is in Boston University. So I'm going to be presenting my work on identification of mean field models using transformer architectures. Okay, so let's start with motivation. We want to use the transformer architecture to approximate mean field dynamics or collective behavior of interacting particle systems. And so what is these models are characterized by particles which are indistinguishable. So they don't have identity to them. And so what this leads to is a permutation equivariant system. What that means is that if you exchange like particles, right, if you permute them, the dynamics does not change. So because of this property, this is quite an important property. I'll come back to that. So why transformers, right? So transformers are, of course, like the core of a lot of these large language models. And these are essentially sequence-to-sequence maps, but on RD, right, on finite dimensional vector spaces. But the key property here is that transformers are permutation equivariant. And so the idea is that perhaps we can use these mean field models, which are permutation equivariant, we can identify them better with transformers. Why mean field models? Well, because they're an important class of problems in biology, physics, robotics, so machine learning, and networks, right? So here we see flocks of birds and swarms of fish, traffic models, large networks, robotics, and also machine learning, right? So all of these models, I mean, there's just so many applications where mean field dynamics are quite important. Okay, so let me introduce the equations to you. Let's consider this n particle system. So here Z is the state of the particle, and F is the dynamics. So because of you'll see that F depends on mu, right? Where mu is the distribution of the particles. So please recall that I said this is an interacting particle system, so they are not. And so this mu is the distribution. So F takes a subset of omega, right, and the probability measure on omega to RD. The mu, which is the distribution of the particles, evolves according to this continuity equation, okay, which is a partial differential equation, right? Okay. Right, so now let me introduce what transformers are. Well, these are, I'm not going to give you the mathematical formula, but these are essentially sequence-to-sequence maps. So N here is the sequence size, and D is the dimension. Okay, so the sequence size is given by N. And standard transformers have many components, like the attention layer, the neural network, layer normalization. We're now going to be considering the layer normalization in this work. All right. Now a recent work, so this is 2023, last year, Alberti et al. They came up with a universal approximation theorem for transformers. What they say is, if you have a f which goes from Rd cross n to Rd cross n, and more importantly, if it is a permutation equivariant function, please remember that means if you permute the domain, it doesn't change the dynamics, right? So it's a permutation equivariant function. Then you can approximate this f by a transformer arbitrarily close and in the uniform norm. Yeah. So, okay, now let's go back to our goal. Our goal was to, if you remember this f, which is our mean field dynamics, right? It takes omega and a probability measure on omega to Rd, right? Now, this probability measure on omega is an infinite dimensional space, right? So, but unfortunately, the transformer which is defined, or the standard transformer, only works on finite dimensional vector space, right? It takes Rd cross n to Rd cross n. So we have to come up with a version of the transformer which is like this continuum version of a transformer. And we do this via this expectation operator. So what is this continuum version? I'm going to call, so all the stylized letters are for the infinite, they act on the infinite dimensions, and all the non-stylized ones are just on finite dimensions. Okay, so going forward, that's what I'm going to stick to. So this t sub n, so for a prescribed length n, okay, we take the sample of the measure. Okay, so here mu is a measure on omega. We take a sample, so the z is a sample of mu, and then we evaluate. We look at the average of the transformer acting on all of these samples. This one represents because if you recall, like the output of t is a vector. And so one means that the first element of the vector. Okay, so that's how we are defining our continuum version. We are going to call this the expected transformer. Okay, that's what it's titled. Okay, so we have two goals. First, we want to use this expected transformer to approximate our f. And our second goal is to approximate the solution of the continuity equation. Okay. Okay, let me talk about some related work. So first, a set of work are related to mean field approximations using machine learning architectures. So of note is the work by Pham and Warren. They constructed a neural network, which is actually permutation equivariant. So they had to come up with their own architecture to capture the equivariance, permutation equivariance, to approximate mean field mappings. There are several work which use kernel-based approximations to identify interacting particle systems, and then there's some other work as well on SINDI and things like that. So there's quite a bit of work on trying to approximate mean field models. The second set of work is about defining the transformer on probability measures. So of note is the work by Kishkovsky et al. They too defined a continuum version of the attention, okay, which is like the core part of the transformer architecture. And a recent work in 2024, actually, very recently, it's still on arXiv, I believe. They also proved a universal approximation for this version of the transformer. Okay, so let me come to the assumption section. So what are we going to assume? Okay, let's recall what the Wasserstein metric is. We need a metric on the space of probability measures, so that's why we need this. We're going to assume that f, please recall, f takes omega and a probability measure on omega. So we're going to assume that f is Lipschitz continuous with respect to omega and with respect to the probability measure as well. Now this condition, this Lipschitz condition, implies that we have linear growth for f, and so you can show that this leads to the second condition. So let's note these two constants, L and M. They will play key roles in the theorems that I'm going to present next. Okay, so here's our first goal. If you recall, our goal number one is to approximate f using this expected transformer. And right, so given an arbitrary epsilon and fixed size n, right? We can find, and if omega is a compact set, and if f satisfies the Lipschitz assumption, which I showed on the previous slide, then we can find a transformer T, this is the standard transformer, such that the expected transformer satisfies this bound. Okay, so this epsilon comes from the error in just is the epsilon from the universal approximation theorem by Alberti and et al. This is because of the finite dimension approximation. And this big gigantic term that you're seeing here, that comes from the fact that you're taking samples of the probability measure. Okay, so as you can see that as n tends to infinity, this term will tend to 0. Okay, so we can say that f can be arbitrarily approximated by this expected transformer. Okay, so proof of how do we prove this? So first, we want to identify a finite dimensional map with the mean field model, right? So we do this by taking particles. We're going to consider that. Let's assume that we have n particles, okay, and these n particles, they have a state z. So we can associate this Dirac delta with these particles. And now we can write down the particle dynamics. So dz by dt is given by this vector. So what we have done is we have actually identified a sequence-to-sequence map, which is a finite dimensional map for these n particles. Okay, and this Fn is also permutation equivariant. Okay, and this Fn can be approximated by the transformer, by the standard transformer. Okay, moving on. We're going to use this norm for our so this, if you recall, like these are objects that act on probability measures. So we're going to use this norm to approximate them. Now just using the standard, like we're just going to put in the definition of what Tn is. This is the standard this is the standard transformer. And now we're going to do is we are going to split this term into three more terms. This is just a trick. You're just adding and subtracting more terms and then kind of individually bounding each of these terms. So what am I doing? So this T is right here. This F is here. And now we are adding some terms. Okay, we're adding and subtracting terms and bounding them. So this Fn and these two are the same objects. Okay, yeah, these two are the same objects. And of course, these two are the same objects. So you can bound this because if you remember, this is just the standard transformer. This is that epsilon that you saw in the theorem that basically comes from this. This is just the universal approximation theorem of the regular transformer. This term can be bound. This is just the Dirac delta, so it can be you can use the Lipschitzness of f and bound this term, and this term comes from the gigantic term that, if you remember from the theorem, that comes from approximating a continuous measure mu by samples nu. Okay. All right. So that was the end of the proof sketch. Moving on, our second goal is to actually not just identify the dynamics, but also to approximate solution of the continuity equation. So continuity equation gives you what is the continuity? Well, this is the continuity equation, and it tells us how the distribution of the particles evolves, right? Now, let me define what a solution is, because the continuity equation, usually you give weak solutions to this. So instead of defining the weak solution, we're going to define something called the Lagrangian solution, which is basically particle level dynamics. We're going to follow a particle x, right, which starts from this initial condition little x, and this is how it evolves. And the solution of this continuity equation will then be given by the push forward measure of the initial density, right? So mu naught is the initial density. Under x, under this capital X, how does mu naught get pushed forwarded, right? So this is our solution to this continuity equation. It's called the Lagrangian solution. Okay. All right, so now we want to approximate x, the capital X, where we can show that the continuity equation has a unique Lagrangian solution because of the Lipschitzness and all of that. So that's not a problem. We're going to now, instead of this f, if you remember, this is the continuity equation. Oops, excuse me. Okay, so instead of this f here, we're going to substitute our expected transformer, Tn, right? And now we're going to see the solution of this continuity equation. And we can also show that under some, we can also show that this equation, this continuity equation, also has a unique Lagrangian solution. Okay, and we are going to denote the solution by this mu superscript Tn. Okay, so our goal is to, we're going to, so this is our second goal and the theorem. We can say that if the support is bounded, if the initial condition, right, the initial distribution of the particles is bounded or is given in a compact set, and if you can bound the expected transformer and the f, which we have already shown in theorem 1, then we can in the Wasserstein metric, P Wasserstein metric, you can bound the solution by something. Okay, so this is the solution to the original continuity equation. This is the solution to the continuity equation with the transformer, and you can bound this. So great, we were able to do that as well. Okay, again, I'll give you one slide on the proof idea, but instead of showing you the proof on something very complicated, let's just go down to finite dimensions. Nice and easy. So x dot is equal to f of x. Assume that x dot is equal to f of x, and f is a Lipschitz continuous function. If you have an approximation of f, let's say g is an approximation of f, and you have it in some norm, okay, of your choosing. And if you want to show that y dot, the solution of y dot is equal to g of y approximates solution of x dot is equal to f of x, that means y approximates x. How do you do this? This is quite standard. Okay, you use you add and subtract as everything in math, like we add and subtract some terms, and then we bound this f because it's Lipschitz continuous, so you can bound this term, and then this term can be bounded because we know that g approximates f. Okay, so we have something like this, and then we have this magical lemma called Gronwall's lemma, which I'm sure everyone here knows about. You can use Gronwall's lemma to show that the solutions remain closed. Okay. Now, where does the problem come here? For us, our vector field also depends on mu, the distribution. So this is going to be proof. This is the tricky part of our proof. But other than that, this is the idea of our theorem. And that's it. Let's come to the fun part, which is numerical simulations. So here I'm presenting Cuckus-Mail equation. This Cuckus-Mail equation is quite a very famous. Anytime you type mean field models, like one of the first results in Google will be the Cuckus-Mail. Okay, very, very famous. What it does is it shows you the consensus of these particles, and they're consensing as in they are all coming together, and they're aligning their velocities for whatever reason, because you can see birds and fish, they all align their velocities with each other. So let x, this x be, so this is we're doing this in 2D. So let x be the position and this v be the velocity in x and y direction. The vector field is on, this is the vector field. Phi gives you the interaction potential. Phi is called the interaction potential. It shows you, it tells us how the particles are interacting with each other. And we were able to, so this is the solution of we are able to use the transformer dynamics and the true, oops, what happened? Oh, no. This is supposed to be a video and, oh, wrong mouse. Oh, yes, yeah. Okay, so here, x, what is happening here is if you see, the rightward arrow is the transformer dynamics and the leftward arrow is the true dynamics. And we can see that the transformer is really able to capture the dynamics of the mean field model. That's quite nice. Okay, we see that here are some error bounds that we would like to present. The bolt line, so this is x and u, and this is y and v. So remember, x and y are the positions, u and v are the velocities, right? So the bold lines are all the the median value over 100 trials, and the shaded region is the error in approximation by the transformer. It increases as time increases. Okay, let me also present an example from machine learning. So as I also said, mean field models can also be found in machine learning. Everyone knows the neural network, right? So these, the parameters here are A's and W's, right? And so this famous paper, this is like they showed that as n tends to infinity, right? So the particles here are the layers, n is our particles, right? So you get a PD you get a mean field model for the parameters, right? Okay, so we can also use the transformer to learn. So again, we are learning the mean field, the parameters, and we see that this is how the transformer, it doesn't do that bad of a job. Well, it's able to approximate the dynamics here as well. Okay, so in conclusion, we defined a continuum version of the standard transformer. So we were able to lift the standard transformer to probability measures. We proved convergence results for this expected transformer, and we showed that mean field models, especially the interacting where you have interaction between particles, can be approximated, and the solutions can be approximated by transformers. This is our paper on arXiv, and with that, happy to take any questions. Thank you so much.
Thank you very much for the nice talk. We have a couple of minutes for questions. Yes, please.
So I was wondering about Navier-Stokes equation.
No, we're not doing any. Oh well, Navier-Stokes. We're doing mean field models, so Navier-Stokes equation is not something that we have considered. I mean, also Navier-Stokes is not necessarily you don't have interaction. Well, you have interactions, but not the way we are considering. It's not arbitrary PDEs.
Yes.
That is correct. Yes.
Challenges arise.
So they do depend on each other. We do have interaction. Where is it? Oh yeah, here it is. Right. So we are not assuming that the particles are interacting with each other, because if you see that our F, where is our F? Oof. Okay. So our F is F is dependent on mu. So the particles do interact with each other. So they're not independent tokens.
So the product measure you use slides from calories for approximating that using samples.
Yes, so yes, at each time step we take the sample of the measure, and yes, so Z is, but they're interacting, Z's and Z, they're not independent. Yes. Do I also have? I can also show you this one here. So we do have Z1 to Zn. They are interacting with each other when they do look at the Dirac deltas, right? Which is the sum of all the particles.
Yes, please.
Can you go to slide 17?
17, sure. Oh. Yes.
I suppose you had subtype of YT. But these are under the absolute random norm. You can't do that, can you?
Well, this is just on RD, right? I'm just showing you a proof idea here. We're of course more rigorous, and when we actually do it for this F, it required more work to show all of this. So I'm skipping a lot of steps here. I don't think I'm being like, this is just a proof idea. This is like, again, this is not at all, this is not even, this F is just where X is just an RD. This is just a proof idea. This is not the actual proof. Yes.
One last question.
You approximate people dynamics for the transformer. Do you assume that you can query the true velocity of the particles?
Sorry.
How do you actually train the transformer?
I was informed. How do we train? Oh my God, I was not part of the training person.
If you already know the true velocity of the particles, like through the net, then I guess my question is, why would you approximate?
Oh, we don't always have, actually, we have another very nice example, which we did not decide, decided not to put in the paper, but this is actual real fish data. It's called fish milling data. We do not know the dynamics. We just have the data, as in we know the positions X and we know and the velocities V. And from that, we are actually able to learn using the transformer, we are able to learn the dynamics.
So there is some loss that is.
Yes, yes, yes. Right. Yes. Yeah, thank you.
One last question at the end.
Sorry, could you please repeat? It depends on what? Yes, yes. It's a compact subset of RD. Yeah. Yeah. Yes, yes, but then we also, yeah, so we have to take larger ends or larger tokens, as you said. So n will decide. So given an omega, we can take a transformer of sufficient token size, large enough. Yes, such that this can be approximated. It does depend on the diameter, unfortunately.
And sorry, and since we're here on this slide,
Yeah.
what is Q and P here exactly? I lost track.
Okay, so P is it comes from the Lipschitz assumption. So, oops. P is coming from this.
Okay, good.
And if you look at the proof of, so this term here, okay, you're actually bounding the taking the measure mu and you're sampling it. Oops, you're sampling it. So the Q term comes from the fact that we're taking the moment of Q.
Okay.
So, yeah.
Thank you. All right. Please join me in thanking Shiva once again.
I keep my laptop sleeve here.
Oh.
Laptop sleeve.
You prefer using this mic or the? Okay, yeah.
So up next, we have Dayal Talbra, who is going to talk about universal sharpness dynamics in neural network training from University of Maryland. Thank you for.
Hello, everyone. First of all, thank you for the organizers for organizing this wonderful conference. I'm Dayal. I'm a graduate student at the University of Maryland, and I'm here to describe our recent work on sharpness dynamics in neural network training. And this work is done in collaboration with another graduate student, Tenu He, and my advisor, Mason Bhakrishnan. So in the recent years, we have seen that neural networks have done a really great job in different domains like language modeling, vision, science and mathematics recently. And for me, the most interesting question is how we can train these complex models, which have billions of parameters, and these result in non-convex, high-dimensional loss landscapes. And there are probably a lot of minima or saddles in this loss landscapes, and yet consistently we can optimize these landscape really well and find really good solutions. So what's the magic recipe here? The magic recipe is that we just follow the negative gradients and add some momentums to the gradients and some adaptive terms and repeat until convergence. And the popular optimizers here are like gradient descent, which basically changes the parameters in the negative gradient direction scaled by learning rate, which is denoted by eta t here. Also, we have in practice, usually people use adaptive optimizer like Adam, which updates the parameters using a scaled version of the moving average of the first moment divided by a square root of the moving average of the second moment of the gradients. So I would like to point out that if you have trained neural networks, learning rate is like one of the most important hyperparameters in optimization. And I would like to, the way I think about learning rate is it is like a focus of a camera which is looking at the loss landscape. And if we tune our learning rate really well, we look at the landscape in a really in an optimal way, and that's how I think this entire optimization works. So the learning rate is intrinsically related to the properties of the loss landscape. In the full batch gradient descent case, when we have like convex landscapes, then this is related to the sharpness of the loss landscape, and which is basically the top eigenvalue of the loss recession. And the reason is that this is called the sharpness because it corresponds to the sharpest direction in the landscape. So we just massage the the update equation of the loss. Then a very nice lemma, which is descent lemma, tells us what's the maximum learning rate we can use in convex optimization settings. And this is basically simply given by 2 over the sharpness of the loss landscape. So basically, as a function of learning rate, we have 2 phases in convex world. A convergence phase in which we monotonically decrease the loss, and a divergence phase where training just diverges. And this is separated by this critical learning rate, which is 2 over sharpness. However, in the neural network world, the sharpness evolves during training, right? And usually, typically, we observe that there, in addition to the monotonic convergence phase and a divergent phase, we have a intermediate phase, which is called the catapult phase. In this phase, even in the deterministic setting, where you have no noise in the dynamics, you'll probably you converge, but you converge through a slight increase in loss. So the loss decrease is not monotonous, but you still converge at a long time scales. And this has led to various different phenomena which are observed at large learning rates. And one of them is called catapult dynamics, which corresponds to these training instabilities. And also we have observed something called progressive sharpening, in which the sharpness at late training time keeps on increasing. And then there's something called edge of stability phenomena, and I'll describe them in a couple of slides. So the goal of this work is to understand the sharpness dynamics in neural network training. So basically, we'll measure the sharpness during training, and this is a proxy of this basically measures the most the sharpest direction throughout training. Okay, and how it evolves. So these are the typical training trajectories, the loss trajectories and sharpness trajectories of a neural network. So what I would want you to notice is that the sharpness has a very consistent behavior across learning rates. And we will get into this deeply in a couple of slides. But here I just want you to notice that it has a very systematic trend throughout training. And the goal of this work is to understand it. And these trends are observed for not just fully connected networks that I've shown in the previous slide, but also for CNNs and ResNets. And so let's dig deeper into this training dynamics of sharpness dynamics of neural networks. So typical training trajectories of neural networks basically can be classified into 4 training regimes. The first regime, which is sort of like an early training regime, in which loss in sharpness may increase during training, depending on the learning rate. So there will be some critical learning rate for loss and some other critical learning for sharpness. And above these learning rates, the loss and sharpness will increase, but they will eventually decrease after a few training steps. And this is like order of 10 training steps in math. And this is this part of the curve. After this, we observe an intermediate saturation regime in which the sharpness slowly changes, and in some cases it remains almost constant. Beyond this, we observe a progressive increase in sharpness. So the sharpness keeps on increasing until it reaches a critical threshold, which is for full batch gradient descent is 2 over learning rate. And finally, the sharpness will oscillate around this fixed value, which is 2 over learning rate for full batch gradient descent. And in this regime, where it's oscillating around 2 over eta, the loss also decreases non-monotonically. So there are some oscillations around here, but at long time scales, you still converge. Right. Yeah, it's a local notion of sharpness. So you, at a given training step, you basically compute the top eigenvalue of the loss assertion numerically. This one is full GT. There are some differences, slight differences in SGT, but first we want to understand in full batch GD case. The main difference is that this threshold 2 over learning rate is actually some constant which is less than 2, basically, in case of SGT. And there's a complex dependence on batch size. Okay, so this work we have found that the sharpness dynamics heavily depends on the initialization and parameterization of the neural network. So let me just summarize what do I mean by initialization and parameterization. Initialization basically corresponds to the initial weight variance of the model. And we have basically 3 types of parameterization that are used in practice. And first is the standard parameterization, in which we just ensure that the activations are order 1 at initialization. And then we have neural tangent parameterization, which is well studied in the last decade or so. And in this case, we not only ensure that the activations are order 1, but we also ensure that the function outputs are order 1. And if we take an infinite width limit in this case, we get a kernel method or kernel learning. But in the recent years, people have also identified a maximal update parameterization. In addition to ensuring that the activations and the function updates are order 1 at initialization, it also ensures that the activations are also receiving order 1 updates. And this results in a feature learning infinite width limit. So what we have observed is that, okay, so in the previous slides, I've described you the 4 regimes that are observed typically in neural networks. So, but if we consider slightly large initialization, which in this case would correspond to 2 over fan invariance in the standard parameterization for LUFCNs, in this case, we observe that the sharpness only decreases during training if you exclude the catapults, and it doesn't show any progressive sharpening or adjustability like we had. Then we can also consider, go to the other end, we consider slightly even smaller initializations, which in this case corresponds to the maximal update parameterization. In this case, if you ignore the catapults, what you would see that training usually experiences progressive sharpening right off the bat and doesn't have this initial reduction in sharpness. So far we have observed that sharpness dynamics can show up to 4 training regimes. And this also differs slightly on the basis on changing initialization and parameterization of the model. And the key question we want to answer in this work is that Yeah. So the key question we want to answer in this work is that does there exist a very simple model that we can analyze in order to understand this, different sharpness phenomena that we observed in the previous few slides, and understand at least in these simpler settings. So in this work, we show that a very, very simple model, which is probably the minimal model if you, to be considered as deep learning. It's a two-layer linear network with width n, so it has n neurons, and trained on a single example. And I would like to claim that this simple model captures all the different phenomena that I've described in the previous slides. So this model has been studied in various works, but in this work we generalize this model to consider different parameterizations. And the model is as follows: it takes an input x, and we multiply it with the matrix matrix U and a vector v. And this U and v are initialized using a Gaussian distribution with zero mean and a variance of sigma square w by n power p, where p is some parameter that I'll get to. And once we have this output of the matrix products, then we basically divide this output by square root of effective width, where effective width is the width power 1 minus p, where p basically interpolates between different parameterizations. So p is equal to 0 corresponds to the neural tangent parameterization that I talked about, which results in the kernel infinite width limit. And the mu p corresponds to, p is equal to 1 corresponds to the mu p case, in which case the effective width is 1, and it corresponds to the feature learning limit. And in one slide or so, I will demonstrate what the kernel learning and feature learning limit will correspond to in this model. So the model is simply trained with MSE loss. So because there's just one example, our loss is simply delta f squared by 2, and delta f here is the residual f minus 1. So next, we just train this model with full batch gradient descent, because this is one training example. And here are the gradient descent equation, and eta is the learning. So next, we will write down the gradient descent dynamics in function space. So by that, I mean that we will write down the update equations of the function, and what we find is that this can be described by two coupled nonlinear equations in terms of just two scalars, which is the residual that we encountered in the previous slide, and second, which is lambda, which is a trace of the Hessian, which basically looks like the weight norm if you think about it. And these are basically two nonlinear coupled equations with three effective parameters: eta, the learning rate, a ratio of the input norm divided by square root of effective width, and third, the target one. And the dynamics is completely described by these two equations. There are these two scalars, and there is no approximation. So let's take a quick detour and understand what do I mean by infinite width limits in these cases. And this is a very simple model to understand infinite width limits. So if you consider the neural tangent parameterization, in which case the effective width is basically n. And what you notice is that the width only comes in the higher order terms. And as you take width to infinity, the dynamics simplifies quite a bit. The trace of the Hessian, which is a measure of curvature here, doesn't change at all. And the function update becomes linear. And this is basically the infinite width limit or the kernel limit that we get. It's a sense of that kernel limit we get in neural tangent parameterization. But we also can consider this maximal update parameterization, in which case the effective width is 1. And in this case, if you take an infinite width limit, the equations don't change at all. The equations don't simplify, and the equations don't depend on width at all. And this type of simple analysis basically tells you that why there can be learning rate transfer in these maximal update parameterization. Okay, so let's go back to understanding sharpness dynamics using this UV model. So what we'll do, we'll find fixed points of the dynamics. So we had these two coupled nonlinear equations. We'll just set delta ft plus 1 is equal to delta ft and lambda t plus 1 is equal to lambda t. Why do we analyze fixed points? Because these fixed points will determine the long-term behavior of the dynamics of this node. So okay, so let me plot these fixed points in a phase space defined by lambda and delta f. And let me slowly describe this slide because there's too much information on this slide. So this is called the phase portrait, and here we have divided this phase portrait into different regions. The gray region basically corresponds to it's not accessible and it's forbidden because of the positivity of lambda. And the colored regions basically correspond to convergent region, or sorry, allowed region, and it can be explored by the model. In this allowed region, we use these gray arrows to denote the gradient direction in this allowed region. Then we have 4 type of fixed points. First, zero loss fixed line, which is here, and a few of these fixed points are stable with respect to learning rate, which are denoted in the blue color, and the others above it are just unstable, and they're separated by this dashed dot line shown here. And this basically comes from the stability of a fixed point with respect to learning rate. If eta lambda is less than 2, then it's stable. Eta lambda greater than 2, then it's unstable. Other than that, we have 3 more fixed points. The second fixed point corresponds to all parameters being 0, and it's a saddle. So it has an incoming stable direction and an outgoing unstable outgoing direction. Apart from this saddle, we have 2 more fixed points, which are stable all the time, and their stability doesn't change, and the gradient basically points outward from it. So let's use this UV model to understand the 4 regimes of training that we observed. So I'll first consider this large initialization case in which we only observe initial catapults at large learning rates and only a reduction in sharpness. So at small learning rates, in this UV model at least, the initialization is somewhere in the sharpness reduction region, which is denoted by this. Okay, I think I missed saying that this green region corresponds to where lambda is decreasing. The yellow region corresponds to when lambda is increasing, and this blue region corresponds to just divergences. So you will just diverge here. Okay, so let me come back to this understanding this large initialization case. In this case, if at small learning rates, the training is initialized in the sharpness reduction region, and we observe a decrease in sharpness, and nothing else happens. Just slight decrease in sharpness, and you converge. But if the learning rate is large, the training is initialized at a higher region, and the nearby zero loss fixed point in this case is unstable. So you can't really converge there, but the gradients still point towards it. Okay, so this results in an increase in loss, which is denoted by this trajectory. And once this causes a decrease in sharpness because the fixed points 3 and 4, they are pointing the gradient toward the center and downwards. And this causes a decrease in lambda. And once you are in the stable region, then you just converge to a nearby zero loss solution. Next, if we can consider the small initialization case in which we only observe progressive sharpening at a small learning rates and then edge of stability. So if in this case the model is initialized right above this 0 parameter saddle and in the yellow region, which corresponds to increasing sharpness. And what we observe is that training just converges. There is no zero loss solution with that lambda. So all zero loss solution have lambda that is greater than that. So resultantly, we observe an increase in lambda during training, and then finally the training would converge to a nearby zero loss solution at small learning rates. But at large learning rates, something very interesting happens. All zero loss fixed points become unstable. So there's nowhere with respect to that learning rate you can converge. And the idea is that the gradients are still pointing towards the zero loss line, right? So this results in an unstable convergence that instead of converging to a single fixed point, you converge to this manifold defined by a fixed point 2 and 4. So you basically converge to this line. I'll come back to this line in a couple of slides, but let's in the next slide, let's understand why we observe sometimes we observe this decrease in sharpness and then increase in sharpness later on in training. So in this case, model is initialized to the left of this saddle in the sharpness reduction regime, and the training is attracted towards this zero loss fixed point, which causes a decrease in sharpness, like shown, which can be thought of somewhere here. And then after that, we observe a sort of slow dynamics because we are near a saddle. And once the training passes the saddle, then we start observing progressive sharpening, and then finally the dynamics follows the same behavior as the previous case. So let's now look at more carefully about around what happens at this manifold defined by this fixed point line segment defined by this fixed point 2 and 4, and we refer to this as the edge of stability manifold. So if the learning rate is above some critical threshold, we observe that lambda oscillates around two values. And once you slightly increase the learning rate from, let's say, going from 0.54 to 0.63, you start observing that lambda oscillates around 4 points, and it eventually becomes chaotic. So let's now plot the limiting values of lambda as a function of learning rate. And we observe this beautiful bifurcation diagram. So below a critical learning rate, training just converges to a zero loss fixed point. And above this critical learning rate, which is mentioned here, you oscillate around 2 points. You further increase the learning rate, it oscillates around 4, and then eventually it follows the period doubling route to chaos, and eventually it becomes completely chaotic. And how can we understand it? So we can write down the loss function on this EOS manifold that I just described. And the loss function basically looks like this, which is a quartic loss function, and quartic loss function in some norm of the parameters. And if you do gradient descent on such a loss function, which corresponds to a cubic map, these type of cubic maps are well known to show period doubling route to chaos. So far we have understood a lot of these complex sharpness phenomena in this UV model, and I would like to argue that this UV model gives us a very simple explanation to this complex sharpness phenomena. So progressive sharpening can naturally occur when the training starts with the initial lambda, which is less than the smallest lambda for zero, corresponding to zero loss solutions. And initial sharpness and followed by a progressive initial sharpness reduction followed by a progressive sharpening occurs when training passes this zero loss saddle that I showed you. And adjustability in this UV model basically occurs when the zero loss fixed point with smallest sharpness becomes unstable with respect to the learning rate, and we observe this form of unstable convergence. And finally, I'll just take a couple of minutes to go back to real worlds and say what UV model can tell us about real world models. So in the UV model, we had this critical learning rate, and we argued that edge of stability like behavior would be observed when the critical learning rate is above some threshold. Then we can write down this learning rate as some constant over the initial sharpness of the model and massage this a bit to get a condition which is in blue. And this condition basically says that large initialization, which have large lambda, or large effective widths, which corresponds to neural tangent type parametrizations, and small learning rates may not show edge of stability at all. And this we confirm by plotting a heat map of eta lambda by 2, which is the threshold for edge of stability, as a function of this C constant that I just described, and the initial variance of the weights, which basically control the initial sharpness. And we observe that a blue region, which corresponds to non-edge of stability region. And on the right, I have a similar plot for parametrization, but in interest of time, I will just skip that. This is the last part where we wanted to check if there exists a route to chaos that I described in real world models. So in the top row, we basically train a neural network, in this case, just a 2-layer FCN but with general input output dimensions and multiple examples. We train it with random, completely random data, which doesn't have any correlation with input and output. And in this case, we again observe a nice bifurcation diagram and 2-point oscillation and so on. And this can be further quantified by the Fourier transform of these trajectories. But in the bottom panel, we show it do the same for a when the same model is trained on CIFAR-10, and instead of observing a nice bifurcation diagram, we observe bands of sharpness which increase in magnitude. And what we found is that the sharpness basically has long range correlations, which can be quantified by this Fourier transform of these trajectories. And this what we found is that these long range correlation in time basically come from long range correlations in the input spectrum of input covariance matrix of the data. And with that, I would like to just mention that this has motivated some further studies, and we have to understand warm-up mechanisms, and we have also introduced a new version of ADAM from this understanding, and which will be presented in the NeurIPS conference. And with this, I would like to thank you for your attention, and we'll take questions.
Thank you very much, Daya, for the talk. If I can ask the next speaker to come and start preparing his talk, that'd be great. And we have a couple of questions a couple of minutes for quick questions. Yes, please.
We haven't, but with biases, let me see. Biases usually restrict the maximum trainable learning rate in these small models, at least. So one of the issues with observing all the behavior that we saw here is that we need a large space, or we should be able to train at large learning rates, which biases usually restrict us to. That's why we didn't consider biases, but biases I don't think changed much of the story.
Any other questions? I have a simple question. So the simple model that you guys studied is nice because it allows you to capture already very interesting behavior. What can you say about non-linear extensions to these, though, including, for example, non-linearities in matrix vector multiplications?
So
like a very basic non-linear.
So the problem we actually wanted to solve that problem, model, because that could capture this sort of dynamics that I was talking about. And in this case, the problem is that we have like these interacting UV models, and which are coupled with each other, and they only simplify when we consider input covariance matrix to be of identity. Otherwise, the dynamics is very complicated, and I still don't know how to solve it, to be honest. But yeah, if someone has to know, please reach out. I'd like to talk about it.
All right. Okay, with that, join me in thanking Dayal once again. Perfect. Okay, so to wrap up this session right before lunch, we have someone local. We have Davis Brown, who's going to talk about the shape of 1 + 1. Very much looking forward to your talk.
Yeah, thank you for having me. Yeah, and this was work done at Pacific Northwest National Lab, and most of these folks are from PNNL. Right, so today I'm talking about some interpretability work we performed and are performing on language models on very simple arithmetic tasks. This is like ongoing work, like very preliminary, but yeah, we're excited to talk about it. Right, so why do we care about this? Language models famously make all kinds of mistakes, and but these mistakes are often hard to evaluate because many of these tasks are very open-ended. They have no possible or known correct answers, and we lack non-statistical algorithms that we can compare the model's processing to. And in general, this is often bundled up into this hallucination problem, right? And there's like a definition of hallucinations there. Okay, so why study arithmetic problems there? These are great because we have ground truth answers There are multiple non-statistical algorithms for solving them. And also there's like a huge range of properties that we can measure on models around these algorithms that could suggest like greater understanding or world models these algorithms are using to compute this kind of thing. So we provide some examples here. These include questions about the geometry and topology of the input space and the output space, algebraic properties of operations. We particularly look at commutativity, and then like arithmetic properties, so divisibility, integers, and so on. Yeah, and so there's like this example, 34 times 12. We have like our input space, our output space, and like all kinds of structures one might expect when you look at a range of these. Yeah, to highlight some prior work here. These two on the right are concurrent. This one on the left, we were aware of when we started this project. But these all have like a lot of interesting things to say. And like I will emphasize that some of what I show here is not like completely novel, but is us kind of just like throwing the interpretability kitchen sink at this model in order to understand what's going on. So this paper on the left showed that addition is performed via some like combination of approximation of the solution magnitude in the MLPs, and then some precise solutions via like these like modular information computed via like Fourier transformations. This middle one I particularly like. It explains the errors that models make, which is like somewhat interestingly not normally distributed around the correct answer, but is instead kind of just like uniformly distributed nearly on like the token space. And they explain this because they're dependent on a base 10 representation. And then this final one on the right basically says, hey, models neither memorize solutions nor have like one correct algorithm, but instead use these like bundles of heuristics to compute these answers. And we kind of show something, or we have work that here that suggests that models also do this as well. Okay, so what are our takeaways from this current work? We found that models reconstruct the geometry of input space and their intermediate steps, intermediate layers. We found that, or we've extracted representations which capture interesting properties of numbers. And we found that models have some notion of algebraic properties like commutativity in their hidden layers. Yep, so I'll go through each of these. But first, some background. What are transformers? This is maybe something a lot of you have seen before, but I think it's like worth going through. So we're particularly focused on Llama 3.8b here. This is a model trained on 15 trillion tokens that Meta AI released. And we are looking mostly at the residual stream of this transformer. So the intuition for what the residual stream is it's this like information bottleneck that every single attention layer is reading into or reading out from. And so if you want to find information the model's using to make some computation, it's going to be at some point in the residual stream by definition. And so that's where we focus on here. We could focus on other places, and like we will as this work progresses. And then we're also focusing on multiplication of numbers in the range of 0 to 100. So for example, we're giving the model 42 times 61 and asking it to compute the answer. And again, our goal is to better understand how models successfully or not successfully complete this task. We don't really care about making models better at this task. And there's been some interesting work done around like tokenization, particularly of like making models handle this kind of arithmetic task better. Yeah, we don't really care about this. We just like care about studying why models fail on this, so we can generalize to more interesting hallucinations. Okay, so what is actually going on when models see a multiplication problem? So we give it a prompt, 45 times 23 equals. This text is chunked up and tokenized into a set of ordered tokens. Yeah, again, this process is like very messy. We're not focusing on tokenization errors here. I think this is like something that will be just like solved pretty easily. But yeah, the text is chunked and then embedded into an activation space. For Llama 38B, this is something that's 4096 dimensional. Yeah, right. So here's like us embedding each of these individual tokens into an embedding space. Each of these individually gets a vector to represent it. But this is going from something in token space, vocabulary space, that's much higher dimensional, something like 128,000, into something much lower dimensional. And it's worth noting that these like kind of word to vec looking like embeddings have all kinds of interesting properties, even without anything else. Yeah. Yeah, just Llama standard organization. Yeah. Not doing any of these like fixes. Okay, and then what happens next after the model's been embedded or tokenized, or these tokens have been tokenized and embedded? Multi-head attention happens. You can think of this like a mechanism that shares information between tokens. So if we're sitting at 45 and looking at where information gets passed from 45, it gets put forward into the multiplication and put forward into the 23 and put forward into the equals, all at the first attention layer. Likewise, where's the information getting passed from the times, it's getting passed into these future token embeddings. And this is all happening in the hidden layers and on the attention operation. Right, same with 23. Oops, sorry. Yeah, and then, okay, so that's what attention is. And then what are MLPs doing? The intuition you should have here is MLPs are just acting on the individual tokens. They're not doing any of these like information sharing computations. One thing people often say, and it's like been found somewhat robustly in the interpretability literature, is that these MLPs encode something like facts. So if you want to look for a place where the model is saying the Eiffel Tower is in Paris, you look at these MLP layers. Yeah, and so these are just acting on these individual dimensions. And then finally, the model takes the final token dimension and applies the unembedding operation that's at the top of this diagram, and puts them into token space. And people sample from this. And we do it greedily, so we just take the highest probability token and we get an answer from this. So yeah, like 45 times 23 is 1035. Okay, so first of all, you might ask, like, how well do models do at this multiplication task? Yeah, pretty well. They're particularly good at multiples of 5 and 10. The model performs much better when the magnitude of the factors is smaller. So you can see that like models often get things in the top left correct, and then like errors start happening as they go down to the bottom right. This is like something that's known. Another question we asked here, and is like a nice way to get an initial map of where things are happening in the model, is how early does the solution appear? So what we did here is we used a trick called the tuned lens. This basically early exits from a model and looks at, if the model could only compute, or if we can only sample from the model at some given layer on this x-axis here, what would the answer to the model be? And you can't just do that early exit naively. So we learned this affine transformation that takes the model's answer at some layer in the residual stream and maps it to the correct logits. And it turns out that around block 18 to 19, the model, like the correct solution starts to appear. And then after block 25, this answer is like correct. And here we're plotting both the accuracy, which is like the sharp metric, and the KL divergence, which is like a softer metric. And we can see that both of these kind of support this hypothesis. Yeah. Okay, so now like a walking tour of what's happening geometrically in the model. So one question you might ask is like, what is the local intrinsic dimension of these answers as you go throughout the model? Yeah, so here we're looking at this final equals token, and we're doing local intrinsic dimension estimation with this like 2NN method. And we can see that the intrinsic dimension increases during initial integration phase, And then as we go deeper in the model, during the second half of the processing, it goes through this consolidation phase where the local intrinsic dimension decreases. I'll point out that this is like something that has been seen pretty robustly across like lots of both generative and like supervised models, this kind of integration and consolidation phase, including in problems like protein folding. And there's like not a clear that I'm aware of like answer of why this kind of thing happens. So like this is kind of, yeah.
Why those specific tokens are equal to sign?
Yeah. So good question. So the model is like taking this equal sign token, and like that's where the unembedding process is happening. So the eventual like sample like has to come from this. You could look at like, for example, every single token, or like some average of these tokens, but I think like if you were to choose a single token, you would choose this one because like this is where the actual embedding procedure is happening. So it's like the model has to compute the answer from this token at the very end. Okay, so what's actually what's actually happening as we step through the model and go deeper and deeper? So here we are just doing PCA and looking at like PCs 1, 2, and 3, and we are coloring by the magnitude of A on the left and B on the right. And kind of the takeaway here is that the model is organizing things after just the first layer globally in terms of B. And then if you like look at these local little groups of clusters, the gradient is in terms of A. So this is like an interesting thing the model's doing. Yeah, and it like happens very quickly after the first layer. After the third layer, when we, again, coloring by magnitude of A on the left and magnitude of B on the right, the representations appear to form a cube with one axis corresponding to the magnitude of A, one to the B. So like, in other words, the model's kind of realizing the like R2 domain here. We actually don't know what's happening on PC3, like maybe not anything interesting. But yeah, this is like an interesting thing we saw like pretty robustly across a bunch of models, but this is for Llama 3AB. We have no idea what's going on for layers 4 to 14. Like it could be nothing. So like the model could be doing some other computation that like makes it such that when you look at the first 3 principal components, these like are not super well organized anymore. So we don't have like a confident claim here. All right, none of these claims are confident, but like we don't even have like a strong intuition as to what's going on here. And then and this has also been observed in the literature for like these middle layer blocks. Yeah, things do seem to be colored by by different modular representations. So if you look at like A mod 2 in the middle here for block 9, and B mod 2 also in block 9, these things are like relatively cleanly separated on one of the principal component or 2 of the principal components. Likewise for B mod 10. So the model is starting to do some modular arithmetic stuff, and then in some results that didn't make it onto these slides, we've like explicitly looked at Fourier decompositions of these things and found that like models do like actually use these like Fourier components. Yeah. And then finally around layer 15, like these representations kind of shatter and like low dimensional structures start to emerge again. So here's coloring by magnitude of B. We have this clustering. The model's like starting to prepare to give its answer. Yeah, and then some like interesting structures here. Again, another circle. And some interesting cone-shaped structures. And this is for layer 19 and after layer 21, respectively. These incorporate features from A and B and A times B. This is colored by B mod 2. Yeah, and then finally some like really interesting saddle point looking things. Like we have some like really rough guesses as to what's going on here, but we're not super confident. And so if anyone has ideas here, that'd be great. Okay, one question we had was that like these circular structures start to appear around block 19. This is related to some of this like Fourier computation stuff that's going on. But we were curious if these could be detected by persistent homology, which I'm not going to go into here, but like we can talk about if people are interested. Right, so like, can you find circles, higher dimensional circles in this data using these like set of topological data analysis techniques? Not just in the PCA representations, we're also curious about like the full, you know, R4096. So could we find it in the PCA? Yes. So like persistent homology was easily able to find this like, you know, relatively clear circle. Unfortunately, in the original representations, persistent homology was not able to find this. And the evidence of this feature would be in this like top left-hand corner of these plots. This is basically saying like there's a feature that exists that is a circle. Yeah. So this existed in the PCA, but probably the original representation is like too noisy for our TDA tool to find this. Yeah, so like one question you might ask is, these appear to relate to modular properties of A and B. How much does the model actually know about divisibility? So here we're looking at different probes for divisibility. So this is asking, can the model correctly guess whether A and B are divisible by K? We've taken this up to 50 since this slide and found that like often very robustly, the model knows whether or not something's divisible by K, which is like pretty surprising. You know, you don't need to compute this, I don't think, to get the correct answer here. Yeah, and I guess like this is accuracy, which is not the best metric to use for this because like, you know, if you go to K equals 49, like lots of things are not divisible by 49. But we've also looked at F1 and found that this trend holds to F1. Okay, so that is divisibility properties. Another question you might ask is, can you use this to modify neural networks predictably? And so there's this hypothesis in the interpretability literature that says something like, for models that are trained on a lot of data and a lot of diversity, the relevant features are linear. And we have this conjecture that math, like these kinds of properties are at least like linearly probable in such a way that we can steer the output of models. So for the example we're looking at here, our question was, for A times B, is there a direction that corresponds to whether B is a multiple of 5? Okay, so so the way we find this multiple of 5 feature is we do difference in means probing. So we take a bunch of examples of numbers that are multiple of 5 and compute the centroid, take a bunch of examples that are not multiples of 5, compute that, and then subtract those. And we take this direction and use it to intervene on the model. So without doing this intervention, like without adding this vector into the embedding space, this is what things look like. So we're looking at in the green if the answer is a multiple of 5, in the red if the answer is not a multiple of 5, and then blue is just like not giving an integer answer because models make all kinds of mistakes. And layers on the y-axis and the value of b, and that A times b equals prompt is on the x-axis. And so what we see when we add in this b divisible by 5 direction is the model systematically gives answers now that are divisible by 5. This is not true for all of the layers. So like this only works if you're intervening on layers 15 to 24. And it, yeah, like that y-axis range. and it's not true of all numbers. So this doesn't seem to work for smaller numbers. Maybe the model's memorizing things here. I don't want to be too confident about why this doesn't work for that case. But it does work for lots of the answers to A times B equals. And so, yeah, I'll say that the claim here, I think we can confidently make is that we can at least probe and steer models in such a way with just this direction, such that we can steer the model towards answering, that an answer is a multiple of 5. Another question you might ask is, to what extent do the representations in Llama 3 respect commutativity? So here we're analyzing the distance between A times B equals and B times A equals. That's in this blue. And you can see, this is kind of a confusing plot, but you can see this blue one by, it's the only thing that dips down at layer 18 and then comes back up. We also compute a bunch of variations of this. So we look at comparing A times B plus 1 to B plus 1 times A, and so on. You can see on the legend here. And after initially increasing, the distance between A times B and B times A decreases very sharply at 18 and then comes back up. And this is the only thing that does this. Yeah, and so maybe hold that in your head as I go to this next plot. So a more rigorous way of looking at this is doing a causal ablation. So actually swapping the activations between A times B equals and B times A equals and looking at what the model computes. So here we're taking the representation of the equal sign after these prompts for A times B and swapping it with B times A and vice versa, and looking at whether the model still gets the answer correct. And you can see here that accuracy stays pretty consistent at most layers, except for layer 18, where it seems like the model's doing something specific to the order of these operands. But in general, it minimally impacts performance. And then just to control things, we also look at whether the model got A times B incorrect and B times A correct. That's in the red. So you can see when you swap that activation out, accuracy goes up. And we also look at in the green, A times B correct, B times A incorrect. And you can see that here, the accuracy goes down. And then when it's incorrect, swapping, this is not going to do anything. Our ablations are not perfect here. So we're doing this at the layer level, which is quite coarse. So I don't think it's for example, we're below 100% accuracy, even though the model got these two, this question correct. So there's a more minimal perturbation we could have made here that maintained accuracy. So this is a coarse causal experiment here, but it does get at whether the model is respecting the commutativity of these operations in its representations. Okay, so what are the takeaways from this work? We've reconstructed, in some sense, some of the low-dimensional geometry of the input space and at intermediate steps. We've extracted representations which capture some divisibility properties of the numbers for multiplication. And then finally, we've shown very roughly that these have some notion of commutativity. And so again, this is a work in progress, and so really excited to take this work forward, and I think we're super open to hearing feedback. So yeah, thank you.
All right, we have a couple of minutes for questions for Davis before we move on to lunch. Yes, Darshan.
I'm wondering maybe perhaps possible that some of these things are not actually computing them over the layers as suggested by some of these based on train. So is there some, I think that's a method that more simply memorize all conclusions. How can one isolate that?
Yeah. How do you isolate it? I mean, I think you like a rigorous thing you could do here is like these causal experiments. So you like have an algorithm the model's doing in mind, and you do ablations to test whether this algorithm is present. What they do in this paper is they like take a bunch of heuristics that they think individual NLP layers or neurons are doing and ablate it and systematically show that the model is using these heuristics, which like would not be true if the model were memorizing this. So it's like the model fails if it's using one heuristic and you ablate it, but it succeeds if you like promote this heuristic.
Any other questions? Yes, go ahead.
Just to follow up on this, couldn't you also check whether it's memorizing by giving it, for example, 12-digit numbers that, you know, the probability that it has seen those 12-digit numbers in the training set is like 0. So
Yeah, you could do that for sure. Like unfortunately, models don't get these answers correct very often because the model doesn't get them correct. You can train models explicitly to generalize to these, but you know, if you take a model from the wild, it's often not going to get a very hard multiplication problem wrong. So it is definitely not, you know, it's definitely using heuristics that don't generalize to like very hard cases, but it's not just memorizing either.
Yep.
The AI detects is like how it processes the information wrong instead of knowing if it's computing wrong.
Yeah, and I mean, in effect, that's why we chose this problem to study this kind of thing. Because there's a ground truth solution, we can just pass these to Python and check the answer. And in effect, when you query ChatGPT for this kind of question, the interface is detecting whether this is something you should pass to a calculator or Mathematica, and then computing that. Yeah, we were interested in studying how or why models failed at these kinds of tasks, and so we didn't pass it to a calculator here. Yeah, like for example, for this experiment, we ran it 100 times 100 times. And that's true for most of the things I showed. Some of them, yeah, that's true for most of the things I showed.
I have one quick, perhaps more broad philosophical question, which is you started the motivation of this work by saying, you know, we want to understand why sometimes these models fail. And here there's a subset of the problems that we may care about, which is arithmetic, and it's nice because we have ground truth. And so we're going to try to understand things here so that then we can translate them to more general scenarios and understand why these things fail. So how do you see that happening? Like, how do you envision generalizing some of these observations and ideas to things that really have to do with natural language?
Yeah, I think I can give like two good cases here. One is we've thrown the interpretability kitchen sink at these problems, and lots of things didn't work, and those didn't make it into the slides. Some subset of them did work, and like, you know, by testing these methods on this kind of thing, one might hope that, you know, you're at a good methodological starting place when you hit these harder problems. The second thing I'll say is that like it's definitely not the case that every factor concept is being like represented sparsely when you take a Fourier transform, like these kinds of arithmetic problems are. But you might learn some basis that represents these factor concepts sparsely, and when you like learn that basis, you can check whether the same kind of model algorithms that are being used to compute addition, whether model computation is consistent across these different sparse bases. And so I think this is like a more speculative direction we're excited about.
All right, in the interest of time, we are at 12:30. We are going to move on to lunch, and I invite you for the rest of the questions to take them offline, and David's around. So we will switch buildings, and you can just follow some of the volunteers and organizers. We're going to move there, and we will reconvene in an hour and a half, I believe. Thank you all.
Thanks.
stuff wherever. Okay, we're good. Yeah. I guess let's start with it.
Unmute the podium.
This red. Okay. Let's move then. It's this one. Podium? Okay, yeah, perfect.
Okay, welcome back, everyone. So I have the great pleasure to introduce John Ducey. I think many of us already know John. He's a professor at Stanford University. He did his PhD at Berkeley. He has done a bunch of work in a number of areas, including optimization, statistics, information theory. And he's won pretty much every award you ever wish to get, including a bunch of best papers in NeurIPS, ICML, iClear.
Not iClear, Colt.
Colt.
Yeah.
And
It's easier if you just say John has won a number of awards. 0 is a number, then we can be done.
That's true.
Okay,
That's true.
good. All right.
John has won more than 3 awards.
Damn it.
And with that, please just join me in welcoming John. The floor is yours.
Great. That was a really nice introduction. I appreciate it. It's good to be here. People getting weird feedback. Good question. Sorry, technical issues. No, I'm muted here. Ooh, that's a possibility. Is that better? Oh, that is better. Okay, sorry. Still working on the technical stuff. Okay, anyway, nice to be here. It's good to see a bunch of folks in the audience. So today I'm going to be speaking about some work I did with my students, Chen Chung and Hilal Asi. Chen is finishing up his PhD. Hilal graduated a year or so ago and is now a research scientist at Apple. But we're going to be talking about how many labels do you have, and kind of I just want to talk about data labeling. There's a bunch of seats in the front and in the middle, so folks can scoot in, whatever. Okay, so I'm gonna start this off, and also feel free to interrupt me. Like, this should be an interactive talk. I hope it is. I'm gonna draw on the slides, so anytime you guys feel like jumping in, feel free. So let's talk about the standard story that we teach students when we talk about statistics and machine learning. Okay, that looks good. So what do we teach students? You know, when you take your intro machine learning class or your intro regression class or whatever it is, we tell them, okay, listen, you're going to get a bunch of XY pairs of data. You know, maybe you make some model y equals x beta plus epsilon. Maybe you're a fancy optimizer, so you minimize some function f subject to x and x. You do all sorts of cool calculations with subgradients and prove convergence rates, and it's amazing, right? You do all this beautiful math, and it's awesome. Like, the data comes in, you get a great model out. Yeah, who's taught that class? Damick, raise your damn hand. Yes, thank you. I know you have. All right, so many of us have taught that class, but I think actually I'm a little more interested lately in kind of like a fuller picture of statistical machine learning, broadly speaking. So, you know, there's this box here, which is kind of this fun theory and stuff like that we teach, but it turns out there's a lot more that goes into machine learning problems and solving them, modeling them, doing them in industry. And so if you think about this, you know, there's a huge amount of work. Anytime you're going to do a machine learning problem, you have to collect the data. You choose the population you get the data from, you get data points, you label them, maybe you clean them up, you filter them, you do all sorts of stuff over here before you dump it into your sophisticated algorithms. And then once you fit your model, you release it to the world, right? And so then it goes back out into the world, and, you know, maybe you put it in a hospital. You got to monitor it to make sure it's not doing bad diagnoses. You know, maybe you want your predictions to be calibrated. When you say there's a 70% chance of rain, it should rain 70% of the time, right? You need to identify where it's failing. Maybe a new population comes in because, you know, you did like the Framingham's heart study. You fit this on a bunch of white dudes living in Boston, and it turns out that there are people who aren't white dudes in Boston that you want to measure their heart disease risk, right? Maybe you need to retrain the models because, you know, things change over time. You want to retrain your models. So there's all this stuff that actually should go into any kind of real full understanding of machine learning. And I don't think we spend enough time talking about it. Okay, so kind of what I'd like to do, I mean, big picture, what I want to do is I want us to kind of refocus machine learning on the whole pipeline, right? I want us to do everything from the left side all the way to the right side and start putting mathematical foundations down everywhere. That's like the big long-term goal. In the short term, we'll obviously do a much smaller part of this. Okay, so that's our motivation, or that's the big picture of kind of where I'm excited about. All right, so let me give you guys a tiny bit more motivation. So maybe 5, 6, 7 years ago now, Dave Donahoe wrote this article called 50 Years of Data Science, which was a survey of kind of statistics in the age of big data and deep learning and things like that. And what Dave writes, and I really like this framing, is the following. I'm just going to read it out loud. It's no exaggeration to say that the combination of a predictive modeling culture together with what he calls the common task framework is the secret sauce of machine learning. Okay, so what that means is that somebody comes up with a sort of a challenge data set. There's some challenge set that everybody wants to do well on. And in the 1980s, this was the MNIST handwritten digits data set. Actually, if you go back to the beginning of machine learning, like 1960s, 1965, there was a, oh gosh, now I'm forgetting his name, but there's a data set that was literally at SRI, the Stanford Research Labs, which was punch card handwritten digits. Okay, they've unfortunately lost those, but even in 1960, everything was kind of driven by these test data sets. But you have this challenge data set, and then everybody who wants to participate in this challenge, whatever it is, agrees, okay, we're going to all compete on this. We fit our models on some kind of training data. And then there's this kind of centralized referee or some test data set that's held away from everyone, and we evaluate on that. Okay, and this is how we iterate progress. And when you do better than everybody else, you get to publish a paper. Right? This is kind of the game. So I think one of the most evocative parts of this, or most important versions of this in the past, say, 15 years, was ImageNet. Okay, so most of you have probably heard of ImageNet. So how does ImageNet work? We have input data X, which is some image, say in this case, of a golden retriever puppy, and the goal is to assign a label Y to this image. Right? In this case, Y is going to be a golden retriever. All right, and then this data set, the description of this is for each of 1,000 image categories. And these 1,000 categories include things like cherries, bows and arrows, golden retrievers, dachshunds, all sorts of things. There's 1,000 representative images in the training data that you can then fit on. And then there's this held out test set. And this was originally released in 2009 and updated in 2014. Okay, now so this slide cuts off in 2022 or sort of mid 2022, but just looking at it, let's talk about our progress on ImageNet. So in 2011, this was before deep learning. Some of us were trying to do research then. We had all these crazy things we did. There was shift invariant feature transforms, Fisher vectors, Fisher scoring, all sorts of things on how we tried to develop image processing things. And we got about 50% accuracy. I guess you can't see the vertical axis. There we go. How's that? Told you I'd edit the slides on the fly. Big edits here. We got something like 50% top one accuracy in 2011. And this was like state of the art. Okay, and then in 2013, Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton published AlexNet. And this was the first deep learning, basically what initiated kind of this whole deep learning explosion was this jump from a 51% accuracy to something like 63% accuracy. All right, and over 3 years. And before this, the progress, I mean, you could look at it and it was like sort of just this incremental progress, very slowly coming up and up and up, but not big. But we had this massive jump right around 2013 when AlexNet was released. And so, and then after that, we had more and more advances, residual networks sometime around 2016 gave us another jump. And now we're, well above 90% accuracy in identifying like 1 out of 1,000 classes for each image. Okay, and I would actually argue, I mean, kind of following on the Dave Donahoe position, I think that at this point it's kind of incontrovertible almost that deep learning doesn't exist if ImageNet doesn't exist. It's like the existence of this kind of challenge data set is why we have had these like massive revolutions. I mean, more just this culture. Okay. So with that, the funny thing is, like, so actually, sorry, let me go back a couple of slides. With that as motivation, I think it behooves us to really start trying to talk about, what's going on over here? Can we put down some kind of mathematical foundation, some understanding of what's going on over here, and kind of add it to like our intellectual frameworks that we're using? How do we actually understand that? Okay. All right, so let's talk about supervised learning. And who here knows how they constructed the ImageNet data set? Does anybody know how they did this? Kind of. 2.5 of you, 1.5 of you, some 5 of you are admitting it now. All right, so if I got something wrong, correct me. I will probably screw this up slightly, but that's fine. Okay. So the usual machine learning story when we teach our classes or statistics, whatever you want to teach, is there's an input data, it's X. Then there's some noisy label Y that somebody assigns to the image, or like it's just something we observe later, so we don't know anything with perfection. Maybe somebody says this is a dog, somebody says it's a golden retriever puppy, somebody gets confused and calls it a cat, right? There's some noisy label Y that comes from this image, and we have X's and Y's, and the Y's are noisy. Okay, and then the machine learning pipeline is you feed a bunch of pairs in, magical fitting happens, deep learning, transformers, whatever, and then we output some model that makes predictions Y hat equals f of x. All right, that's the standard story we tell. We all know this story. Now, if we actually look at how we constructed ImageNet, it's kind of wild. I mean, it's ingenious, but it is very, at least to my thinking, very different from this. So what they did when they constructed ImageNet, they started with this database called WordNet, which was a hierarchy of relationships between different entities. And you started off with entity, and then you could have units and conveyances, and it went down in this huge tree all the way down to say like motorcycles, cars, bicycles as kind of the leaves in this tree. And what they did is they picked out 1,000 of the leaves in this tree, so motorcycles, cars, bicycles, and then they went to Flickr and they downloaded a huge number of images that were tagged with the particular word of interest. So in this case, this image is tagged with the word bicycle. Okay, so they got all these images that were tagged from Flickr with the word bicycle on them. In this case, if we're looking at bicycles. After that, they went to Mechanical Turk. They would show web pages to individuals, and then they would say, okay, select every image that contains a bicycle. All right, so you'd go on this image, and if you're a Mechanical Turker, this one probably not, because that's just a bike wheel. But yeah, this one looks like a bike. That one maybe contains a bike. I don't know what we're going to say about this one. Maybe it does, maybe it doesn't, right? So you go through and you select all of the images that contain a bike. Then after that, they went through and they filtered things. And they said that basically include a particular X, in this case, an image. And this is not quite correct, but let me work through this. They said include X, an image as an example of the Y equals bicycle class. If I wrote if the selection frequency is bigger than 70%, if the selection frequency is in the top 1,000 of these images. Okay, and so for the hardest classes, these selection frequencies were something like 70%. For the easiest ones, these selection frequencies were much higher. All right, and that's how we constructed ImageNet. All right, and now I think, and then we repeated this, not we, they repeated this for 1,000 different classes, bicycles, cars, motorcycles, 121 breeds of dog, it turns out. And what is this? I mean, it's ingenious, it's clever, it's surprisingly effective at getting a really nice big data set. I don't think what it is the way we think about labeling it. It's not just I got an X and then I got a noisy label from an individual, right? I don't think this is the same as that. I mean, there's still labels for images, but it's not how we think about the standard kind of image generation process or label generation process or anything like that. Okay. All right, how people feeling? Thumbs up? Okay, we got some thumbs up. That's good. All right, so anyway, with that, I think it's important then to start to think about, okay, and well, how much does data construction actually matter? Like, do these choices that they've made actually matter? And there's a paper I really like by Ben Reck, Becca Roloffs, Ludwig Schmidt, and Vatsal Shankar called Does ImageNet Generalize to ImageNet? And this was published about 5 years ago. And what they did is they tried to reconstruct the ImageNet data set using exactly the same labeling process, okay? And what they showed is that, or what they saw, what they observed was that, and they very carefully tried to do this, that when they did this, the actual accuracy on a new constructed data set, which was supposed to be from the exact same distribution as the original data set. Now time had passed, it was 10 years later, so there were some changes on the ground. But they observed something like a 10+ percentage point gap in absolute accuracy when they tried to reconstruct the test data set. Okay, and what I'm plotting here, or what the plot I'm reproducing here, what it's showing is a scatter plot of model performance. So each of these dots represents the performance of a model. Excuse me. The horizontal axis is the accuracy of the model on the ImageNet version 1 test set. The vertical axis is its accuracy on ImageNet, the new version. And so this dotted line is identical accuracy. And what you can see is there's kind of a 10% difference between the two. All right. And so I think, this is just evidence. And the methods that when we do these predictions, they're quite overconfident. They don't actually reflect reality in terms of their own error rates. So I think this is just kind of evidence that this whole idea of data set construction and how we think about it does really, really matter for the performance of these methods. Yeah. No, it's not that it was easier or harder. The performance was worse on the second one. Sorry, did I misspeak? So original test set accuracy is 80% here. Accuracy on the new test set is 69 or 70%. The same classifier. So all they tried to do, and I mean there are, we could actually spend a ton of time talking about this paper and making arguments about its validity and things like this. They tried to just make a new test set. Okay, so they just said, okay, we have an ImageNet test set. We're going to try to now just have a completely new test set that no one could have overfit on or like done any kind of data peaking to try to tweak their models to do better on the test set than other models did, and all sorts of things. And they actually, I think there are two astounding things in this plot. One is that there was still this 10% gap in performance. The other astounding thing in this plot, and this is kind of wild, is that the relative ordering of the methods is completely the same. Okay, so there was some overfitting in that there is a 10% gap, 10 percentage point drop in performance, but the best models are still the best models. Yeah, sorry, question. Oh, this doesn't imply, sorry, that's an also. This does not imply that the methods are overconfident. That's another problem with these methods. So the question is, do the methods make the same kind of mistakes? And no, that's a very good question. And I want to say the answer is no, because there were additional experiments that I'm not reporting or discussing where I believe they looked at exactly where they were making mistakes. But I'm not super confident in that. It's a bit nuanced. It's not, they don't make exactly the same kind of mistakes. They're not totally different. And I don't feel comfortable saying more than that because I'm going to be very quickly very wrong. Sorry, Renee. Yeah. Yeah, no, this is the thing. I mean, there is definitely they fixed the resolution though. I mean, every image is the same size, so at least the resolution is the same because the images are exactly whatever it was, 256 by 256 or 1024 by 1024. So the resolution is the same, but it's true. Yeah, 10 years have passed, right? There's the original data set 2009. There's this new one in 2019. Flickr has changed. The images they're downloading have changed. They're using exactly the same. I mean, the mechanical Turkers have changed, right? There's different humans participating in this, right? Or even if they're the same humans, they're 10 years older. So yeah, admittedly, it's hard to control everything. I will say, I actually think, I've spoken with the authors quite a lot. I think the paper is very impressive, and I think it's I actually do think they did it conditional on that 10 years had passed, all of this stuff. They did a really good job of trying to control as much of this as they could. Anyway, but I mean, I guess at some level, all I want this to be is evidence for this thesis I'm making, which is that we should be studying the whole pipeline, like from data set construction to model release, not just like the core innards of how we do all the fitting and stuff like that. Just because the way we make progress is so fundamentally tied to these challenge data sets and things like that. So hopefully that, at least that part of my argument, hopefully is believable. And then there's a lot more. Yeah, sorry. Right. Well, so that's an interesting question, right? I mean, this is, I think, one of the reasons this is so remarkable is that, like, literally the accuracy. I mean, you can see there's a best fit line. The accuracy is on a line, right? Like, I can predict your accuracy on the new test set linearly from your accuracy on the previous test set, or affine actually, because I have to add an intercept. I call it -10, right? And so that's kind of wild. And at the same time, there is still a 10% gap in performance, right? So we could call that whatever we wanted. We could say, like, there's some overfitting, and yet there's this wild phenomenon where the ordering doesn't change, and who knows what's going on. I don't know what's going on, right? I think it's striking, I guess. Okay, sorry, one more question. I certainly don't. I don't think any of them know either. I mean, there's a gap because of, time is 10 years went by. Like, so that's why there's a gap. But why specifically, who knows, right? Things are a bit different. Yes, all right. Hope. Nothing has changed. I mean, the only thing that has changed is 10 years have gone by. And so there's just a slightly different composition, presumably, of images that we're using. But we used exactly, they used exactly the same process as the original construction. Okay. All right, let's keep going. Okay, so for the remainder of this talk, what I'm going to do, I mean, I think it's clear that we are all finding this, I mean, given the questions, I think it's pretty clear we're finding this kind of phenomenon fairly interesting, right? Surprising, interesting, whatever you want to say it. And so for the remainder of the talk, I'm going to try to give an extremely stylized model of this data set collection and construction process. No, sorry, I will succeed in giving a very stylized model. I will also analyze that model and do some experiments. And then after that, we'll argue about whether anything I've done makes any sense. Okay, or we could argue while we do it. That's fine too. All right, so we can continue that. Okay, so that's what I'm going to do. Let's try to start understanding some of this. All right. Okay, good. Okay, so steps. Step 1, we propose a model. Step 2, we analyze the model doing math. Step 3, it's going to make some predictions about what should happen in the real world. And because I am totally happy to be wrong and I believe in the scientific method, I'm going to test these predictions. And either we're going to be correct or we're going to be wrong, right? So one of those two things is going to happen. And so we're going to see what happens. All right. Okay, so that's the game plan. Okay, so let's start with the model. And I will be the first to admit this is an extremely stylized model. Like, I have made this as simple as I can because I want to be able to do math, and I can only do so many math things. Like, I mean, my students can do more math, but I can only do a little bit, right? So we've got so here's the game. I have a binary classification problem. I'm going to have m labelers. We're going to just imagine there are m labelers, m for number of measurements, m measurements of each example. So I have x is my examples. They're a d-dimensional vector, labels y and plus minus 1. And then we're going to make this the usual sort of kind of basically logistic regression type assumption that the probability that y equals to y, given x equals x, is sigma of y times x transpose theta star. Okay, so theta star, we're thinking of this as something like the true parameter. And we have that y x transpose theta star. This is the margin of the particular prediction, right? And when this is very negative, we are more likely to output y equals -1. When this is very positive, then we're more likely to put out y equals +1. Okay, so this is just the probability that we assign a particular label to something. We get data in tuples. We're given an individual x. We observe y1 through m distinct measurements, IID from this process. And I'm going to assume, so here's where we're just going to go totally off the rails in assumptions. I'm going to assume my covariates are just Gaussian IID covariate vectors, okay? So about as simple as I can make it. Everybody copacetic here? It's a $10 word for okay. Yeah, well, you guys are like, like Wharton professors and stuff. You guys are fancy. Okay. All right. So continuing the model, I'm going to have a loss function because we're going to be doing loss minimization just like we always do. And that loss is going to just satisfy that its derivative is, there's a particular sign convention here, but basically that the loss reflects this, this link function. Just the derivative of the loss corresponds to the probabilities that you assign to a particular label. So what you should be thinking of is logistic regression, right? So the derivative of the logistic loss, log 1 plus e to the t, This is the loss. It gets smaller when my predictions are more correct, right? So when my predictions are more aligned with reality, my losses get smaller. And we're going to have that the loss is such that it just matches up with this, this link function, this probability of correctness. Okay, everybody cool with this? So this is just standard, vanilla logistic regression that you would teach in machine learning 101, something like that. Okay, so that's our game. And now we're going to, at least for now, I'm going to be thinking about having two estimators. Okay, and we're just, and because I can't analyze sort of sophisticated multi-layer, labeling processes or anything like that, we're going to only consider two very simple estimators. One is I just toss in all of the labels to my method, and I minimize this. And if this is, you could think of this as like the maximum likelihood estimator. Okay, I just toss in all the labels. I minimize the average loss over both my sample, my sample data set and my labels, and that's what I do. And my alternative, and this is kind of my stand-in for like data cleaning or label aggregation or any kind of aggregation. Sorry, I can't spell. This is going to be my stand-in for any kind of sophisticated labeling process that we use to clean our data. And I'm going to use a very simple one, which is just that on example I take a majority vote of Y1 through YM, and I say that's the label for this example. Okay, if more people agreed that it was positive, I'm going to call it positive. If more people said it was negative, I'm going to call it negative. All right, so these are my two estimators. Uses all the labels, and I do a majority vote. All right, okay. And then we're going to ask about two quantities. We're going to measure error, measure performance of these methods in two ways. And one is going to be what I'm going to call this the calibration error, which is really just, the error in my estimate in theta hat as an estimator of theta star. Okay, and then the other is going to be, I'll call this the classification error, which is when I normalize. So I'm going to have U star be the normalized version of theta. So this is just theta minus theta divided by theta star divided by theta star. And I'm just going to ask, when I look at the direction that I'm predicting, is that aligned with the actual correct direction, right? So I mean, in pictures, you think of a decision boundary. Here's our decision boundary. Here's the sort of somehow the truth is the true decision boundary, so that everything, any example on this side is a positive, any example on this side is a negative, and then I'm just going to ask how aligned is U hat equals to theta hat divided by theta hat to this somehow the true decision direction. Okay, so I'm going to be asking about these two quantities. One is we recover theta star, the other is do I just recover the right decision rule? All right, and I should just say in the case where we have Gaussian data, this error is really basically proportional to your expected number of mistakes. Okay, so are we cool with this? So these are the two quantities we're going to look at. All right, so with this setup, let's now just talk about convergence of the maximum likelihood estimate. So this is really just stats 200 or something like that, like your first class in asymptotic statistics. Listen, I'm going to use theta hat n minimizes this log loss. And as long as these models are all well specified, you really got data from the true thing, well, we have this classical result that says, so classical statistics, what does it say? Classic statistics says that, that theta hat, when you are well specified, is approximately normally distributed with a mean of the true theta star, and then 1 on n is the sample size times the Fisher information, inverse Fisher information, sorry, I should remember this. The inverse Fisher information at like the true model. Okay, so classical statistics tells you that this should happen. These are the asymptotics you should get out of this. Okay, let's unpack this a little bit. It's kind of a funky looking theorem. Let's just try to understand what's happening a tiny bit here, okay? All right, so unpacking this a little bit, what is this saying? Is that one, there's this asymptotic covariance term. So I'm just going to call this, we'll just give this a name. We'll just call it sigma. It's just some covariance. Some covariance. And there's this multiplier in the front, which scales as 1 on m. Okay, so remember that m was the number of labelers that you had. And this is saying that, you know, if I give an increase, a linear increase in the number of labelers, my asymptotic error decreases at exactly the same rate. Okay, and we can also do this with our errors in terms of the actual classification errors as well. Okay, so writing this a little bit differently, this is approximately saying that u hat n, which is equal to theta hat n divided by the 2 norm of theta hat n, is approximately distributed as normal with mean, oopsie, the true classification rule divided by 1 on n m times identity minus u star transpose, and then this kind of constant normalization. Okay, so asymptotically, our error goes down as 1 on n, the sample size, times n, the number of measurements. That's good. That's exactly what we would expect from classical statistics, right? Okay, how are we feeling about this? Everybody's cool? All right, so now let's talk about what happens when we actually have the majority vote estimator. So things are going to be a little bit different here, and I'm going to need a tiny bit of notation, and so forgive me for the slight notational overload. So remember, what are we doing here? I have my empirical loss, which is just my loss on the cleaned labels. So remember, these guys are now cleaned up labels, or these are my stand-in for whatever our sophisticated data labeling process is. And what I'm going to do to state the result is I'm going to decompose my x vectors into the variability in the direction of the truth plus kind of some orthogonal component. Okay, so this is the variability in the kind of correct direction. U star direction, that's the true classifier, or the sort of unit direction of the true classifier. And then this is just extra noise. And now what happens here is you get the following result. Okay, and I'm going to try to unpack this as we go through. So what happens is you still have convergence. The estimator still converges with the clean labels, but you get this slightly funnier behavior, okay? And it's kind of a sophisticated, it's a kind of a complicated statement. What you get out of just computing a bunch of integrals very carefully, but let's unpack this. So first things first, sorry about that. The majority vote estimator, it converges to have the same direction as the true classifier, but the scale of it is all messed up. So it basically, it's sort of saying that theta hat n with the majority vote is somehow approximately equal to square root m times u star. Okay, so it's like much bigger than it should be. It should be somehow like of scale 1, and instead it's like growing with the number of labelers we have. And it's also asymptotically normal with some kind of crazy formula here. But the point is, when you unpack this formula, what you get out is, you know, roughly that u hat majority votes, that is to say the direction I'm picking, is approximately normally distributed around the true u star. So I normalize things correctly. It's giving me the right decision rule, but the asymptotic variance looks like 1 on n times square root m times some kind of covariance term. Okay, so your error goes to 0. You learn the correct decision, but the rate at which it happens is slower. So remember on the previous slide, we had a 1 over m here, and now we're kind of getting this slower convergence of 1 on square root m. So things are somehow a little bit different. Okay, so that's, at some level, this is like the entire main 2 theorems of the paper. We actually have a bunch more, but I want to unpack these a tiny bit to try to understand what's going on. So big picture, when you use all the labels, asymptotic variance goes down as 1 on the number of labelers. When you clean the labels, asymptotic variance goes down as 1 on square root m times the number of, which is like not as fast, right? You get this kind of different behavior. Let me see what I had. Yeah, okay. And let me say a few things, and then we'll kind of unpack a little bit of intuition for what's going on here, if that's okay. Let's folks have questions on these 2 statements. Oh, okay. So the funny thing here is there's a few things that are happening. One is when you're using the clean labels, like at some level, because you're actually effectively misspecified, right? You use a majority vote, you're kind of converging to something overconfident, right? You're actually learning a classifier which predicts what are m individual labelers going to kind of be most likely to predict here, right? And so that correspondingly, you're going to be overconfident. All right, so you have this kind of overconfident behavior, but and so you get improvement for increasing the number of labelers. It's just not as fast as it could be. But the take home is that this majority vote is uncalibrated, it's overconfident, but at the same time, you get this behavior where it is actually more robust. Okay, so it doesn't actually matter if you have a correctly specified link function. In fact, you don't. You're fitting the wrong model. But because you clean the labels, you're still getting convergence to like at least the correct decision. All right, and if you actually had a model that was powerful enough to kind of represent the truth or represent like the actual statistical process, then cleaning up the data is going to hurt you. All right, so if your model is good enough to represent uncertainty, then you should use that. You should use it. Okay, so that's I think that's at a very high level. This is kind of the prediction or the take-home message. That if you have a very, very strong model, you want to, at least our theory suggests, you should use all the data. While if you have a model and you're not totally confident in its ability to capture all the intricacies of whatever data generating process you have, well, maybe it makes a lot more sense to actually clean the data because that's going to give you better performance and be more robust. That's kind of the two take-home messages. Any questions about those as take-home messages? No, feeling good. Okay. Sorry about that. Okay, let me talk a tiny bit about why this is happening, just to give some kind of intuition about what's going on. Oh, sorry. Is that true? Do we have 1 or 2 or 3 raters? Like, so here in ImageNet, they had like 50 raters for image class. Okay, so M being 50, like square root of 50 and 50 are different numbers, right? Right, square root of 50 is 7. Yeah, thank you. 49. They have 49 raters for turns out. They actually they knew this paper was in the pipeline 14 years ago, right? Yeah, so they have 49 raters per image. Square root of 49 is 7. So that's a big difference, right? Or potentially a big difference. And I think you should also have caution. Like, I'm telling you, this is what the theory says. Like, this is theory in this kind of wackadoodle model that I just made up and pulled out of my pocket, right? I was like, hey, I love Gaussians. Like, let's assume that X is Gaussian. And I was like, hey, I love logistic regression. Let's make Y equals just a logistic regression, right? I wanted to prove some theorems. I wish I was a mathematician, but I'm not good enough for that. So then I do statistics instead, right? They don't let me teach the probability classes at Stanford. Okay, so anyway, so here we are. So let me try to give a tiny bit of intuition for this, for what's going on here. We'll just give ourselves a kind of a clear slide here. Boom, boom, boom. Okay, so I said that, for the majority vote, we're getting U hat n minus U star, sort of square root n times this, is converging in distribution to some normal with mean 0, and its asymptotic variance scales as 1 on square root m times some stuff. Okay, and I'm going to kind of punt on this stuff. So let's actually think a tiny bit about what's happening here. So if you're super familiar with excuse me, if you're super familiar with like logistic regression and things like this, the convergence of if I have any estimator that is solving some kind of loss minimization problem, right? What do convergence rates of that thing depend on? They depend on strong convexity, right? So we all know that estimate convergence rates depend on strong convexity. The more curvature your loss function has, the faster it grows, the easier it is to get to the bottom of it. Everybody agrees with that? That's kind of what we know. Okay, so let's think about what that looks like in the case of logistic regression. So this is L of theta. And what we know is that, when we have estimation, you're minimizing some convex function, then kind of like your estimation accuracy is somehow going to correspond to when the strong convexity, that is to say grad squared L of like theta star, say, is kind of commensurate somehow with the kind of variance in your gradients. Okay, so as soon as kind of the upward curvature of your loss dominates any variance in your gradients, then you're in good shape. Okay, that's kind of how our estimation trade-offs work. The curvature has to dominate the variance. That's how we know things work. Okay, so taking that on faith, let's ask ourselves about logistic regression. So I have a loss function, which I will write as L of t is equal to log 1 plus e to the t. L prime of t should be equal to e to the t divided by 1 plus e to the t, and L double prime of t is equal to e to the t over 1 plus e to the t times 1 minus e to the t over 1 plus e to the t, which is like, I'm going to write that as p of t times 1 minus p of t. It's just the variance of a Bernoulli. Okay, so it's kind of, this thing is constant when p is kind of close to, 0 or something like that. So there's a lot of curvature. So what does this thing's Hessian actually look like? It looks something like this. Well, here's p. No, it doesn't. I'm sorry about that. What does this thing actually look like? It's 0 at 0, and it bumps up, and then it bumps down. Okay. And so all of the action is when all the action, all the kind of curvature is when you have something like, basically that theta transpose x times, the probability that y equals to some little y given x is something like it's something in the neighborhood of about a half. Okay, so all of the action, all of your curvature is right there at probability 1/2. And if you get too far away from that, you have no curvature, there's no more signal. Now, when you clean up data, what's the probability that, the sign of theta star transpose x is equal to the majority vote of y1 through ... ym? So if I get m measurements, this is just a binomial probability. What's the variance of a binomial? I'm teaching intro probability. My students could answer this, and they're all like 10 years old. You guys can do this. Sorry, it's a little cruel, but and that was a lie. They would not answer this. They'd stare at me and shrink in their seats a little bit. So I appreciate that all of you guys are not at least like, that's the standard error. But yeah, but you're basically right. The variance is m. The standard deviation is square root m. That's exactly right. Okay, and so the actual variance of this, of a binomial, mp, is equal to m times p times 1 minus p. Okay, and so somehow the places where we are unlikely, oopsie, that was the wrong button, and I can't even write that back. That's okay. X equals to the majority vote of y1 through ... ym. So because this is the variance, somehow the only places where we're getting probabilities neighborhood of a half, like we have any uncertainty at all, are places where the the actual signal strength is extremely small. Okay, so we're only going to get only signal is available if the probability of success is something like 1 on if the probability of an individual success is like 1/2 plus or minus 1 on m. Okay, so somehow you're losing this massive fraction of examples, like everything where you're very likely, where there's actually where you have a strong probability of being correct, you lose all the information. And so the only place where action is happening is in this very small neighborhood of 0, like theta transpose x. It turns out, you can work this out, it needs to be something like 1 on square root m. Okay, and you're just not going to have that often. So you have to have very, very small margins to actually get any signal at all. Okay, and it turns out that, so here's a funny fact, and I didn't state this, but there is actually a fundamental limit, meaning there's an information theoretic lower bound that says if you actually clean up your data, that says this 1 on square root m scaling is sharp. and I'm not going to talk about that, but it's unimprovable. So you really are this result, that right there, is as good as it can get. As soon as you clean your data, you are forced to have a slightly slower convergence than if you could actually model things correctly. Okay, all right, question. So the question, if I'm understanding it, is, does this say we should be somehow perturbing our data to add more noise or something like that to get our classifier stronger? Probably. I actually have not thought about that, but it's a good question. I don't have a good answer. Yeah.
Are you saying that the ImageNet shouldn't have clean data, and then if we had access to what?
That is the hypothesis that this generates, yes. And unfortunately, and I'm friends with the people who made ImageNet, they lost or just didn't keep track of all of the intermediate labels. We don't have access to that data. It was in some version control repository somewhere 10 years ago, and it's gone. Because I asked them for that, and they didn't have it.
So like in this binary case, the extra information is just what fraction is.
Yeah.
One, and so.
Exactly.
Yeah.
Yeah, it's very, this binary case is very simple. What's the fraction of zeros and ones? Yeah, it's totally trivial what at least what I'm saying you should collect based on this simplified statistical model. Yeah. Why don't I do that offline so that I don't derail us? But yeah, let's do this. We got a chalkboard. We'll do this in the intermediate sessions. Yes. Yeah. What if they're not? That's a good question. Then, of course, we proved more theorems, which have nothing to do with reality, but we did it because we could. Sorry, well, I'm just trying to be honest, right? Like, I'm not going to pretend. But so we have these things. We could do what's called a semi-parametric approach, where if we have M labelers, you can actually try to, this is not this slide. Let's go with this slide. How about this? Okay. Where what you're going to do is you can try to estimate the link functions that the individual use. And now this is again a simplified model, but what you can show is that if you do this, then as soon as you can estimate these things consistently, I don't care you can estimate them fast or slow, just that you can estimate them at all, then you actually recover the sort of efficient estimator. So once if I have a good estimate, or even any halfway reasonable estimate of how good my labelers are, I can use that, minimize my losses, reflecting the particular labeler accuracies, and I will get improved performance. How's that? But again, this is still stylized. I don't totally know the answers to that question. Like, we have some evidence that that's a good idea, but it's like not perfect. Okay. Any other questions before I start talking about experiments? Yeah, sorry, Renee. Yeah, so, okay, so I'm not sure I'm going to answer that perfectly. I'm going to give you sort of two answers here. One is that so this fundamental limit we proved says that if you clean your data first, like, you can use any strategy you want to fit a model. I don't care what it is, but there's an information theoretic lower bound that says you have lost a fraction of 1 on square root m of your data. Like, no method can fix that. Once you've cleaned the data and taken out these majority votes, you're done as far as that goes. Now, are there other losses that are somehow intermediate between, like, something that uses auto labels versus something that uses majority vote and somehow, like, partially cleans things? I don't know. That's a good question. I don't have any great insights there. Yeah, On the fly, I mean, on the fly, yeah, that sounds like a great idea. I don't know exactly how I would do it. Okay, let's go ahead and do a few experiments here. So, you know, I'm gonna try to put on my science hat, like and do the scientific method that we all learned when you're 10 years old, which is if you have a hypothesis and you try to falsify it. Okay, like, I'm not going to be right. I'm just going to get data that's either consistent with what the math I did, or the math I did is nonsense, right? Okay, so as I said, unfortunately, there aren't a whole lot of data sets. So we're going to be stuck with a few smaller data sets, and then we kind of generated a semi-synthetic data set to play around with stuff. The first two are going to be just a binary classification thing of bluebirds versus, blue grosbeaks versus indigo buntings. Okay, so there's your indigo bunting, there's your blue grosbeak. These are actually confusable birds, right? Okay, and then the second one is Tom Griffiths, Olga Rysakovsky, and two of their students actually did generate a small, but unfortunately it's quite small, data set of a 10-class classification problem based on CFAR10, an image recognition problem with tiny images, where they actually did have multiple labels per image. Okay, and in this blue grosbeak versus indigo bunting thing, we also have that. And so what I'm plotting here is we ran a resident on this, and then we ran PCA on the top layer to get a fairly small model. And in this experiment, I'm showing you the results on bluebirds. Okay, so indigo bunting versus blue grosbeak. And on the vertical axis here, we're seeing classification error. Horizontal axis, we're seeing what happens as I increase the number of labelers M. And at least in this experiment, which is fairly small, you know, it's just a binary experiment with some birds, we do see that there appears to be a gap between the methods. So blue line is full information, as in like I included all of the noisy labels, all 35 of them. Red line is what happens when I do majority vote. Both of them get better in terms of classification error, but there is a gap of something like 5% absolute percentage points in accuracy. And that's the left plot. And I'll get the question one second. The right plot is showing you the errors in the log probability, where p hat is our estimated probability of being a blue grosbeak or an indigo bunting, and p turk is the probability on a held out set of mechanical turkers that they assigned their average votes to to being one of the particular birds. And so you can see there's a massive gap there. Like the majority vote one never gets calibrated. It's just wildly overconfident all the time. Okay, sorry, there was a question here. Yeah, that's a good question. When we compute classification error, does this even make sense? At the end of the day, we had another like total of 70 labelers, and we used the majority vote for them, for those 70 as the truth. Yeah, it's true. I mean, I don't have a perfect way to do this. If you have a better experiment to do on all. No, he doesn't. Yeah, that's okay. I mean, these are good questions. I don't know all the answers. Yeah, sorry. What's that? Oh no, these are that 0.3 minus 0.25 is 0.05. No, these are this is like point. Those are numbers. Yeah, those are numbers. Sorry. That's like 0.3, 30% accuracy. Yeah. Well, I mean, I don't know what's going to happen when M becomes 10,000, right? Like lots of curves can go down more slowly. Like 1 on square root M does not go down very quickly. In spite of what people who analyze stochastic gradient would tell you, 1 on square root T is very, very slow. And I mean, 5 years ago, I would have told you it's fast. In fact, tomorrow I might tell you it's fast when I'm talking about optimization. But today it's slow. How's that? Okay. I don't have to be consistent. Okay. CFAR10H, we sort of see a similar thing. So I'm not going to bother spending too much time on it. And now for our last experiment, as I said, we don't have big data sets that we know of, at least. And so what we did is we generated a semi-synthetic. And how we did this is we actually took CFAR10, the whole data set, so 60,000 images. And I mean, that's not that big now, but whatever, we wanted to run it quickly. And we regenerated this. We took a ResNet 18, so that's an 18-layer residual network. So this is kind of the vague form of it. You have convolutions and then a bunch of residual layers stacked on top of each other. And then at the end, you output a classification label. So what we did is we regenerated labels using a prefit ResNet 18. And then what we did is we would vary the accuracy of these ResNet 18s to kind of simulate different labeler accuracies. Okay, and so we would say, okay, we're going to have 50 different ResNet 18s. And we're going to make each of them have different accuracies. Some of them like, 80%, some of them 10%. So they're just random guessing. We're going to throw all their data in and see what happens. Okay, does that big picture make sense? Okay, so, so this thing comes in, it goes through this whole thing. And then, in this case, like, what is that? 7 out of 12 of them said it was a bird, and a few of them said it was a ship and a dog and some other stuff. Okay, so we're going to generate a data set doing this so we can actually get multi-labels. And here we have, we kind of know the ground truth because we have the residual networks. So when we did this, this is what we saw. And, let me unpack this a tiny bit. What we're seeing is like a little bit of a mess, but we can kind of get some sense of what's happening here. So on the left, and I'm sorry, we also applied, in addition to majority vote, we also used 2 crowdsourcing methods. So DS corresponds to what's called the David-Skeen crowdsourcing procedure. And this GLAD is I forget what the abbreviation is, but it is another procedure for imputing labels from data. Okay, so we also used some crowdsourcing procedures, and these probability ones also try to assign probabilities to the labels and not just hard labels. And what you see is sort of a similar story. That is, the number of labelers increases. And here again, we have a well-specified model because we generated the data. But as the number of labelers increases, the MLE, the thing that uses all the data, does continue to improve in terms of test error here. Okay, with 1, I have a test error of something like, 5%, and then it goes down to like 0.1%. Or maybe that's like 1%, I don't know. And the other methods don't go down quite as far. And we see this similar behavior across many different median labeler accuracies and numbers of labelers. All right, and so with that, I'd just like to stop here. I mean, I'm out of time anyway, so that's good. I think there's still a lot of work to do here. I will be the first to admit this is a very particular model. We were only able to do certain limited experiments because this is the data we have available, at least as far as we know. But I think it's really important to start thinking about data set construction and this kind of fuller pipeline of machine learning. I hope many of us start to do some of this. I think there are interesting questions about would obtaining data with human perceptual uncertainty help us build better prediction methods? And also, we did make some theoretical predictions here, and we could have been wrong, right? And at least the data we observed was consistent with what our models predicted, but we could have been super wrong. It was kind of fun when we first saw those results, right? Like we didn't know what was going to happen. And I really do think there are some interesting questions for like large language models and the data set construction we use when we actually fit these. We mush together all sorts of data sets from across the web and things like that, and it's not completely clear what effect those have and how we should be understanding them. So I think there's some really nice future work questions. I'll stop here. Happy to talk more, and thank you guys so much. This was great.
All right, given that we're already right on time and we had many questions, let's just thank John one more time and
Beautiful.
take the rest of questions offline.
Sweet. I'm done. Am I done? I'm done.
You are.
Okay.
Okay, So next we have Alejandro Ingrosso, who's going to tell us about statistical mechanics of transfer learning. So please, let's welcome him.
Thank you. Thanks for the introduction. So what I'm going to tell you about today is a very recent project that has been sort of inspired by Federica Gerace, and it's also with Rosalba. It's kind of related to what you heard about this morning in her talk, and Pietro is also here, and he has a very interesting poster for today, so tomorrow actually. So check it out. So we're going to start talking about transfer learning. What is transfer learning? I'm sure every one of you knows what it is, but just to set the discussion for later. So it's a very kind of very convenient way of teaching, because you get to just replace the student's brain completely. So in deep learning lingo, you have a large public data set, let's say ImageNet, and then you train, say, a very large convolutional network on this. And then you take all the weights and then you transfer the weights, or partially some weights, onto possibly smaller or basically like the same architecture. But when you train on a small data set, when you're basically prone to error fit. Okay, so you don't have enough data. And this is a technique which is used to fight overfitting. And it's not a chance that I'm showing this kind of data set, because this almost always happens in like the medical case, in which we don't really have so many data and we don't really have so many patients. And I'm gonna call this the source task and the target task when you're prone to error fitting. So some phenomena. I'm sure there's a lot of papers describing this, because this technique is nowadays used, and I mean, you guys know LoRa and all this stuff in LLMs and ChatGPT. So I'm gonna tell you about some phenomena. I haven't read most of these papers, I've read some, and I'm gonna tell you about this layer-wise deep transfer. Very recent work by Federica Gerace and people at CISA in Italy. So what they did was they studied the problem of transferring just layer-wise in a very deep network, which is basically the same network we saw like 5 minutes ago, I guess. So it's a ResNet, an 18 layer ResNet, which is pre-trained on ImageNet, and then it's again trained on a way smaller data set on breast cancer data, in which basically you have to compare benign versus malignant kind of tissue, okay? And what they did was they trained by selectively transferring weights from, say, the first layer up to the 17th layer. So in this case, you have like the weights are transferred up to layer L. That's what they call transfer depth. So this guy here is a case in which you don't transfer anything, okay? And here in this case, you transfer up to the 17th, so you just retrain the readout layer. And as you can see, the test accuracy is not monotonous. And it has this maximum here, which basically tells you that there is sort of an optimal amount of transfer weights in this case. So you better transfer all the weights up to this layer and then retrain the last 2 or 3 layers, okay? And also this depends on the training size. So you take the training set, you can subsample the training set. This is the smallest possible training set here. And you can see it has this peak, which is very close to the readout. So you transfer all the layers up to this point. But then as you crank up the number of patterns in the data, so you can sort of see that this peak is slightly shifting to the left, okay? So basically what this is telling you is that there are some features, you're using the feature from the pre-trained ones, but then you can afford to retrain and to learn new features if you have enough data, okay? And so this peak is kind of shifting to the left. It's telling you that you're learning low-level feature on your data set. There's a bunch of other interesting points in this paper, and they show that if you construct some sort of clones of the data set, and these clones are effectively different source tasks that increasingly approximate the target task, okay? You can afford to transfer up to deeper in the layer. So for instance, in this case, you have a network which is trained on ISOGM and transfer, and they're using a Gaussian clone, which is preserving just the average per class, and then it's just a ball, an IID ball, okay? In this case, they're actually using a Gaussian clone, which is preserving both the averages and covariances per class, and so you can afford to take the weights which have been used to train on GM to a Cypher10 target up to a certain transfer depth, and then in this case, you sort of first train on an autoencoder clone, so you have a strong similarity between the source and target task. You can just reuse all the features that have been previously trained and just train the last layer, okay? Train the readout. So transfer learning depends on the similarity between the source and target task in a way which sort of depends on the hierarchical way in which, say, the features are in your data set are constructed, and the way in which these are represented in the hierarchy of the deep network. Some theory that we have so far. So we had theory, at least for the single layer case, so like perceptrons, basically, trained on random features or on features which have been sort of transferred from a previously learned model, okay? And the only possible theory so far was making a theory for the readout, but with correlated feature which have been instructed from a pre-trained network. So I'm going to tell you about this very interesting work by the Zdeborova and Sarkala group on the correlated hidden manifold model. So right now I'm going to tell you just very sort of give you a qualitative introduction, and then we spend a little bit more time later actually discussing how they construct this synthetic data set. But the idea is that this is a very simple synthetic data set in which you can control the level in which the features in the source and target task are related, or the labels in the target task are related. Target and source task are related, okay? So you have procedure to generate the inputs and the procedure to associate the input to a certain output. And then you can construct some correlation between the labels and correlation between the features, okay? So what they do is that they first train a single hidden layer neural network. So they both train the first and the second layer, W and V, and then they take the WS and then just put it in another network, which is trained on a similar task, say, similar synthetic task, and they just retrain the second layer, VT. And they can do the theory for V, taking a certain covariance matrix, which is extracted from these features, okay? Using Gaussian equivalence principles in which you can just return the second order moment, and then you can compute the whole training and test error. So, okay, more on this later. I will be more precise later. So what they find is that they get learning curves, which are extremely similar, at least at the qualitative level, between real data. So I guess they did it on IMNIS and on Cypher and the synthetic data set, okay? Here I'm showing the test loss as a function of the usual ratio, a usual list in the statistical mechanics formulation of this kind of stuff, between the number of patterns and the neurons in the first layer. And I'm always going to work in this limit in which P over N1 is order 1, okay? So this is called the proportional limit. And so as you can see here, the curves in the synthetic case and the real case are kind of almost the same, at least at the qualitative level. And just look at the difference between the random feature case, which is this orange curve here, and the two transfer feature cases. So the blue and the light blue and the other blue, in which there can be or not fine tuning, meaning like you first transfer and then you train a little bit with a smaller learning rate. And so you see the transfer is always better than just regenerating the features, okay? And there is a regime, this whole regime, in which transfer is always better than actually train the first layer, because you don't have enough data, and so you lower fit. And so at some point, of course, this green line, which represents the two-layer case in which you both train V and W, at some point there is a crossover, but in this regime here, you will always overfit, okay? So transfer learning is better. And in this kind of case, you can use a lot of toggles here to control the similarities between the features, similarities between the labels, and do a lot of experiments. So from here, we take as a take-home message the fact that this simple synthetic data set can actually recapitulate what happens, so the transfer learning phenomenology, and you can improve generalization, but you can do a lot more games. There are a lot of more games you can play. For instance, here you can construct sort of a phase plane in which you can compare transfer learning versus random features, or transfer learning versus actually training both V and W, so the first and the second layer, where you on one axis you're changing the overlap between the teachers, so the overlap between the mechanism which is generating the labels for the source and target task, and then on the y-axis you have the data loading, so the number of data, okay? And then you can see both here and here, and in cases in which there's a strong overlap between the source and the target task, so the labels in the source and the target are kind of the same, and you don't have enough data, so it's always better to transfer. And it's better than using random feature, is better also than to actually train the first layer. And if you look at this part, this is a classical example of a negative transfer, in which transfer is actually detrimental. And so this is a case in which you don't have enough data, but also there's no overlap between the labels. So the Y's in the source and target task is so different, then it's better to just regenerate completely random feature, not using the ones that you transferred you to learn in the source task, because they are absolutely specific for the source. Okay, so in this case, you really don't want to transfer. Yes?
Is there a case where the source and the target tasks are the same?
Yeah, so one is the same, yes. So the target, so this is IntelliTask in the sense that the generative model, you have generative model for the inputs and for the outputs. At least you have the same outputs given a certain input, but the inputs are the same. So the rules generating the outputs are the same, but the inputs, they are different. They just come from the same model. The generative model is the same, but the function that generated goes from X to Y is the same. Yeah, okay. Yeah, the same. What do you mean by the same data? So here. Oh, okay, yeah. So yeah. Okay, this is all for like fixed amount of data in source task. And this alpha here is the number. So this is the amount of data in the target task. Okay, so our approach, we wanted to take this farther onto a network with one in the layer and do a theory for both V and W, okay? And our approach, so I'll go kind of fast on this because Rosabla already talked about this in the morning, is a statistical mechanics formulation in the Bayesian framework. So we have a source net and a target net. Both are described by this theta S and theta T. So we have WS and VS for the source, and the same vectors for the target. Okay, so we first train the network on the source task, and then in some way, and being more specific, we sort of transfer WS onto WT. And the framework is the classical Bayesian setting, in which we have a weight prior here, like a generic weight prior. We're going to take a very simple IID Gaussian weight prior. And then a likelihood here, which is weighted by the usual inverse temperature from statistical mechanics. The loss function here, like the likelihood, the log likelihood, is just the MSE loss, okay? And the network output is classical with the classical 1 over square root of n scaling. So this is this will not in general lead to feature learning, but we are taking P of the order of N1. So in this limit, the proportional limit, we're far away from the infinite width limit, so we know that there's gonna be feature learning, okay? So why am I calling this Franz Parisi? So, okay, this is the Franz Parisi, this is a quantity that we want to compute. So the idea is we would like to average over the posterior of the source task. So e to the minus beta ls is the weight on the source task. And then when we extract a certain ws from the source, then we put it into the target task, we would like to also understand the structure of the target task. And the specific coupling is mediated by this gamma parameter. So this is telling you that the target wt has to be close to the source ws, okay? And when gamma goes to infinity, basically you're transferring all of it. And if gamma is like 0.1 or something, then you gotta stay close to the initial configuration. So we average a posterior over another posterior. And so normally you have to basically compute this log partition function if you want this free entropy, then averaging with respect to a sort of a quench disorder, which has structure because it comes from the posterior on the source. And this is just a source specific function, which we can compute in a sort of an easy way. So why am I calling it Franz Parisi? Because this is a long history in statistical mechanics. It started with the work of Silvio Franz and Giorgio Parisi. And they want to understand metastable states in spin glasses. So there's a way of not using, say, dynamical mean field theory to understand metastable states, but do it in an equilibrium way by counting the how much like the number of configuration gets reduced when you want to stay close to a certain configuration at a given temperature, or you can just be freely sprawling in the landscape, okay? And this is what the Franz Parisi potential is actually measuring. So if you start from this maybe from this idealization in spin glass sense, you cannot really understand how this can be applicable to our cases, but there are a lot of subsequent works which have been used to study the landscape of actually MPR problems like learning with binary synapses. And this is a very nice paper by Haiping Wang in which he actually uses as Hamiltonian the energy for learning on a perceptron with binary weights, which is very hard to train. Like there are ways of training using top approaches and belief propagation and stuff. And you can use this kind of formalism to understand the local structure of solution in this very big 2 and 2 to the n dimensional space. And we built on this and we sort of generalized this approach and we understood that the usual Franz Parisi approach wasn't enough to understand what was going on, and we introduced the concept of local entropy and studied the flatness. So this all comes from, like, just to tell you, there's a history and there's a reason why I'm calling it Franz Parisi. So the basic difference between the usual Franz Parisi computation and this one is that we don't average over the disorder as everyone in the usual statistical physics does, right? We don't average over the data set, but we make a calculation for a specific data set. So we have X and Y, which are specific matrices for the input and the output. So I want to give you just a sketch of how you can compute this kind of stuff, okay? So we want to average the log of this quantity, the target partition function, on the posterior over the source, okay? So this guy is kind of easy in some sense. I mean, it's easy in retrospect in the sense that we have papers that already did it. So this is a source-only action. It doesn't care about whatever is going on here. And it gives you this quantity here, which Rosalba, I guess, already showed. And the main point here is that you have a renormalization of the NNGP kernel. So this is the NNGP kernel for the network, meaning like you take the prior, nothing changes in the weights and for the first layer, but then you need to self-consistently renormalize it. So you have a single equation for this guy, QS, it gives you the saddle point and you can compute ZOS. Now the problem is we have to average this guy over the log. Whenever a statistical physicist sees a log, it thinks in terms of using the replica method. So you can turn a log into a limit when n goes to 0 of a derivative of a moment, of the nth moment of the partition function, okay? And so that means we have to replicate the target. There's an asymmetry between the source and the target. The target is fixed and the source is fixed and the target is replicated. And that means that the source is quenched and the target is varying, okay? So we're averaging over the target configuration by keeping the source weights. So just to give you a hint, okay, I lied, it's a 2-slide derivation. So we can first integrate in this replicated space over the first layer weights, both of the source and the target. What we get is, at least at the prior level, the pre-activation are Gaussian, okay? Because we have a Gaussian prior on the weights. So the pre-activation are Gaussian, at least in this replicated space. And they are coupled because we are coupling with gamma the target and the source. Now, for the second layer is a little bit more complicated. We cannot really do that. But if you look at the characteristic function of the outputs, so I'm calling S here, just the outputs, the replicated outputs. The characteristic function of this S is complicated. And if you look at the, say, the Fourier modes of this, you have this quantity Q. Now, what you can do is a Gaussian approximation. In some cases, you can sort of wave your hand and say, oh, at some point, someone will actually prove a multivariate version of a Brownian measure theory, but it hasn't been proved yet, so we just hope that someone will do it. And we just call it this Gaussian approximation. Within this Gaussian approximation, you get in the end, that what you're actually interested in is a form of these conjugate quantities, which are sandwiched. So the NNGP kernel is sandwiched between these conjugate quantities, okay? And then you get this replicated matrix, which is living in this fake n-dimensional space, which in the end will go to 0, okay? But at least in this replicated space, what we get is a specific replicated kernel randomization. So it's something similar to what Rosalba was showing in the case of multiple outputs, in which case you had like all the outputs were renormalized by a number, okay? But in this case, this lives in this replicated space. And when you take n to 0, you don't have to keep track of all these numbers, but just 8 of them. So you take the limit n goes to 0, and you have a saddle point structure for this action. And I'm not going to write this action because it's just awful, but the idea is that this action here only depends on 8 numbers. Now, instead of solving for 1, like in Rosalba was showing, for instance, at least in a fully connected case, here you need to solve for 8 different numbers, 8 different order parameters. But these order parameters are naturally coupled to these source target kernels. So now basically using the replica method gives you something more, which gives you a KST, which is a renormalized source target kernel. And it's telling you that whenever you have the source target covariance, you can compute an effective kernel, which is gonna tell you how much the test loss in the target will depend on the similarity between the structure of the target and the source, and how this relates to the y's in the targets and the source. Because this guy, KST, is going to be sandwiched between ys and yt. So the similarity between the input covariances and the input-output covariances are all written inside this KST, okay, which mediates the transfer. All right, so some results. We constructed some transfer tasks. So the way you can do it, you can take like MNIST and construct a C or correlated MNIST, just swapping one category. So it's a binary classification task in which you have this class versus this task, but then we swapped one of the two, like the E for the F here and J for the I, and the same for cipher. Okay, so we swapped this guy with this guy and this guy with this guy. So some of the features are there, but the data set is not the same. And then what you can do is that you first run a Langevin to sample from the posterior of the source, and you take W's of the source and couple them with a new Langevin for the target, and then you extract all the quantities of interest in the target, okay, from the posterior of the target. That means you have to average over the posterior of the W and run multiple Langevin to sort of get these quantities. And so what these curves are telling you is that in these two cases, transfer learning is actually working in the sense that so gamma equals to 0 is just learning from scratch, and then if you crank up gamma, you get that the test loss is going down, okay? So up to the point in which like this gamma 20 basically means that you're not learning anything for WT. You're just transferring completely WS onto WT. This case is different because you have like a non-monotonous behavior. That means you are supposed to learn a little bit, but don't go too far away from WS, okay? So this is like going very far away from WS. This is, WT is equal to WS. This is telling you don't go too far away, and least in this Bayesian sense, like not in the dynamical sense, but at least in this Bayesian sense. Okay, so a little more information on what I was talking about earlier. So the correlated and the manifold model, just to be more precise. So the idea is that you generate your input, here the X for the source and X for the target, by a lower dimensional C representation times some features, and these features are just random, okay? But you can control the overlap between these features in the target and source. And this is the teacher. So this F function is controlling the output for the source and the target task. So you can play a whole bunch of games like how theta S is close to theta T, how Fs is close to F of T. What we did was control the level of source target similarity. So you can take some F of S, okay, some features which you have in the source task, And then you replace these features with a certain probability and calling this probability rho. So with a certain probability, 1 minus rho is just f of t are equal to f of s. So you just keep the same feature. With the probability rho, you just regenerate completely new IID features, okay? So they are uncorrelated. And then you can plot the test as a function of rho and as a function of gamma. And I mean, not surprisingly, what you find is that like here, rho is 0.1, so you have 90% of common feature between the source and the target task, and the transfer learning is actually always good in the sense that you crank up gamma and you get more generalization. In this case, this is a negative transfer effect because at least from the theory perspective, here you have rho is equal to 0.5, so 50% of the feature are completely new for the target data. And so the test error here is worse than here. So it's better to just retrain completeness from scratch. And I guess yes. Increases in, so. Oh, okay, so this is not average over the train set. So this is for a specific train set. So it could happen in principle. So this is not over an ensemble. Okay. But I have in general I mean, I don't have intuition as to how far you want to be. So this is telling you that you don't want to be too far, right? So the theory is telling you that you want to be close to the teacher, but not too far from the teacher. This is the minimum. It doesn't have to go, yeah. So in terms of gamma equal to infinity, so if you just transfer completely, then it's negative. The theory is predicting negative transfer for full transfer. For partial transfer, I'll discuss this in the conclusion. But for partial transfer, yes, it's telling you have to fine tune. So the optimal fine tune is represented here. So I think, okay, I don't have much time for the last slide, maybe, or do I have? Okay, okay, this is kind of a trivial thing, so I go just to the conclusion. So we introduce a new framework to understand transfer learning in Bayesian neural network, at least without averaging over the input ensemble. And when we do the calculation, what we get is that we have the source target kernel renormalization that couples the source and the target, and we can sort of construct transfer learning curves for specific data. And this is, I didn't tell you about this, but it's very easy. Like we can, if you think of the difference between infinite width and proportional limit in terms of transfer, there's nothing to transfer in the infinite limit, in the infinite width limit, because you don't learn any feature, okay? And you can see it directly from the transfer learning. So the curve is completely flat because there's nothing to learn from an infinite width source. And I think the most interesting part is like the future direction. As I said, we don't have really a Broglie measure theorem to justify rigorously this Gaussian approximation, but we can do it anyway since we're physicists. We can apply on top of it a mean field approximation and write a recurrence relation to write replicated renormalization recursively for deep networks. And in principle, we can do this whole thing for a deep network and try to get a theory for the results that I was showing at the beginning. You can, in principle, do the same for convolutional networks. It's gonna be a little harder if you want to do like a tensor layer, but I mean, at least the replica formulation is quite clear. We don't, and this is connected to your question, I guess, the gamma coupling for me is a proxy of what's actually happened when practitioner initialize WT on WS and then have a small learning rate, so it doesn't go too far, right? But it's not exactly the same because we are in the Bayesian case and we are looking at equilibrium. So normally you are always working non-equilibrium gradient descent. We are waiting for the non-equilibrium. You have this coupling. So it remains to be seen whether this is a good proxy or not. And we expect that all these theory will break up in the limit in which you have that p scales like n1 square, And this scalar renormalization for the kernel breaks down, and you have that the kernel actually changes in a way more complicated way. Okay, with that, I'm done.
So given that we are already over time, we're gonna stop here. We're gonna reconvene in half an hour. Let's thank Alessandro one more time.
Thank you. Since we want to stay on time, let's start. It's my pleasure to introduce our next speaker, Dr. Virginia Smith from Carnegie Mellon University. She has won numerous awards, including Sloan, NSF Career, and works on distributed optimization, machine learning. And we're very excited to have you. So thank you for joining us.
Awesome. Thank you so much for the invitation. Thank you all for being here, especially I know we're getting towards the end of the day, so I appreciate you all sticking around. So today I'm going to be talking about machine learning safety. So over the last couple years, I have been going on a journey that many of us have been going on as well, to the land of LLMs and foundation models. Even within this land, the mystical area of machine learning safety. So today I want to tell you a little bit about this journey and what I've gathered from this journey. And in particular, what you'll see is that this is a bit of an unusual talk, I think, for the DeepMath conference. So there's only going to be a few equations. But I want to talk about this area because I think that this is an area that desperately needs more rigor and needs more of the work that's happening in the DeepMath community. So I think that this is a really promising area for future kind of more principled research. All right, so here's sort of an alternative title of the talk today. I'm going to be talking about machine learning safety vibes, kind of what I've been seeing in the machine learning and LLM foundation model safety community, and some of the sort of troubling trends that I've been seeing in research there over the last couple of years. And in particular, to kind of summarize my thoughts, I want to explain a big branch of research in this area around post hoc machine learning safety. So trying to view these models as sort of a black box and improve safety after the fact. I want to explain some reasons why these post hoc machine learning safety approaches fail. I think this is an area where we could really use more rigor, as you'll see in the talk today. But what I'd like to advocate for even more strongly is that we really rethink this idea of safety and how we're approaching safety in the context of these foundation models. And in particular, I want to share some thoughts on sort of a new way forward here and how we might ensure safety by design. All right, so as a starting point, as you know, there's been sort of this shift in the last few years in machine learning, where we've gone from sort of this nice classical machine learning workflow where you start with a data set that you curate, you do some training, and you learn a model from this data. In the foundation model era, this workflow looks a little bit different. You might take tons of data, maybe just data scraped indiscriminately from the web. From this data, you learn this massive pre-trained model. And then we try to fix this up a little bit. So maybe we do some alignment. We have some user feedback data. We try to use this to align our models. And then maybe we want to apply this to some downstream tasks. So maybe we prompt the model, or we apply some task-specific fine-tuning data. I think we can all agree that it's been pretty impressive to see how effective this workflow has been over the last several years at providing some really interesting and exciting machine learning applications. But this more complicated workflow doesn't come for free. All right, so what can go wrong by using these downstream fine-tuned foundation models? Okay, so you see interesting things happening as you start to use these models. So they might output some harmful or hazardous behavior. They might tell you how to make, these LLMs can tell you how to make bioweapons or how to hotwire cars. They might contain copyrighted data. So this is a very popular example. This is from the Getty Images Stable Diffusion example, where on the left, you have the original image, which was watermarked image from Getty Images. On the right, you have some output from Stable Diffusion. It might be hard to see from where you are, but this is a very similar image and in fact includes the watermark, the Getty Images watermark. So I think at this point, it's very clear these models are being trained on massive amounts of copyrighted data, and you can output this copyrighted data, right? They're very good at memorizing. In terms of memorizing, you can also do weird things like this. So this is this popular poem attack, if you've seen this before. So you can basically ask an LLM to repeat some word forever, and it does this, and then eventually it just starts spitting out random stuff. including things like people's email addresses and phone numbers. Okay, now if you go and scrape the web and search the web, you can find this information online. But what is potentially problematic is just how good these models are at memorizing random corners of the web, right? So this might make you a little bit concerned as we're starting to train these models over sensitive data, right? As we need access to more and more data, and we're going to start leveraging sensitive client data. All right, so you're seeing this, you're seeing these issues start to arise. There are a number of lawsuits that exist currently about this copyrighted data and how it's being used to develop these models. There's concern about some of the harmful knowledge that these models might have and how they might use that in very convincing ways in chats with different individuals. And you can get highly sensitive information out of these models, right? So they're possibly very good at memorizing, and this can become problematic as we might be reaching a limit to the amount of quote unquote public data that we have on the web. I think it's very natural to imagine that these model developers are going to start taking data from the people that are using the models. Some of this might be sensitive data and is likely going to be memorized very easily. Okay, so I think that we have reason to be concerned about some of these privacy issues. All right, the current landscape in machine learning safety, I would say, is one where there's a lot of excitement, I think, about safety. There's a lot of very positive vibes here in the community. So in terms of the developers, if you go to the front page of OpenAI or Anthropic, you'll see things like this, right? So this is very important in terms of their messaging. They clearly are messaging to us that they care about safety at every step. Anthropic, puts AI research, puts safety at the frontier in terms of their research and products. Okay, in terms of regulators, all right, you also have, organizations like Thorn, All Tech is Human. You have a lot of groups that are trying to get people to commit to improved safety. So they're doing things like having these organizations, sign these safety commitments. It's not clear exactly what this will mean, but clearly there's a lot of interest and push towards safety. And then you have things like, this is from Biden's, executive order on AI. You have scenarios where these regulators maybe are just saying we're going to do something in safety. Like, I don't know, these models need to be watermarked. And as you'll see today, later in the talk, there's a real question about whether or not we can actually deliver on that technology at the moment, okay? But there's a lot of interest in these safety aspects. And then in the research community, you're seeing a lot of work in safety as well, right? So I am going to be one of the program chairs for ICML 2025. So we just released the call for papers a couple days ago, and I was looking in developing that call for papers, looking back at ICML 2024 to see what were the main topic areas that people were submitting papers in. Okay, LLMs, obviously, but number 2 is trustworthy machine learning. All right, so researchers really care a lot about this topic. There's a lot of research going on in this space. And what approaches are people taking in the research community? So people are coming at this from a lot of different perspectives. But one of the most popular approaches is the same approach that's been very popular for a long time in machine learning. So to borrow from John's talk, this is the David Donahoe, perspective on the secret sauce to machine learning, right? People are developing benchmarks around machine learning safety, and people are trying to climb the leaderboards for these benchmarks, okay? And what I'd like to point out today is I just don't think we're at the point where we're going to make a lot of progress yet by climbing the leaderboards on these benchmarks, because we don't have a great understanding of what the constraints are for these systems, how to even properly define safety in many cases, and how we want to trade off between different considerations in safe machine learning. So I'd like to point out some trends here that I'm seeing around evaluation, and I think that these are areas where folks like you could make a lot of improvements in terms of making this a little bit more rigorous. All right, so the reality is that despite these very strong vibes, the current landscape is a bit more nuanced, right? So the approaches are quite heuristic. The implementations are opaque. We don't have a great sense of what these organizations are doing for safety. it's difficult to even evaluate whether or not the systems are safe. It's unclear how we would expect these things to work. So I'll talk about this in the context of things like unlearning and watermarking. I think there's some real fundamental limitations in terms of how effective these could even be in best case scenarios. The result of this is that these safety measures are easily evaded in existing systems. And I think an underlying thread here is that there's really mismatched incentives between what developers might want to do or regulators or researchers. Okay. So, all right, how are people thinking about safety currently? One of the predominant approaches is really to take this entire workflow and let's view this as sort of a black box. And then let's try to think about applying safety in a post hoc manner. So what might this look like? Some popular approaches for safety currently are things like machine unlearning. So if you've heard of this approach before, the idea is that rather than retraining the model from scratch, you want to be able to quickly update the model so it doesn't display some behavior or it removes some reliance on problematic data, like copyrighted data, for example. Okay, if that doesn't work, we might add some guardrails around the system. So we might look at the output, for example, of the models, and we might say, okay, I'm not actually going to give the user that output if that's problematic output. Okay. And then finally, watermarking. This has been, I think, talked about as sort of this silver bullet for how we might audit the usage of these models. But as you'll see today, there's major issues with applying these watermarking schemes, which again are kind of viewing these models as black boxes and trying to perturb the output distributions in order to encode these invisible watermarks. You'll see that it's very, very easy to remove them, to leverage them for things like spoofing attacks. So to produce text that looks watermarked, but actually didn't come from the model. And I think that there's major discrepancies here between what we can actually provide in terms of technological solutions and what people want from something like watermarking in terms of auditing these models. Okay, so this is going to be the focus of the talk today. I'm going to talk about a series of recent works from my group, looking at some failure modes and some challenges with these post hoc approaches to machine learning safety. And then I would like to end on a more positive note. I'm going to talk about some alternatives and examples for how we have been thinking about encoding machine learning safety by design. And I think that these are areas where it would be very useful to have, as you'll see, more rigor in terms of understanding these post hoc machine learning safety approaches, but also I think it would be very interesting to try to lay some foundations for these machine learning safety by design approaches as well. Okay, please stop me at any point, by the way, if there are questions, if you have feedback. I would love to make this more interactive. All right, so let's talk about unlearning. If you are not familiar with unlearning, the goal is, I would say, first of all, quite vague. People use this word machine unlearning to refer to many things. But at a high level, the goal is something like you want to update the model so that it behaves as if it was never trained on a certain subset of data. Okay, so this can take many interpretations, but at a high level, you want to do something like take the model, do a little bit of updating, and then have it produce this unlearned model result such that it, maybe was never trained on some copyrighted data. It behaves as if it was never trained on copyrighted data or sensitive information or harmful knowledge, right? Okay, how would you want to do this ideally? You'd want to just train your model from scratch. Get rid of that data, train it from scratch. Are you going to do this with GPT-4? No, because it's very expensive and it takes a very long time to train that model. Okay, so you want to just provide this patch or band-aid to the model. All right, how might you do this? A really popular approach is just do some fine-tuning of the model, right? So you might do things like, okay, not gradient descent, but gradient ascent on the information you want to forget. Okay, you might do things like take the forget data, and if there's some natural label for that data, maybe you turn that label into something that's uninformed. So in the classification example, you give that forget data just random labels and then run gradient descent on that uninformed data. And while you're running things like gradient descent on the forget data or gradient descent on this uninformed data, you might also care about retaining good information. So you want to unlearn the bad information, but you want to make sure that the model doesn't become terrible after this, right? And it still has some general knowledge. So you also care about this retain loss. So keeping information about, say, general knowledge of the model. All right, so what does the workflow look like for machine learning? Typically, you start with a model which maybe has been fine-tuned on some task-specific data. And then you feed through maybe this fine-tuning procedure to the model some forget data and some retain data, right? Through these forget losses and retain losses. We do some fine-tuning on the model and we produce our unlearned model. And then how do we evaluate whether or not unlearning has happened? Typically for things like LLMs, what you have is some set of queries, your forget queries and your retain queries. So I want to query the model several times to make sure it's forgotten the thing I want it to forget. And then I'm going to ask it about some general knowledge in the retain set to make sure it's still, working for general problems. All right, so here's an example of what this might look like for the TOFU data set. This is a very popular data set for machine unlearning. So the model here, you're looking at something like Llama 2, and you have some data about 200 fictitious authors. So you fine tune the model on this data, which was generated specifically for this benchmark. And then for unlearning, what you do is you take some of these authors, imagine these are people that maybe are concerned about their data, and they say, I want you to unlearn information about me, right? So you unlearn data about a subset of the people, right, these authors, but we want to ensure that we still retain information about the other authors that are okay with having their data be part of this process. Okay, so you can split this into forget data and retain data, and then you can ask kind of question-answer pairs about the forget authors and question-answer pairs about the retain authors, and also kind of maybe questions about more general knowledge to make sure the model is still working appropriately for the data that we're okay with the model seeing. Right? You may already be seeing problems with this evaluation procedure, but we're going to get into this in more detail. All right, so what can go wrong here? A big issue with these existing approaches, which rely on fine-tuning, is that the resulting unlearned models are very brittle. So what do I mean by that? I mean, you can take Llama and you can do some unlearning. So you've unlearned about these fictitious authors, for example, or maybe you've unlearned information about bioweapons, right? So we don't want these models to produce any results that tell us how to build bioweapons. And so I can run my unlearning procedure, and across all of my queries, it looks like the model is doing a great job at unlearning. Right, so I ask it some problematic query, how should I make influenza A more virulent? And it doesn't return any output. Right, so this is what we want. But then you can see in terms of this being very brittle, you can take some totally benign data, maybe data from Wikipedia, for example, and you can feed it back to this model. And suddenly, the model has recovered all of the stuff that it ostensibly had forgotten, right? So we're able to jog the memory of these models very effectively just using benign data, right? Without using any hazardous information. Okay, so we observed this across a bunch of different pipelines. And in this recent work, we were interested in understanding, why is this happening? What's going on under the hood here, right? And how effective might this be in practice? And what's interesting is you can see that this can happen for even more, I think, extreme examples. So another really popular data set for machine learning is, yeah.
Affecting Wikipedia articles on virulence of viruses, or was it just like there are some wackadoodle Wikipedia articles and like you put in one on bikes and one on?
It's a good question. So this is exactly what we wanted to understand in this work. And you can actually show that any sort of Wikipedia data gives you a small boost, but this is more effective if the Wikipedia, the general knowledge is somewhat correlated with the harmful information. So you might have a Wikipedia entry on COVID-19, which is all general knowledge. It doesn't tell you how to make sort of bioweapons from that. But obviously that more correlated data is more effective at these relearning attacks. So I'll get to that in just a moment. So you can see that there is varying degrees of effectiveness to this. And this is actually something that in the last few months, there's been a bunch of follow-up work from other groups as well that have shown, I think, even weirder things like quantizing the model. You can see that it jogs the memory to some degree. So there's a lot of sort of like weird things you can do, weight perturbation, that get back some information. But for this to be very effective, it helps if the data is correlated. Yeah. I think that's totally valid. So a few things. One is that it can be much easier to get answers from this model than maybe just searching the web. The web actually has a fair bit of guardrails in place. I think we're maybe better at putting guardrails in place for the web than for these models. These models are also being used in a way where I think average users of the system feel like they're actually talking to a human. And so you can have this weird interactive process where there's a lot of influence in not only maybe being able to build these bioweapons, but encouraging you to do so. And so certainly I agree that this information exists on the web. But think about if you train these models then on other sensitive data as well, right? Yeah, so this tofu data set, which I'll talk about, is a good example of that, where that was completely falsified data that didn't exist on the web that they're using specifically to test this issue of unlearning. So there's varying degrees. This is known as the weapons of mass destruction proxy data set. This one is a little bit more hazy in terms of the definition of unlearning. I think this is something much more related to kind of alignment. But you'll see this is also kind of an issue that we point out with the unlearning community. It's trying possibly to do many things at once. I think this is more related to kind of an alignment example. But you'll see other examples, which I'll talk about in just a moment, that are more related to things like private information. Yeah. This is not a prompt, it's fine tuning, but follow-up work has also shown that you can do this with in-context learning as well, which I think makes some sense. So you could give this information in the prompt as well, and it's not as effective as fine tuning, but is still somewhat effective. Yeah, so a lot of these model developers do allow you to have access to fine-tuning APIs and to do some fine-tuning. But again, people have shown very recently that you can also do this with in-context learning, which I think makes sense. They want these models to be good at doing some in-context learning, so you could feed these examples instead of through fine-tuning through some prompt as well. Yeah, was there a follow-up question? Okay, cool. All right. I want to revisit, by the way, I'll revisit it towards the end of this talk, this question about, I don't get it, this data lives on the web, why do we care about this? So I think this hopefully should become very clear when I talk about this example. I've been collaborating recently with this group called Thorn, which looks at the prevalence of child sexual abuse material in these models. And I think you'll see there, I think the big question to ask with all of this is, what is the marginal risk? What is the new risk that is introduced that didn't exist just from having this data be on the web? And I'll cover that at the end. So you can show some concrete examples about how there are new risks that are introduced by having this data be part of these models, as opposed to just living on the web. But this is a totally valid question. Okay, so, all right, there's this example of bioweapons. I think an even maybe more compelling example is that for something like copyrighted data, you can show that you can take a model that has been fine-tuned on the complete works of Harry Potter. So it's memorized this data basically completely. These models are very, very good at memorization. So if you provide it some prompt randomly selected from one of the books, it will output that exactly as it was written in the book. You can then do unlearning. You can run gradient ascent on this same data to unlearn this information. And it appears across all of your evaluation as if this has done a very good job at unlearning. And then you can relearn it with just some general knowledge. So wiki data about Harry Potter. Maybe that you know that Hermione Granger is a muggle, right? So a bunch of just basic facts about Harry Potter, and you can see that it's now able to completely verbatim spit back the memorized data again. Okay, so this is a problem if you're being sued, if you're a model developer being sued and you're hoping that unlearning is just going to allow you to quickly update the model, and now you're no longer able to output that verbatim memorized text, right? Yeah. Yes, that's right. Yes, which is how we're evaluating the fact that it's been unlearned. So no longer is it able to output memorized text. This depends on how you're doing on learning. So sometimes, and the model that you're using. So sometimes more expressive models will hallucinate in a more effective way. Other models might hallucinate in a not that good way, like in this example. And I think this is a useful point because it also asks the question of what do we actually want the model to do in this scenario? Another perfectly valid thing for this model to do might be to say, I can't respond to this prompt, right? So this is another reason why evaluating unlearning is somewhat challenging in practice. Okay, so this is those were some, cherry-picked sort of examples, but you can see across many different popular methods for unlearning on the x-axis here that what we're able to do is take the original model, which is able to effectively complete these tasks, tell us about how to make bioweapons. You do unlearning, it looks like you're much, much worse at these tasks. Then you feed it some just benign information, and now we're able to do, in some cases, even better than we were previously on this task of teaching people how to make bioweapons or memorizing text from Harry Potter. Okay, and crucially, the thing we want to point out in this work is that we're not just relearning the same data. I think it's obvious that if you were fed the unlearning data, you could have the model fine-tuned on that data and relearn things. We're leveraging sort of benign, possibly loosely related data. So we can actually evaluate this in the sense that if we take the original model and fine-tune it just on this relearn data, it's not good at these tasks. It's not good at outputting memorized information or telling you how to make bioweapons. But if you do this procedure of unlearning and then using this relearn data, you're able to sort of jog the memory of these models that appear to be unlearned. Okay, so these are some examples that we talked about. You can use kind of Wikipedia articles, general knowledge for this bioweapons example. You can use Wikidata about Harry Potter. This is a very effective way to relearn even verbatim memorized text. And then there was a question about, this TOFU data set. So in this data set, you're unlearning this fictitious data, which does not appear on the web. And you can see that if you unlearn on a specific set of authors or a specific set of books, you can relearn on a totally disparate set of books, but somehow you're able to get back information about the books that you unlearned. All right, I think the obvious question is what is going on under the hood? Why is this happening? And there's two, I think, really clear things that are happening here. One is that there's insufficient unlearning happening, right? So it's easy for us to convince ourselves that the model has unlearned when it actually has not unlearned. And you can see this in terms of, so this is the TOFU data set on in the color here. We're showing that our attack is more successful if it's yellow, less successful if it's green. On the x-axis, you have the amount of unlearning you do, and on the y-axis, the amount of relearning that you do. So you can see this maybe obvious trend, which is that if you do more unlearning, and by the way, all of these unlearning steps through our evaluation procedure appear as if the model has unlearned, but nonetheless, you can continue to do unlearning steps even to the degree that now you have very poor retained performance. And you can see eventually maybe you hit a wall where relearning becomes less effective, and the effectiveness of relearning depends on how much unlearning you do. Okay, this doesn't always happen in this nicely controlled way. You can see for some examples, like this Who's Harry Potter example, we unlearned a terrific amount, so much so that basically the model is doing quite poorly even on the retained data, and still we're able to use this relearning attack to get back some of this verbatim memorized text. Okay, so one clear thing that's happening here, I think, is that our evaluation is not effective enough. I'm going to get to this in just a minute to talk about how we can improve evaluation. But this seems like a clear reason why these models are somewhat susceptible to relearning. The other thing that we found in this work I think this is also fairly intuitive, is that if you have data that you're using for relearning that is somewhat correlated with the information you're trying to unlearn, these relearning attacks are going to be more successful, right? So here's an example. I might be, I don't know, John might want his information to no longer be used for ChatGPT, and so he might, submit one of these unlearning requests. And maybe I use unlearning and I forget all the information I have about John. But then there's some information about John that lives on the web, right? We might know his email address. This is public information. So I, do some fine tuning with John's, email address. And then because his email address in data that exists on the web has maybe been correlated with things like his home address, maybe we can figure out what his home address is from using this relearning attack, right? So this benign knowledge is often correlated with potentially harmful knowledge, right? Think about these other examples that we talked about. Wikidata for Harry Potter, maybe Wikipedia articles about COVID-19 share a lot of, terminology, keywords with potentially harmful information about how to make bioweapons. Yeah. Yeah, so this is to point out the fact that you can do too much relearning. Basically, what's happening here is that the model starts to become ineffective because you're overfitting to that relearning data. Yeah, so there's sort of a sweet spot here in terms of how much relearning to do. Yeah. You're jumping ahead, and this is a great point, and this is, I think, it should be a clear issue, but is an issue that exists with all of these existing benchmarks that I think is very problematic for the field. Exactly this. This is something that I'll talk about in just a minute. Okay, but high-level punchline here from the correlated data. We look at this in some sort of smaller synthetic examples as well. We have this really simple example where we're looking at basically pairs of words, and we're trying to unlearn on one word and then relearn on the other words, and you can see if those words appear more frequently together, your likelihood of relearning is more effective, right? So there's something about the correlation is making relearning attacks more effective. All right, so what are some considerations for unlearning in light of this? The high-level takeaway here is that seemingly benign data can jog the memory of these unlearned models. From a safety perspective, you should exercise caution when using these approximate unlearning methods in real-world deployments. As I mentioned, more recently, there's been several other works that have shown other types of attacks that are effectively doing similar things. So you can, use this data for in-context relearning. You can just perturb the weights. You can do more advanced adversarial attacks. I think it's clear why those might be more effective. I saw a recent, work that is just looking at the effect of quantization on relearning. So clearly, these approaches are somewhat heuristic and maybe not very effective at performing unlearning. All right, so what is one solution to this? I think a natural thing that you might think of is we're not evaluating these things properly. Let's just propose some new evaluation metrics to make sure that we avoid this false, sense of security. And indeed, this has been a big focus of recent work, is proposing many, many different sort of evaluation metrics that we could consider to make sure that we've actually done unlearning. But as I'll point out in just a minute, and related to this question, there's serious issues with how we're even setting up these benchmarks, such that even if we have better metrics, we're not going to be effectively measuring unlearning. Okay, so I'll talk about that in just a moment. All right, so to talk about evaluation, I actually want to talk about this other approach of guardrails as well, to talk about some of the issues that exist with these, the solution of just applying guardrails to your model. All right, so what do guardrails look like? Yeah.
Privacy or something like that, if we're training the model with your data, or we're training the model without your data.
Yes, so yes. This is the definition that people have taken historically in the context of unlearning for smaller models where we have a sense of what the training data is. The difficulty now with LLMs is we don't know exactly what the training data was. So, okay, you could perform membership inference attacks, for example, if you knew what the training data was. Or maybe you would train a model with differential privacy, and then you wouldn't have to deal with things like unlearning. But this is not what's happening with these massive trillion parameter models, unfortunately. And so that's why we're relying on these sort of more heuristic approaches for evaluation. But I think this is totally valid, and I'll get back to this in just a minute in terms of what might be some, more principled metrics that we could use for unlearning. And the short answer is there have been some really nice metrics and definitions proposed that don't yet apply to this scenario of using these massive foundation models. Yeah. So what I'm going to advocate for is that I think that this idea of approximate unlearning may be fundamentally flawed, especially if we have the constraints that we have now of not knowing what was in the original training data or being able to evaluate that as part of this process. And in light of that, what I would like to propose is that we go about this process of unlearning entirely differently. So we think about encoding safety during the training and fine-tuning process instead of doing this sort of approximate unlearning thing. So I'll get back to that in a few slides. Okay, so what about a guardrail? So this might be another approach. We might say, okay, let's forget about unlearning. It's clearly not working that well. What about if we try a different approach? So approach that's common with these LLMs might be that you have some input query that a user gives. You could assign some prefix to it. You could modify that query. You could filter it or ascribe some conditional prefix. Then you send that to the model, and then you could also filter the output. So you can look at the output and say, okay, I don't like that output. I'm not going to respond to anything if it's a problematic output that you see. For fun, I don't know if I would call this fun. If anyone has done prompt engineering, it's actually quite painful. But we tried to do this for this problem of unlearning. And we looked at the following simple prompt. So we took one of these models and we said, okay, let's use this prompt. You're an AI assistant who is supposed to unlearn about the book series Harry Potter and provide answers without its knowledge as if you never knew about it. Don't tell anyone that you unlearned anything. Turns out that this is really effective. So if we compare this approach to state-of-the-art fine-tuning baselines, what you can see is that we're able to do significantly better. It depends on the model that we're using. Something like GPT-4 is much better at taking this prompt and just rolling with this. The downside, though, is what you don't see under the hood with these results is that this was a terrible process. So this prompt did not work. Answered the following questions, assuming no knowledge of the book series Harry Potter. This prompt, which provided a bunch more information, also did not work. Annoyingly, this prompt, which is almost identical, except that we use the word forget instead of unlearn, also is not effective. So prompt engineering, building these guardrails, if anyone has done it before, you know that this is really a frustrating process. I don't think this is really a super effective solution for doing this at scale with many possible unlearning applications. Okay, so what else is there? Another common approach instead of prompting is to use something like a filter. So to look at the output and filter it, so don't respond if the output looks problematic or it's revealing sensitive information or harmful information. We looked at this for this TOFU benchmark where we have a pretty good sense of what the unlearn and retain data is. And you can use models like Llama to get really good performance on forget and retain queries. GPT-4 improves this even further. But actually, there's an even better, really stupid baseline to use, which is use a keyword search. We know all the authors that we want to keep. We know all the authors we want to forget. So let's just search over the author names, and let's only output information if those authors are in the retain set. Okay, so this might seem really silly, but in this recent work, I won't go into the details here, but we looked through several recent works and found that basically under the hood, this is exactly what they were doing. They were proposing some very sophisticated method for unlearning, but that unlearning method relied on a classifier that was basically completely overfitting to the particular forget and retain data that they have, which is actually quite easy to perfectly classify because going back to this question from before, often for these benchmarks, these things are quite disparate. Okay, so going back to this, high-level workflow that I showed previously, you maybe can already see this, right? So for this example of tofu, actually what they typically provide is just the forget set and the retain set. And this forget and retain set might be quite distinct from one another. So for this example, the authors, you can almost completely distinguish between these two authors based on just a single keyword, these two sets of authors. Okay. So what are some weaknesses with existing unlearning benchmarks? It's very easy to potentially sort of solve these benchmarks by using some simple means other than actual unlearning. The forget sets themselves are often incredibly vague. So things like forgetting an entire concept, right? And they encourage you to actually look at the test queries to think about what type of method you would like to do. If you are thinking from the machine learning literature, you might know we don't want to be knowing exactly what our test set is and then finding a solution for that test set, right? So it might seem clear why this is problematic. And I think the bigger thing, maybe going back to John's question, is that should we be using these test queries to do evaluation? Like, does this actually correlate with the underlying definition that we care about for unlearning? Should researchers be optimizing these sort of heuristic benchmarks, or should they be trying to show that their method works for some sort of truer formal definition of unlearning? Okay, and this is particularly problematic because, like with all LLM evaluation, these evaluation sets are quite brittle and quite narrow. So this is a problem with all LLM evaluation, but if you do silly things like change the order of multiple choice question answers, change the query type, so from multiple choice questions to keyword detection to verbatim memorization, you translate the text, these are all things that can pretty significantly affect the performance of these approaches. Okay, and the last one that I want to point out here, which is not just specific to LLM evaluation, but is more specific to unlearning, is that often in these benchmarks, there's very large discrepancies between the forget set and the retain set, right? So as one simple sort of way to test this, we did the following experiment. For this weapons of mass destruction data set, we took sort of the state-of-the-art unlearning methods, and we looked at their performance on the retain set. And we saw that many of them did quite well on the retain set. But when we made the following modification, they started to do very, very poorly. So what was this modification? We took a keyword from the forget data, right, like SARS-CoV-2, and we swapped that out as one of the incorrect answers to one of the multiple choice questions. So note that this shouldn't actually change your answer to this question, right? This was not the correct answer originally, so it shouldn't change the result here. But you see weird things happen where now the model gets messed up with this information, right? Maybe it's learned that when it sees this keyword, it should just output, a random answer. And this model does quite poorly, right? So if we look at across a bunch of the sort of test suites that they have there, the original model, not the unlearned model, and we swap out the questions, you can see, okay, first of all of these models are somewhat brittle to this idea of the answers being swapped out. But if you look at the unlearned model, the performance drops substantially, so much so that you're hardly doing better than just random guessing for these examples. Okay, so this should, I think, it points to the fact that these benchmarks are giving a really, really optimistic view of how these methods are performing in practice. If you can take this really simple modification, and now the performance on the retained data is basically no better than random guessing. All right, this is particularly problematic because just like with all of machine learning, maybe we can go back to the ImageNet example. There's really been an outsized impact from just a few benchmarks. So if you look at, in the last year or so, papers in the space of unlearning, we did this big sort of meta-analysis of the field. You can see that most papers are just using a few benchmarks for evaluation. And then, I don't know, perhaps, weirder, if you look at those papers and you scale them by the number of times those papers themselves have been cited, the papers that are sort of more popular in machine unlearning are also ones that are just using these like very small subset of benchmarks. Okay. All right, so what does this mean in terms of unlearning evaluation? What can we do here? What are some recommendations? At a bare minimum, we should introduce forget and retain dependencies and use held out test query sets. It's also, I think, very valuable to specify threat models along with the algorithms that we're proposing. Clearly here, I think there's a lot of interesting questions about the scope of unlearning. Do we expect this to possibly be effective? What types of data sets or problems could this actually be useful for? Are there certain data points that could be unlearned more easily than other data points? And in terms of these evaluation benchmarks, I think that things like this sort of vibes, I call this vibes-based unlearning, but unlearning like an entire concept, like how to create bioweapons, is going to be more difficult than unlearning information maybe about a particular user where we have all the data for that, that person. Okay, but what do I really think we should do? I think in an ideal world, as researchers, we don't have to be focusing on these possibly bad solutions. We can envision a different way for these systems and models to work, right? Maybe we develop models that have privacy by construction. Maybe we try to develop techniques for exact unlearning. So I'm going to talk about how this might be possible in a few slides. And maybe we try to provide some formable or achievable definitions for approximate unlearning instead of relying on these empirical benchmarks. All right, I don't have too much time to talk about watermarking, so I'm going to talk about this pretty quickly. But I do want to talk about this because this is one, I think in particular, where there's a real discrepancy between the way people in maybe the policy land are talking about watermarking as being sort of the all-encompassing solution for auditing these models and what we can actually deliver in practice. All right, so first of all, how do you watermark an LLM? I think this is a kind of fun technique to think about. So these LLMs are autoregressive models. So we predict the next token based on the previous token. So for example, if we have the prompt input, DeepMath is a conference on the, maybe the word mathematical is going to be the next token selected with high probability. And then maybe after that, the word theory is going to be selected with high probability, right? So this is how these autoregressive models are working. So how do we take this notion of autoregressiveness and then apply a watermark? We can do that in the following way. So we can perturb the output distribution slightly, right? And we can do it in a recognizable manner such that once we have that output, we can go back and say with some confidence that the output has been watermarked, okay? So how could this work? You could take all of the tokens in your vocabulary and using some secret key here, right? Some way to get at the randomness, you can randomly partition these tokens into a green list or a red list. And then what we're going to do when we're embedding our watermark is we're going to boost the probability of things in the green list, and we're going to downrate the probability of things in the red list. Okay, so note that this hopefully should still result in quality output. If a particular token is really, really, really likely, then it's still going to be likely after this. So we're still going to get reasonable output. But if you do this with a long enough sequence, you're going to start to see an unusual number of tokens that are coming from the green list. All right, so this is how you can then take the watermarked output and detect that there's a watermark in place. So you can use some statistical testing to estimate the confidence, the likelihood that that output came from watermarked text, given how many green tokens you're seeing. All right, so there's a few things that people care about with these watermarks. They want them to be robust, so someone doesn't cheat on your exam or on their homework and then do some modifications and now the watermark is removed, right? Or maybe a more compelling example, we don't have a bunch of issues with misinformation or disinformation where we can't tell that it's coming from bots, right? We also want this watermark to be invisible. A way to think about this more formally is that we want the expected distribution to be unbiased, right? So this is something that might be nice to encode in terms of the watermark so the text still appears quality. And then we want it to be easy to detect. And this is one where I think there's the biggest difference between what we can actually provide now and what people want. So ideally, you have some output text. You think it might be coming from an LLM. There would be some API you could use to feed that output text into the detection API, and it would tell you whether or not the candidate text was AI generated. And it would tell you specifically what model it was coming from, right? This is model specific. There are major issues with this, right? Because then you can game this to try to, remove the watermark. You can edit it a little bit by little bit. or you could do some spoofing attacks, try to get text that is not watermarked, but it looks watermarked. So I think this is a real reason why you see very few companies that have actually released watermarks with these models. Okay, so this is some recent work where we're looking at some challenges that exist with these properties with watermarks. And in the interest of time, I'm not going to cover these in too much detail, but I think they're actually quite intuitive. So these are really, really simple attacks that apply to existing watermarking schemes. If your watermark is very robust, meaning that you can edit the watermark and it's still going to appear as watermarked text, you could also use this in a nefarious way. I think this is another reason why companies are not that excited to release these watermarks. So I could, for example, take this watermark text from the newest GPT version, and I could modify it so it has a bunch of toxic tokens or it's incorrect. And then I could say, look, this output is still watermarked. This model is doing terrible things, right? So that you can easily launch these spoofing attacks the more robust the model is. Okay. There's a specific attack that you can also apply if you're leveraging the fact that these watermarks are unbiased. So a way that people do this often is by using multiple watermarking keys. This is a common technique in cryptography. It turns out that you can use this to pretty easily remove watermarks. And similarly, I think this is the most straightforward one. If you have access to these APIs, which is the way a lot of people talk about these watermarks, is that we can use this to audit the usage of models and it's somehow available to society. We can all use this as this tool. Well, we can also use that to just remove the watermark or to produce spoofed text. Okay. So I'm not going to talk about this in too much detail, but I think these things are fairly straightforward. So in this work, what we do is try to kind of explore these attacks more rigorously, show how effective they could be on existing models. The answer is that they can be quite effective. They're really pretty simple attacks. If watermarks are more robust, it allows you to do very simple things like spoofing. You can, if you make some small edits and it's going to be watermarked, then you can do that in a sort of nefarious way. And the output z-scores here, the confidence that we have about this coming from a watermarked model will still be very, very high, even if you do this sort of piggyback spoofing attack. As I mentioned, watermarks slightly bias the output distribution as a way to ensure that distribution is unbiased. A common strategy is to use multiple watermarking keys. So you have this unbiasedness property and expectation. If you have this property, you can leverage that to just remove the watermark. So you can query the model many times. It's going to produce output according to these multiple keys. And then you can sample from this output. And then you'll have output that does not carry the watermark. And finally, these APIs, if you make them public, they can easily enable these watermark stealing attacks. So you can work with these models and with these APIs in an adaptive way to take some watermark output, see if it's detected, maybe modify it a little bit, see if it's detected. You can do this iteratively to easily remove watermarks or to produce spoofed output. Okay, so a few guidelines for watermarking. So in this work, we kind of analyze this more rigorously, but the high-level takeaways are that these robust watermarks are vulnerable to spoofing attacks. Approaches that try to reduce the likelihood that watermarks are going to be stolen are in turn vulnerable to watermark removal. And these public detection APIs, we have looked at some approaches to try to make this more difficult. So you can do things analogous to what you're doing with differential privacy. You can maybe inject some noise in this API. Right now, this has not been a terrifically effective solution we found. So this ends up really reducing the performance of the API significantly. But I think to make watermarking actually useful, we need to really try to understand how these detection APIs could possibly be deployed to the public. All right, so the current state of LLM watermarking, this is again one where I think there's a big difference between what we're seeing in practice right now and what we would hope to be able to do. So there's a lot of work developing new, I think, really interesting watermarking schemes. There's really strong interest in this from regulators, but there's incredibly strong deterrence for people, the model developers, actually providing this. So you might imagine if you're a model developer, if you know that spoofing is possible, this might not make you very excited. But you could also say, well, if I'm just going to produce this watermark and people can remove it, why do I care about that? Especially if there's any chance it's going to degrade the results, which is what they really care about the most, I would imagine. Okay, and without public detection APIs, the applications here are pretty narrow and are quite self-serving, right? So watermarking could still be useful if you don't release these APIs, in the sense that an organization could use it to make sure that they aren't taking data from the web that was coming from an AI model and then using it in their training procedure again. So this does have some use, but it's a much more narrow use than what we're talking about watermarking being useful for. All right, in the last few minutes, I want to talk about some different approaches that we could take here. And this is an area that I think would be, very interesting to spend more time in moving forward, as opposed to maybe trying to fix these post hoc approaches. All right, and the key idea maybe is obvious, right? To encode safety by design, we need to reckon with the data that we're using and the way we're accessing that data. So the data and the training procedures. So let's stop viewing this as a black box, okay? And let me give you a few case studies. So let's imagine I have a model and I want to fine tune it over some sensitive data, right? And I know that someone might submit one of these sort of GDPR style data deletion requests. All right, rather than using approximate unlearning, which I think really has some fundamental flaws, what about if we fine tune in a way such that we can exactly unlearn that data when we get one of these unlearning requests? Okay, there's a really simple approach to this. You could do something, and I apologize because I have spent a lot of time doing work in federated learning, so you might call this something else like model soups, model merging. But you could do something like run a one-shot variant of federated averaging. So you could fine tune on each of your clients, your sensitive data, and then just average the results, okay? For deletion, we can do this exactly. All we need to do is go back and compute that model update. We can delete it from the average, right? And then now we no longer rely on that sensitive information. There has been work thinking about this in limited settings, right? There's a lot of work in the model merging literature about trying to merge, 2 or 3 models. But some work we're working on right now in my group is thinking about how to make this most effective at scale. And I think that there's some reason to believe that this could be effective because you're starting with a pre-trained model and you're just doing some fine tuning and averaging the results. But to me, this would be a much more compelling case for allowing an organization to actually use my private information if I knew that information could be exactly deleted if I asked it to. Okay, what about copyrighted data? How do we remove copyrighted data? The current practical solution is not awesome, right? What these organizations do, they're actually quite upfront about the fact that they're using copyrighted data. So they're using copyrighted data, but they're trying to reduce the amount of memorization during training. If they get hit with a lawsuit, maybe what they're going to do is add some guardrails and remove the data for the next training iteration. Can we envision a better world? I hope so, right? So maybe we don't train on this copyrighted data, or even better, maybe we find ways to compensate data creators, right? So what would this look like? We might need to figure out, scalable ways of valuing how much data is useful as part of these processes, and then compensating creators. And I want to throw up a quick plug here because I think that there's been a ton of work in this related area of collaborative learning, thinking about some of these ideas. I'm actually helping to organize, along with John and several others, a program at the Simons Institute next year, all around federated and collaborative learning, trying to think about some of these ideas. So how can we effectively incentivize participation and develop trustworthy schemes when learning from multiple people, maybe multiple sources of copyrighted data? Okay, and I'm almost out of time, but let me just spend 2 slides on this really quickly. This is maybe to go way back to the question of like, why do we care about this? This is all coming from information on the web. And this is a valid question. So the thing you should be asking yourself with these safety issues is, to what extent do these foundation models actually increase risks beyond previous technologies? Okay, and this is a direction that I've been spending some time looking at with my group. We've been partnering with this organization, Thorn. And what this organization has found is that these models lead to amplification, in this case of child sexual abuse material. So unfortunately, there have been data sets like the LION data set that included CSAM material. Many models at this point have been trained on that CSAM material. So this is amplifying the effect of this existing CSAM. It's allowing you to create new CSAM with increased ease. So a large volume of images can now be created from existing ones. This can re-victimize children. It increases the difficulty of identifying victims and offenders. And novel forms of CSAM are possible through these models. So you can take non-CSAM images, and through these expressive generative models, you can use them to create CSAM, which is leading to things like bullying, harassment, and extortion. Okay. Okay, so I think certainly in this case, we might envision that things like approximate unlearning shouldn't feel satisfying for getting rid of CSAM data in one of these models, right? And even more broadly, I think here, when you think about things like child safety, you might realize that in safety critical scenarios, we might want models that are not these general massive expressive models, but are much more narrow. And a particularly challenging technological issue with this example of CSAM is that in really safety critical applications, you actually have real limitations on doing things like running membership inference attacks. So you want to be able to execute these safety measures, but you're not actually legally able to do that without, you can't create new examples of CSAM. You can't even have access to existing CSAM. Is something like approximate unlearning enough for these scenarios? I would say no. I think you need proof of data removal. And so this is, I think, an important open question is to think about how to apply safety measures to applications like CSAM with these constraints in mind. Okay, and just to summarize, the high level, perspective here I have for the community is that for machine learning safety to really move the needle here, I think before we can just let's produce some benchmarks and do some benchmark climbing, we need to really consider the target applications of safety. We need to understand how solutions will be used in larger ecosystems. What is the threat model? What constraints exist? How will we actually evaluate success? How should we even define things like unlearning and measure it? And what I'd like to advocate for is prioritizing approaches and research that thinks, 20 years down the line, let's not just focus on making approximate unlearning better. Let's think about ways that we can actually provide safety by design. And I think this is going to involve understanding these applications and finding principled solutions. So really trying to provide, tangible definitions for this rather than heuristics. Okay, and my final parting thought is that, of course, a question we should ask ourselves is whether this is really the wrong approach for safety, if we care about safety, these foundation models. I think there's been sort of a cacophony of recent work showing that there are real issues, that maybe these models are not all we hoped that they would be for every single type of machine learning application, that these models actually perform much worse than really simple baselines that exist for target applications. When you add things like safety or efficiency on top of this, maybe it becomes really clear that we should think about going back to some of these more classical scenarios as well. And I just wanted to thank my co-authors for help with this work as well. So I was able to work with a tremendous number of wonderful CMU faculty and students. So thanks.
So we're coming out of time, so it's like 1 or 2 questions.
Yeah, that's totally valid. That's a very good point. Yes. Even beyond what exists now, there could be future harms based on actually using these models. And that's where I think we need to really reckon with how much we want to use these models in systems where they can actually take action or do things or are touching safety critical data. Yeah, absolutely.
All right, let's think one more time and
cool.
Get my
I'll be around for a little bit after this.
Okay, awesome. All right, we have
share.
All right, thanks for sticking around. And we have one last talk before we break for the afternoon. So I'd like to present Bokun Wang, who's one of our contributed talks, coming to us from Texas A&M University. So thank you for joining us, and all yours.
Thanks for the introduction, and it's my great honor to be here to present our recent work on self-supervised learning and from the DPM perspective. And we noticed a recent paradigm shift from supervised learning on the expensive labels to the self-supervised learning on the many readily available multimodal data on the website. But we noticed some conceptually similarity between these two learning paradigm. Like in supervised learning, we are predicting the relevant label for a given data. And in self-supervised learning, we are predicting, for example, a relevant image given a text, or we are predicting the relevant text of a given image. And clip model is a prominent self-supervised learning algorithm, and it's based on minimizing this contrast loss. It's defined on the image text pairs by learning the parameterized similarity function. And it can generalize better than the supervised learning models on downstream tasks. But the mathematical foundation of self-supervised learning like CLEAP model is underexplored. So for supervised learning, we can start from the DPM and MLE, and we can get, for example, the cross entropy loss or the least MLE loss. And we can build the theoretical guarantees, for example, the generalization bounds or the statistical consistency. But our work tried to tackle the self-supervised learning problem from similar routes. Like, can we use the DPM framework and can we do MLE to derive the theoretical guarantees? So we first designed a general DPM model on the two spaces. So we want to predict the conditional density of a y from space number 1 given x from space number 2. And this model is based on the parameterized similarity function. And then we can do the maximum likelihood estimation on a collection of data x and yi. And W hat star is the MLE. But in supervised learning, the denominator's partition function is tractable. It's a summation over the finite classes. But in, for example, the self-supervised learning, the partition function is not tractable. For example, it could be integral in high-dimensional space. So, for example, in CLEAP model, X is the image space and Y is the text space. So the issue is that we need to estimate the n partition functions. And there are several possible workarounds like MCMC, NCE, or we can just don't care about the partition function. But as far as I know, this methods are not very practical on the large-scale image text data sets. Like the MCMC is relatively slow, and NCE depends on the choice of the noise distribution. So we start from observing the data we have. So we are given a data set of image text pairs from the joint distribution. For example, given an image, the text can be viewed as a sample from the conditional distribution, which is conditioned on the anchor data. So our question is how to leverage the data y1 to yn from the n different conditional distribution to estimate the partition functions. So our work tackles this problem by revisiting this multiple importance sampling approach from 1995, which was originally proposed for the rendering problem in computer graphics. And their problem can be abstracted like this. And we have n different distributions, and this can be designed, for example, uniform of the Gaussian distributions, and we can get a sample from each of these n distributions. And for each sample yi, we can construct the unbiased importance sampling estimators. So this paper tried to tackle the problem how to optimally combine those samples from n different distributions. So their approach is to introduce a weighting function constrained on the simplex, and they can construct the unbiased multiple importance sampling estimators for the original integration. And they also show that if the weighting function has this specific form, we can get near optimal variance. Then we apply this multiple importance sampling approach for our DPM problem. And our scenario is similar. We want to combine the samples from n different, here is the conditional distributions to estimate the partition functions here. And we can construct the multiple importance sampling estimator here. But we have a new issue compared to their rendering problem. So the popularity, we call it popularity, which is a summation over the conditional densities of different data points. But this QJ are available for rendering problem because you can design those distributions, and you can do the numerical experiment to collect those data points, and you know the conditional, you know the density functions. But here it is not available because we have no control over the data generation process. We are given a fixed data set. So we need some approach to approximate these popularities. So we can construct the empirical rates for the DPM. Here we define a Q tilde, which is then, here is the general approximation of the real Q. And the simplest method we can just use a uniform approximation of the real Q. And if we do this, we are recovering the contrast loss. But how good is this approximation? So it's quite straightforward. If we do the generalization analysis, we bound the difference between the true risk and empirical risk. And we can have an error term on the right-hand side. If we do uniform approximation, it will be a non-diminishing error there. So yeah, so a major part of our work is to find a way to approximate these popularities. And we first observed the definition of this QJ, which is summation of the conditional densities. And there are two issues here. So the first one is that we don't know the true similarity function. And at this moment, we just assume we have one, and we will tackle this issue later. And the second issue is that it's kind of a chicken and egg problem. So we need this Q to estimate the integral, but here to approximate these popularities, we still need to know these partition functions. So here we just apply the multiple importance sampling Monte Carlo again to derive this. So this is a fixed point problem, and probably we can use some root finding algorithms like Newton's method to solve this, but it's very challenging because this root finding problem is from Rn to Rn. So if we want to apply Newton's method, we need to compute the inverse of a Jacobian of size n by n. So it's not very efficient to directly solve this fixed point problem. So we use a different approach. We use a non-parametric method. So first step is to do some change of variables. We construct the approximation Q tilde by n-dimensional zeta j, and zeta j star is solved from this convex optimization problem. And for this problem, it's easier to handle this because we can do stochastic algorithm to solve this. We can do randomized coordinate descent to reduce the per iteration cost. And we can have some convergence guarantee on that. So we prove that if we follow these two steps, we can find the approximation of the real Q. Here, the Q tilde is our solution, and it's a solution of the fixed point problem.
And we conduct some toy experiment to verify our approach. So here X is upper disk in two-dimensional space, and Y is the unit square. And we define the conditional density to be like this. And here the partition function can be exactly computed so that we can quantify the error there. And here the similarity function is the simple one, just the inner product. And we collect the data set by first uniform sampling from the upper disk, and then we sample Y from based on each xi by rejection sampling and this conditional density. So we can show that our method can approximate the true Q, and we don't need to compute the inverse of the n by n Jacobian. And we also compute the generalization error. So here MLE is the one using the exact partition function. So here it used the exact integration result. And GCL is the contrast loss. It used the uniform approximation. And our method can almost recover the curve of MLE, and is much improved compared to the contrast loss, the uniform approximation. Now we want to return to the DPM problem and also self-supervised learning problem. And here the approach is that we first solve this lower level problem and plug in to the Q tilde, and we plug in Q tilde to the empirical risk. Now let's return to the issue I mentioned. So we don't know the underlying true similarity function here. Then we take the alternating minimization approach. So in each iteration, we first update the model parameter while fixing zeta to its previous value. And we can do what we did in the contrast learning algorithm, like the SimClear. And then we update zeta while fixing the model to its previous iterate. And this is the convex problem we can apply the randomized coordinate method to solve this. And the interesting part is that it has a nice margin interpretation of the W step, because we can change a variable back here. So we plug in Q tilde and we get the equation in the lower part. So now the zeta can be viewed as a negative margins. It's individualized margin for each data point. And it kind of makes sense because when it is optimized, the zeta has some meaning. So larger zeta means higher popularity. And we assume that the popular data is more likely to be a false negative. So if the zeta is larger, so we can prevent that false negative to be pushed away from the anchor data. So it's kind of, we hope this can tackle the false negative issue in the self-supervised learning. And we did some experiment on the bimodal pre-training, and we pre-trained our model on the CT3M and the CC12M datasets, and we evaluate the model on the downstream tasks. Like we have 2 cross-model retrieval datasets and 2 classification datasets. And we have some baselines like CLEAP, CyCLEAP, CCLEAP, and here the SACLEAR is some algorithm that was proposed for the small batch size setting. And our algorithm is also used some technique from this algorithm. The first we look at the validation curve. So it converts faster compared to the SACLEAR algorithm across the training epochs, and also show the task performance. And on average, our model can improve by like 1%. We also did some experiment on some other data set like ImageNet-R and some data sets from the DataCamp, but we didn't include it here. So lastly, we grabbed some images with the top learned popularities and small learned popularities from the CC3M datasets, And we try to verify the intuition that the tilde cube can learn the popularity of data. So this is the top 10. They are quite popular, related to popular topics like human beings, flowers, and pets. And if we look at the bottom 10, it's related to topics that are not so popular in humans' daily life. So it's kind of verify the intuition that the tilde cube can learn the popularity of data. Yeah, that's all. Thank you for listening.
Well, thank you.
Thank
again. Let me up a second. Yeah, thank you so much. So just a reminder, tomorrow we will be at a slightly different location, just a little bit down. Let me show you. We have some beautiful pictures of a beautiful building. Oh, you did it. Fantastic. All right. Yes. There's circles and arrows, and that's what we love. So we're gonna be from the first circle that the arrow starts in, move all the way over catty corner to this fancy new building, or is it new? Fancy building. That looks like that. So there'll be lots of nice glass to look out of for everyone. So at 9 a.m. So thank you all. We'll see you tomorrow morning, and let's thank all our speakers one more time. Thank you.